Uh, can you hear me? Okay. Um, okay. Hello. Uh, so my name is Chung-Kil Her at Seoul National University in Korea here, and welcome everyone to PLDI and also to Korea. I think many of you, I think that this is first time to Korea, and I think this is a kind of beginning of summer, but I think luckily the weather seems okay and getting a bit hotter because of global warming. But anyway, so it's good. And this logo, PLDI, is made of Korean alphabet. I will talk about some interesting story about Korean alphabet and computer science in the business meeting on Thursday. So if you are curious, please come and hear. So I will also make like slides and maybe 3-4 minutes talk about that. And first of all, I'd like to thank all the sponsors, and in particular, platinum sponsors, Apple, Amazon Web Service, and Huawei. Okay, thanks a lot. And first, we have a Discord channel, so I think all of you received the email about this. So otherwise, you can also go to this link, and there's many things going on. Virtualization questions and also socialization. You can find a friend who you want to have dinner together or something. If you feel alone, you can also say something. So many also virtual things are going on here. Okay, and then I'd like to thank Nuno Lopez at IST in Lisbon. Where is he? Somewhere, I found him before. And he wrote very fantastic article about, post about a travel guide for Korea, Seoul. Transportation, money, payments, food, tourism, sightseeing, culture and etiquette, health and safety. So this is on the main page of PLDI as well, or you can also take a picture of this one. So he is more expert than me about Seoul. You can ask him why. He had something before, a few years ago. And so this is how he looks, but at the age of less than half of current age. So you have to apply some image kind of processing to find him. But this is the only picture I could find online. Okay. So, and then I'll talk about some schedule and hotel information. So for lunch, it's a buffet, and it's going to happen in 3 locations. Basically, 3 places where PLDI sessions are going on. We have 3 per session. So first session is in Grand Ballroom, and then lunch will happen over there, behind the partition. And that's for 200 people, but you have to somehow distribute well. And then if you go upstairs, first you will see this discussion room and resting area. There is some glass door and wall. Inside there is a big sofa, and there are also 5 small rooms where you can discuss. So if you want to have some discussion meeting, you can go there and then discuss. And then you will see some flower rooms, lilac, tulip, and so on. And then they will be merged together to have a big room. So where PLDI second session will be going on. And then if you go further up, then you will see big orchid room. And there is a third, second, there is no order actually, right? So anyway, there is another PLDI session going on, so you can find the information on the schedule page. And so we distributed the food around like the grand ballroom. We have food for 200 people, and flower rooms 150, and orchid room 100. Okay, and so that's logistics and then the lunch. Okay, and also several people asked where is a garbage bin, but in this hotel somehow interestingly there is no garbage bin, and they are running automatic garbage collection system. So you can put any garbage on any table or some decent place. Then you don't know exactly when it's be collected, but there are hotel staffs always working around and collect them and dispose. But in an urgent situation where you want to immediately free your garbage, the only place is go to toilet, and there is a very small, like some place you can throw your garbage. Okay. And then today's events. At lunchtime in Lilac Room, the LGBTQ plus people can get together and they have lunch. But the food is the same. You have to get the same food from the buffet place, and then go there, and then you can have a lunch together. And and then also for students, in the break time in the afternoon, basically 3:30 to 4, it's also basically the same food, but you can go to Grand Ballroom 1, which means over there, behind the partition, and the students get together and then somehow talks. But to somehow motivate or give incentives, we prepared some Korean rice cake, only for students. Okay, so do not steal. Okay, all the people, please not steal. Anyway, so you can go and eat additional dessert, and then you can talk. And then at 6 p.m. We will have a reception in this place, Grand Ballrooms, and we will provide the food and beverages. That's exactly the same, not exactly the same. So maybe foods are some different kinds, but same, basically similar to yesterday's reception. So we provide 2 receptions, and if you missed the yesterday's reception, still you can come today's reception, and then drinks, have a drink and food. But food is not for meal, like a quantity, some small food. Okay, and then from 7:30 there will be some special dinners for special people, like a woman's dinner and PLDI steering committee dinner. So anyway, the reception is for everyone. Okay. And then finally, for me, we are also belong to ACM, and we follow ACM policy against harassment. So it basically means that do the right thing to everybody, other people. Okay, and then if it's unclear what are the right things, you can Google search ACM policy against harassment, or you can go to this link and then read the details. Okay, and then it's now Sukyung's turn on.
Hi everyone. I'd like to introduce Plan Cares to you. I am one of the members of SIG Plan Cares, and it's available to support community members who have experienced harassment, discrimination, or bullying, and to provide information on how to report unacceptable behavior. So if you are interested in the details, you can go visit our website. And here's the list of members. And people with these yellow boxes are supposed to be in this room. So if you want to talk to one of us, you can just come to us. And actually, General Chair kindly listed our names and email addresses on the front page of PLDI, so you can check the list there. And the second thing is that, again, I'd like to introduce SIG Plan M. It's a long-term external mentoring for all aspiring and current PL researchers mentoring program. And so we have these awesome members, and you can see the map. Those purple areas are meaning that we have mentors and mentees. So currently we are covering 59 countries with 270 mentors and 360 mentees. And I think you had a chance to register either as a mentor or mentee. So you are welcome, and we'd like to have more mentors and mentees. Thank you.
Okay, everybody. So welcome again to PLDI. We're so excited everyone's here. It's my job to introduce our illustrious first keynote to kick things off, which, if you could come back on stage, is Sukyung. As a brief introduction, Sukyung runs computing at KAIST, so he's big boss there, in charge of a lot of stuff. Has done incredible research across many of the most important languages that we, as a computing field, depend on, working on ways to bring rigor and precision to the way we think about and work in those languages. And I think that the talk's going to be really exciting. It's sort of a bigger perspective of, not just pushing the frontier so you can get another paper, but how is the research that we do actually make the world a better place? How are we alleviating suffering and helping those around us, which I'm really excited to hear more about. Also, I think one thing I wanted to highlight was Sukyung's service. So if you go to the researcher.org profile and you start scrolling down, this, most people have like a page and a half. Sukyung's just keeps going, right? So basically every SIG plan, every SIGSOFT committee, organization, many satellite events at all of these, Sukyung has always stepped up. Tons of leadership in mentorship, and it's just really an honor to have you. And so we're so excited to have you kick off PLDI. Let's all welcome Sukyung.
Thank you for the nice introduction. It really feels good to be on this stage. So, hi, I'm Seokyeong, and it is my great honor to give a keynote talk at PLDI. And the title of my talk is Programming Language Research for Technical and Social Good. This is the official educational motto of Korea, read 홍익인간, which means to broadly benefit the human world. So as a little kid, I was brainwashed with this motto. And I had a dream, like when I become an adult, I'd like to help people. I'd like to broadly benefit the human world with my own work and my own skills. And it has been long-term pondering for me. How can I help people with PL, right? As a PL researcher, as an educator, as an adult, how can I help people? So that was my long-term endeavor, and today I'd like to share my endeavors until now. So while preparing this talk, I met this article last week. The author asked, what is the fundamental purpose of higher education? And he believed that the purpose was best expressed in the American Association of University Professors' influential 1940 statement on academic freedom, which is, institutions of higher education are conducted for the common good. And it was very nice to see that we are on the same page. Oops. So today, I will talk about what PL can do for technical good and then for social good. So as you can guess, the second part is going to be brief, but let's see. And inspired by our motto, to broadly benefit PL users, that is developers, our team has been working on bringing our PL research into the real world by using our own technology, which is mechanized language specification. So our group has been working on mechanizing language specifications. We've been developing lots of tools by using mechanized language specifications, and our tools and our technologies are successfully adopted by two real-world programming languages, JavaScript and WebAssembly. So WebAssembly, in short, WASM. So I will share our experience with that with you. So what is a mechanized specification? Mechanized language specification is a language specification that defines the syntax and semantics of a language, but as executable data that programs can manipulate. Because the spec is executable, we can type check it, we can test it, analyze it, and verify it just like other programs. Because it's just a program, right? We can apply any existing PL techniques, but at the same time, because it's a specification, it has very specific characteristics that we can take advantage of to find new interesting problems. There are new technical challenges which provide opportunities for novel solutions. And this mechanized language specification is the single source of truth. I may use this term, single source of truth, multiple times during my keynote. What that means is that it is the only one description of the semantics, and out of that, we can automatically generate many artifacts. And because we can generate that from the specification, they are guaranteed to have the same semantics with the specification, right? Correct by construction. And thanks to this automatic generation, it is scalable and efficient to language growth and subsequent spec changes. As you know, all those programming languages, there are so many, right? And they are growing. And in our school, I teach the programming languages course every semester. Even though I am the head of the School of Computing, I'm still teaching the course. And one of the homework is to listen to Guy Steele's 1998 UPSLA keynote. The title is Growing a Language. So that's the main core of programming language design, I think. But anyway, so that's mechanized language specification. As I said, we can generate lots of tools out of this mechanized language specifications, like parsers, interpreters, compilers, analyzers, fuzzers, you name it. And now, among those tools, our group is particularly interested in lightweight formal methods, especially tests. So by using this mechanized language specification, we can efficiently generate diverse and interesting tests. It's efficient because we just write the semantics once in one format and the others are automatically generated. It is diverse because that's a data. We can look at that. We know how to look at data, right? How to analyze programs. So we can see, we can explore the possibilities that we couldn't see before when the specs was written in prose, in a book, right? And it is interesting to see that now that we can go further than before, we are encountering new issues, real world problems that we've never experienced. So I will tell you our experience. And before that, recently, I've been hearing about the emphasis on lightweight formal methods, especially property-based testing, over and over again. Benjamin Pierce, who wrote this Types and Programming Languages textbook, he is emphasizing the importance of testing these days. He even said that before you prove your theorems, you do better want to test them, right? And so with this figure, he claims that this property-based testing, it requires small amount of effort, just the same order of magnitude effort with unit testing, but with high quality by using the similar specifications with formal verification. So he's now using property-based testing for rock implementation and all that. And Mike Dotz from Galway, he shared what he learned trying to do formal methods in industry in Galway. And he emphasized the cost-effective lightweight formal methods like fuzzing and property-based testing in real world. As you know, Galway is doing lots of DARPA projects, right? And he even added that many systems do not even do the top 3 cheap techniques: code review, documentation, testing, and CI/CD. If you do that, then you are good. And yesterday, one Google researcher, developer, also said that if you are doing testing, you're good. So we can do better than that. And finally, last month, another CACM article shared the systems correctness practices at AWS. Again, actually 10 years ago, there was another CACM article from Amazon about Amazon's formal methods, how they use that and all. I was so impressed by the article. 10 years later, they are sharing what they've been doing, and now more emphasis on lightweight formal methods like property-based testing. So it looks like it's trendy that lightweight formal methods are being used widely and very helpful. And our group has been working on lightweight formal methods by using the mechanized language specification. So our work on JavaScript is called ES-Meta, and WASM for Spectac, and I will share our experience one by one. JavaScript. You know what? JavaScript has been the #1 programming language until 2023. Now Python is the #1, maybe because of machine learning, right? But #3 is TypeScript, just altogether JavaScript, right? And the top 5 languages most commonly used in repositories created within the last 12 months on GitHub, JavaScript. So even though we may not like it, JavaScript is leading the world still. And May last year, ECMA TC39 announced this. So JavaScript its official name is ECMAScript because of some political reasons. And ECMAScript is maintained by ECMA TC39. And TC39 announced that our tools on this JavaScript manipulation is now, it was officially adopted by TC39. And that's called ES-Meta. Actually, that was integrated in 2022. And all the details are in our CACM article last year. So that's one adoption story. And another is WebAssembly. After adopting this JavaScript work to the JavaScript community, we contacted the WASM community. I will tell you a little bit more details in a minute, but here is the setting for what's what we have been doing. So WASM is a binary instruction format for a stack-based virtual machine designed as a portable compilation target for programming languages. This language is very well known to be rigorously written. Language specification is beautiful. It's going to be music to your eyes because you are PL researchers. For a language construct like the binary operator, the specification describes its syntax and it describes its semantics rigorously in two ways, in prose and then in formal rules. In prose, it's very easy to follow step-by-step instruction. Number one, assert this property. Number two, pop the value from the stack. Pop the value from the stack. Do some calculation and push the value to the stack. It's step-based machine, right? So very clear. You know what to do. You know how to implement this semantics. At the same time, in this gray box, we have operational semantics, informal rules, right? And the spec editor of WASM, he loves formal rules. He don't even want to read this part. So if he has an option, he'd like to have only a spec with formal rules. And the English phrases are compiled or translated from these formal rules for the developers. So anyway, so WASM was really well written. The spec is very well written. The community group is very formal. In March this year, the community group announced that Spectac has been adopted. 2 weeks ago, the WASM community group voted to adopt Spectac for authoring future editions of the WASM spec. In this posting, the editor explained what Spectac is, what it helps with, and why it takes WASM to a new level of rigor and assurance that is unprecedented when it comes to language standards. Right? And you can go visit and read the discussion. And the team had a poll, adopt Spectac as the toolchain for authoring the WASM spec. And there are 15 strongly in favor, 17 in favor, and 1 neutral. So that was adopted. And this thing shows that not only that our tool is cool that they got adopted, not only that, but also they have a very well-defined process to make decisions. So I'm going to come back to this point later. Okay, so with these experiences, we've learned a lot. And here today, I'd like to share some lessons that we learned along the way. The first lesson is different languages have different demands. Yeah. So this picture shows that JavaScript specification, that ECMAScript specification has been released. Yeah, I know their face, right? From 2015, the spec is released every year. And the spec is more than 800 pages. So like us, JavaScript language designer, not really designers ourselves, developers of the toolchain, we need to understand that every year coming language standard. So like an analyzer developer need to understand the semantics and then build some tools. So it was like onerous work. And Jihyuk Park, who's sitting here, back then my PhD student, he came to me like, we need to change this. This is not for a human being to do. And I was like, okay, yeah, let's try that. And Jihyuk is now at Korea University. What can you do about it? So we worked on JavaScript. We read every single line of the ECMAScript language specification. We knew that by heart. And it's like, oh, right, it's written in English, but in a very regular format, right? Again, number one, let array be the result of this function call. Let something be the result of whatever, and call this function. So even though that's 800 pages, the number of English phrases is 100 or something. So, that's even before the large language model era. So we were like, we can just read the sentences and compile it to our own domain-specific language. So that was Jihyuk's crazy but cool idea. And by using that observation, we came up with our own DSL called Intermediate Representation for ECMAScript, ILES. And this is our language. If you look at the language, this is not for JavaScript program, right? This is not a programming language to describe JavaScript, but it's describing the semantics of JavaScript, right? So this language is just compiled version of the English phrases in ECMAScript, and that's very high level functional language. So we can discuss that later. So in this language, we use JavaScript values, JavaScript ASTs as values. And from this text, we can compile it to some program written in ILES. And now that abstract semantics, how to evaluate this array literal expression in JavaScript is a function in this language. So this is the main thing. And now that we have this spec and extract the syntax and semantics out of this prose specification, we can generate parser and an interpreter automatically. And because the interpreter was extracted from this spec, that's just the same, right? Their behavior is the same by construction. So by using this, we just try to compile the existing 6 versions of the JavaScript and compiled about 96% successfully. Then people ask, what about the remaining 4%? What are they? They are written in a very weird way, like regular expression chapter, right? And the author of this regular expression chapter told us that he wrote the implementation, he wrote the regular expression implementation in C++ first, and then compiled that to English. That's why that's written weird, and we don't want to handle that. And we picked the latest version then and filled in the missing 4% manually and ran it, evaluated its correctness by using the official test suite, and 100% was passed. So wow, it was a big step for us. And in a nutshell, this ES meta, it takes a specification written in prose. That's the input. Here, that's the single source of truth. Not a computer-friendly IL or DSL. This ECMA 262, that's the name of the spec. That's the input, and it extracts parser and interpreter and runs it. That's because the way JavaScript semantics is written is really high-level functional language. It calls a lot of functions with first-class continuations. That's why we designed this language in this way. But WASM is different. Again, after delivering this ES meta to the TC39, we contacted Andreas, like, oh, hey, Andreas, someone told us that we'd better try WASM. And he was like, oh, yeah, come visit our doctoral on the foundations of WebAssembly. Okay. And the very first morning, Andreas gave this presentation. He's like, yeah, WASM 1.0 was released in 2018, 2.0, 22, and he'd like to release the spec every year. Oh, we've heard that before, right? So that afternoon, I gave a talk and explained our work. And on Thursday night, we got together and started working on Spectac. So that's the beginning. So Conrad is here, but he was taking the picture. So not in the picture. So again, WASM is really well designed. And the WASM community group is really thoughtful and careful. So in order for a language feature to be standardized into the specification, you need to provide 4 artifacts. The number 1, formal rules describing the semantics in LaTeX. Number 2, describing that in prose, in restructured markdown. Number 3, implementation of that feature in the reference interpreter in OCaml. And finally, test suite to test the implementation of the feature. Wow, yeah, very picky. So in order to have one feature to the WASM language standard, it has really good checking. And the standardization process is not requiring this yet, but they'd like to have mechanized definitions and mechanized proofs. Yeah, it's really advanced. Then, so it's really good, but it takes a lot of time. And a spec editor is kind of a bottleneck because they need to make sure that everything is going well. So in order to make this pretty rendered version of the spec editor needs to write this. The entire thing is that restructured markup. Why they are using it, I don't know, with some political reason they said. And these Greek letters are now in LaTeX, right? So that's a bit much of work to write this semantics. But in order to formalize this large and growing language, there are many challenges. The prose is written by Andreas in these formal rules and then translated from there. Right? The prose is a compiled version from the formal rules. So it's labor-intensive, tedious, and error-prone. And for political reasons, as I said, restructured text and all those not that common tooling, so there are many hackings around. And code reviews are painful and unreliable. Do you want to see the differences of LaTeX? Oh, I don't want to do that, right? So the spec differences for a single proposal is huge and not really human readable. And finally, they'd like to have this mechanized formalization, but it takes a lot of time. It's not that easy to catch up with this speed. So this is what we did. These 6 lines, right? These 6 lines is the input that's written in the Spectac DSL. If you write the semantics once in this, then all the others are automatically generated. And we call that Spectac. It's a domain-specific language for defining the WASM semantics and authoring the spec. Again, it is the single source of truth. You describe the semantics in DSL, and the others, mathematical rendering, prose description, tests, and interpreters are come that for free. It is easy to write, read, and see the differences, right? And review with meta-level error checking. It is not that ambitious. It is not a theorem prover, just a preprocessor. Then people ask, like, oh yeah, I've heard about similar stories. What about K? What about SAIL? How about Radix, right? Yeah, there are many awesome language manipulation frameworks. This Spectac is an in-house tool for WASM specification. We are intentionally specialized to our use case. All the specs meta notation is built in, and nothing more than that, we hope. And the backends can make domain-specific assumptions. From this too general DSL, we'd like to generate LaTeX and interpreter and tests. There are assumptions. So yeah, that's kind of limitations. And we control the implementation. We do not want to depend on the tools that someone else is developing, right? But at the same time, a long-term maintenance is an open problem, and we are trying to address this issue as well. But this worked for us. So this is the overall architecture. The Spectac DSL describes the semantics in a declarative style, just like inference rules. The DSL is just inference rules. Then we have some checking, a little bit of checking, and compile that to external language. Then it's still declarative. It's still like inference rules. So we can generate LaTeX backend really easily from there. But you know that when you write calculi paper and pencil, then we make mistakes, right? There's a function parameters and there's function call, and you need to match the numbers and all that. If you have sequences over sequences, then you need to check the numbers, right? Our tool can do those checking. So after those checking, we compile that to internal language. And the interesting thing is this animation. We translate this declarative style to algorithmic style. That's what we call by animation. Here, briefly speaking, we reduce these ambiguities. As you can see, in the inference rules, we have multiple premises, and the rules don't say what to do with them. which order. And when you have x equals y, it could be equality checking or binding. And even x equals y, if it's a binding, it could be binding x or binding y, because we are ambiguous in formal rules. So this animation step resolves those problems so that now we can describe the semantics in an algorithmic way. Number one, do this. Number two, do that. That's how we can support both formal rules and prose description. And once we have it, then it's slightly easier to make prose specification and the interpreter, and now we can generate tests by leveraging this data. Okay? So using Spectac, this long description gets to this. Very short. Not only that, we can mix handwritten description and automatically generate text. Here, there are some markup saying that splice in the automatically generated text here, so that we can incrementally replacing the specification. So in a nutshell, Spectac is a bit different. It sounds similar, but the single source is now Spectac DSL, which means that the WASM community group needs to make a big decision. They need to change their way of writing the spec. With ECMAScript, we didn't even think about it. We were like, okay, ECMAScript is the God. We need to follow that, and how can we help them, right? With this WASM, the WASM community group was so friendly and helpful, and they wanted to change the thing because they were suffering with the current status, right? So that's the main difference, and we can talk about the differences later more. And the details of this work is described in our PLDI paper last year. So again, the first lesson is different languages have different demands. JavaScript, ECMAScript 262, ECMA 262 in prose is the single source. Algorithmic prose is important for JavaScript developers and testing. Our group has been working on JavaScript analysis since 2010 when I joined KAIST. And the very first thing that I learned from working with JavaScript community is developers are the king. In this, ECMAScript, as you know, there's version 3 and version 5, but there's no version 4 because the developers vetoed that. So every language is different. And with OWASM, now I'm concerned that this PDF is an old version, but let's see. Yeah, WASM. Spectac is a single source, and it has declarative formal rules are important for formalization and proofs. For the other languages, we've been lucky to work on JavaScript and WASM. They have specifications, and their specifications were rigor. But now, the other languages may not have specifications. And when you say specification, people may think differently, right? Some people think a set of input and output pairs is a specification. So we need to talk. So there's often no specification, and algorithmic formal rules or pseudocode may be preferred. And Ralph prefers pseudocode description for the Rust language specification. And so we'll see how that goes. And the second lesson is specifications are not oracles, meaning that, it doesn't work well. They have bugs, right? This is a ECMAScript, and I'm not going to go into the details, but this math.round is a built-in function in JavaScript. And in JavaScript, X can be anything. X's type can be a string, Boolean, number, or object. And in this code, this toNumber function tries to convert this X to a number. If it's success, then it's going to be a number. Otherwise, throw an exception. So after this number 2, that should be a number. And we should use n. But from number 3, the editor used X, which signals a type error. It was actually happened in an internal version of ECMAScript. So this is a kind of a bug in the specification. And in ES Meta, we have several tools, but briefly speaking, we can type check the specification, and we can test the specification. So JSTAR is a tool to analyze the JavaScript specification. Because it's a program, we have concrete semantics of that. When we have a concrete semantics, we can have an abstract semantics of that. It's kind of an abstract interpretation of the specification, specialized to type information. So that's our tool, and we found many errors in the specifications and implementations. And Jest, it's to generate test data, again, out of the specification. And I'm skipping the details because they are papers and you can read them later. And using Jest, we could find 27 bugs in the specification and 44 bugs in engines. So maybe that's only for JavaScript? Not really. Even though WASM was really well written and all those checking and standardization process, we still have bugs in WASM specifications and more in the proposals, right? And these are the bugs that we could find by using Spectac. There are type errors like missing recorded fields in formal rules, semantic errors or prose errors. We are familiar with missing some names, right? Defining names before using it, and lots of editorial errors. So by having this kind of mechanized language specification, we can not only test the specifications, but also make really cool tests that are easily being missed by manually writing tests. So for example, this is a bug that we found in JavaScript core. Even though the WASM proposal, each of them is really well tested individually, right? But in WASM 3.0, we have several proposals. So this is an example that JavaScript core has a bug when it appears only when both garbage collection proposal and the SIMD proposal are used at the same time. Okay. Another thing is that the WASM has three kinds of specifications: the core specification and JS API and JS Web API, like that. And the core specification is really well checked and tested, but maybe not JS API. And whenever I meet those people, they were like, oh yeah, look at those problems. There are many bugs. And oh yeah, and this is one bug that we found in V8 that happen only when this WASM code is called by a JavaScript function. So there is these interactions. And finally, different implementations, like different engines or different browsers, implement different sets of the specification. Why? Yeah, I couldn't understand that in the beginning, but now I'm understanding. The WASM 2.0 is the official version, and WASM 3.0 is soon to be the official version. In between, there are many proposals. And these JavaScript developers and WASM developers are really diligent. And they'd like to use them even before those features are standardized in the specification. Then browser implementers are really diligent to implement them before they are standardized in the specification. So yeah, these are examples. Maybe I will show you later. But so we found errors in various browsers, and it might be difficult to find them. So in WASM, there was a proposal called profiles, meaning that even though WASM is really big, maybe we want to support only a subset of it, depending on the applications. So that's profile. It has pros and cons, obvious pros and cons. It may fragment the language, and there are going to be some discrepancies between implementations. So it has been discussing for like 3 years. But if the community group wants to take this, then Spectac will be really helpful, in a sense that instead of making each test set for each implementation, we can just change the specification and generate the tests targeted for those implementations. Okay, so specs are not oracles, and JavaScript ES Meta statically analyzes the specification and generates tests. WASM does more than those things. And I believe that now that those languages with rigorous specifications have these many bugs, then we can find more bugs in languages without specifications. So that's our belief. And now the third, we have to work with the language community. At ECMAScript, we were happy and we were lucky to have these awesome editors. One of them is sitting here, and we contacted them and they were kindly invited us to give presentation. So we made a presentation, and you can read the actual discussion there. And yeah, someone said, this is the maximum that I've heard in terms of positive feedback for a presentation. And even on top of that, can we just move these tools to stage 4? Meaning that in this standardization process, there's a stage 0 to stage 4, and then approve. They are asking to just take it. So that was a big success. And I really wanted to emphasize that this was possible thanks to the prior work, right? This is our picture about citation, about JavaScript analysis work. And these two little boxes are the very first type system papers by Sophia and Peter Tiemann. On top of that, there are so many papers, right? And on that, I wrote some names. Lambda.js by Arjun and Shriram, KJS by Taejun and Grigor, the K framework, and Thais from Anders Miller, JSI from Ben Hadekov, Walla from IBM TJ Watson, JSOL and JCert by Philippa and Ellen, and Safe by our team. There are all these people working on JavaScript analysis. That's how we can convince the community, I think. And 5 years before we made a presentation, Philippa made a presentation at the TC39. They were exposed by this peer research. And yesterday, I learned that before Philippa, Arjun and Shriram gave a presentation at the TC39. So thanks to this prior work, we were lucky to have this opportunity. And WASM also, the WASM standard, there's only one editor, Andreas. And it's not only that we need to convince Andreas, but there's the community. So after meeting the people in March at Doxto, in October, we gave a presentation in front of this WASM community group. And thanks to their work, we could make the adoption. Yesterday, here, we had this workshop, RPLS. It was really well received. The room was packed and people were standing back all the time. And this was the last session with a panel. And Ralph about Rust, and Xiao Hong about the K framework, and Jonathan about P4, and Michael about ECMAScript. There are many cool things, and I strongly recommend you to watch our video later. And the quote that I got from Michael is, ES Meta doesn't cover everything. It doesn't cover modules, it doesn't cover atomics, but it's okay. It doesn't have to cover everything to be useful. 96% is much better than 0%, right? And we don't need to report bugs because the people in Korea University already know by using ES Meta. So efficient, right? Another thing that I wanted to steal from Michael is we need to share the same vocabulary. We are working on JavaScript. We are working on WASM, but in academia. In a relatively safe place, I guess. And when industry is thinking about adopting some technology from academia, they feel a bit risky because we know, when students graduate, who's going to maintain the tool, right? So these things. So when we deliver ES Meta to TC39, the first thing they asked us is like, can you rewrite your implementation in JavaScript? What? That's written in Scala. So we were like, we'd like to be good people. So we tried TypeScript for 2 weeks and forget about it. and then now GX group is maintaining that. So we have to work with the language community. JavaScript, they have this TC39 and the rigorous TC39 process for making changes to the specification. WASM, it has this W3C process to describe how feature proposals progress through the standardization process. For the other languages, we are looking at them. The governance even is not clear. Whom do we need to talk to, right? And the final lesson is, it takes a lot of commitment. Look at that. Our first GSTEC paper was published in 2020, JEST 2021, JSTAR 2021, and we were so happy. We contacted the editors, and we had the first meeting in November 2021. They were also excited. They invited us to the plenary meeting in January 22, and they were excited again. You saw that, right? And it took 10 months to make the integration, thanks to Jihyuk and my prior students. And after that, we had another JSaver and JEST paper. And last year, we have Kekun paper. Here, this picture does not include everyone, but a gang of students had to work on this. And Spectac, it's a bit different. We met the people at Doxtual in March 2023. We had the first presentation in October 23, and our first paper was last year's PLDI. And then the committee was really fast. Last June, they had this conditional acceptance, and this March, they officially accepted the tool, and now we are integrating it. So this is like a whole lot of commitment. But it opens the door to new opportunities. This is our PLDI'25 paper. I really like that because when we generate test data, we talk about those testing criteria and coverage metrics that we learned for longer than 50 or 70 years from this SE community. But this is a new kind of program. The spec data is not really a usual program. It has very specific characteristics that we can explore how to test them better. And this one was also I learned yesterday. Jihyuk's group is going to have a presentation next week at FSE. This awesome tool. This is a very proud moment of ex-advisor, right? So take a look at them. It's really cool. That's all thanks to the mechanized language specification. And finally, our group has been finding lots of errors in WASM implementations. And sadly, I cannot share the details because it's under review, but I hope to talk about them more later. So we have many FAQs, like, can I use Spectac for my favorite language, like Go and Scala, OCaml, Rust, those questions. Is Spectac DSL readable, usable for developers? Really? Do you really think that the DSL is good for developers? Can we use English as the single source of truth? Those inference rules are too heavy for me. Can I use just English phrase? I just say something and the tool magically makes some code? Can you mechanize 5G, 6G specifications? It's for real. And this is from my colleague at Keynote in the electrical engineering department. From the very beginning of our GSTEC paper, he came to us like, can you please make this 5G specification mechanized? And he visited us again this year to give a presentation to ask for that. So there are many things. To support a new programming language, we have many things to address. And I'm not going to go over into one by one, but it's still ongoing research, and we are learning along the way. So to sum up, we believe that specification mechanization is an enabling technology to automatically generate tools for language semantics and to help us to explore new possibilities. And our work on ES Meta is now mainly taken by Professor Jihyuk Park at Korea University. Our work on WASM Spectac is now split into this spec integration led by Andreas, and mechanized formalization by many colleagues, and lightweight formal methods by our group. And our group is also working on some other programming languages, and hopefully we can talk about that later. And now, finally, the second part. Yes, what PL can do for social good. Yeah. This picture was taken 10 years ago, in 2015, at PLDI with me and my ex-Sun Labs colleagues. I worked in some microsystems from 2005 to 2009. And I got my degrees, bachelor's, master's, and PhD all in Keynote. But I didn't know that back then. I didn't know that Sun donated Sun Spark Station 5, I guess. I'm not sure, but 5 stations to Keynote. And there were some students who were so grateful, so they made a club and named Spark. That's the club. And this person is my college friend. he was one of those founders of the Sparks Club. And now he's a rich person. He's running a company called Crafton, and now Crafton is the silver sponsor for this PLDI 2024. And he keeps talking about how he is grateful for KAIST and the Sparks Club and Sun Microsystems for him to be in his current stage. And this was one of the main motivations that when Talia made this SIGPlan M program and asked me to be on part of this advisory board, I felt like, oh, this is my turn to return what I've received when I was a student. And now we can share what we've learned and what we've received to those purple map, right? So I was happily involved, and I'm still on advisory board and a mentor. We even wrote a CACM article about this, long-term mentoring for computer science researchers with a similar group in the computer architecture community. And I was also recruited by Catherine and David about this SIGPlan Cares. I didn't really know about this committee, and when they recruited me, I had to study, and I was like really impressed by their passion. I learned a lot from these committee members, and I was also nicely surprised that there are many CARES committees in other SIGs. It was very impressive. So all these education helped me to make some movement in KAIST and in Korea. In Korea, we do not have an anti-discrimination law. So it has been a long battle with the government and people who are against it. Why? I don't know. And KAIST is not an exception. So 2017, we established KAIST Social Inclusion Committee, and I was the founder of that committee. And in 2022, we made KAIST Declaration for Diversity and Inclusion and made this video publicly available and got malicious comments. Right? And one of our main representative activities is to make restaurants for all on campus. We got civil complaints. We are still getting them. But thanks to our brave actions, other universities are following, and other universities are making these restaurants for all. This is just one instance, and we are trying to make differences. And personally for me, that's all educated by this community. And I'm recently helping Kakao Impact. Is a non-profit organization. This organization is to connect technology and platforms for solving social issues. We are running courses at KAIST, and this course is now being opened in other universities. And we are trying to help computer science students to be exposed to social issues and learn that we can solve real-world social problems by using our technology. So I admit that I'm using the term PL too broadly here, but now I'm so grateful that this ACM's core values include diversity, equity, and inclusion, which makes me feel really proud to be a member of this community. So this is our journey to make this world a bit better place using our technology. And I'd like to share my sincere gratitude to many people I owe to, especially my beloved students. Thank you for listening.
Thank you so much for the fantastic keynote. We've got a few minutes before break for questions. So anybody who is curious about anything in the talk, please step up. We've got a couple of mics running, so introduce yourself and ask things. Maybe to kick things off, one thing I was curious about, you talked about growing a language, and a lot of times we think about that in terms of adding features, but also sometimes we deprecate and remove things. So are there any aspects in these projects that have come up that have been challenges with deprecation or removal, or is that something you're looking at moving forward? Or?
Right. The first paper, I think, instead of the introduction of our framework, the first paper we did was to how to safely remove the with clause in the JavaScript language. The with statement is the only dynamic scoping language construct in JavaScript. So we wanted to remove it. So by having this mechanization, we can have lots of combination of testing, and we may be able to show that this feature is not really necessary or prove its duplicative feature.
Super cool.
Okay, hi, I'm Long Fei Chiu from Yale University. Very exciting work. I'm curious, so when you started the ES Meta project, I think you said that a lot of the parts of the specification is already quite suitable for formalization. So are there aspects of the specification where it seems to be well defined on paper, but it turns out to be very difficult to formalize? For example, in C language and C++, they have lots of places where they say it's undefined behavior, but then there are corner cases where it's difficult to tell if it's triggering the defined behavior or not. There are such challenges in building the ES Meta project.
Thank you for the good question. So the second part, like about this undefinedness, even ECMAScript has this implementation dependent or host environment dependent things. But it's good if we have explicit places to name them. Then we can abstract that away and do some other techniques. So that's one thing. Another is that was it 2015? Some year before and after, the style of writing the semantics was changed in ECMAScript. Before, it was not really clear about continuation, but now it uses first-class continuation, and you need to rewrite the specification. If you formalize it manually, maybe a year or almost a year, but by describing this semantics nicely, we can do that if we take a kind of DSL first approach. But again, think about this. ECMAScript, the language in the specification is the oracle. Sometimes wrong oracle, but it's the oracle. We need to follow that. So it has different kind of problems and issues.
I see. Thank you very much.
I'm Ali Donaldson from Imperial College London. Thanks for the wonderful talk. You mentioned that between WASM 2 and WASM 3, there were lots of different extensions and new features being experimented with by browser makers. So I guess I wondered if you could say a bit more about the interplay between being informal and exploratory and implementing things before specifying them versus specifying things upfront and implementing them later. Is it a mixture of these things that's going on, or is it that things kind of settle down in implementations and then get formalized after the event?
So thanks for the good question. The WASM community group, they have this culture that they need to describe the semantics formally first, thanks to Andreas. So either in prose and then formal rules, whatever. But if there are developers in the browser companies and they implement them. So altogether, they are just that happen all the time, and they have long discussions. Like in order for a feature to be standardized, it often takes several years. So I think that's the current status. And now that we have Spectac, people are excited that that timeline is going to be shorter. And but still, which one is the first? It depends on the writers. It depends on who writes that proposal. If the proposal is from Google, then highly likely from the implementation. If the proposal is from academia, highly likely from the formal rules. So that's it. So they have different tastes.
Great, thank you.
Hey, Adam Chapala from MIT. So you told us about several long campaigns to get particular specification techniques adopted for particular languages. And some other things in the world are changing at the same time, like the importance of highly parallel execution. The two languages you focused on seem pretty inherently sequential in the notations that they adopt and the kind of data flow patterns that show up. If we look forward to languages where it's really important to support thousands of parallel threads, what would you see being different in the kinds of tools and even maybe social approaches that you're pushing here?
Yeah, thanks. The main thing I think I'm trying to deliver with this keynote talk, because I talk too much, the main thing is we need to have the formal semantics first, period. Actually, I'm stealing this title from Xiao Hong's talk yesterday. So if you have the formal semantics in K-frame, in K-style, or in big step semantics or small step semantics, I'm happy if you have one. And for concurrency and non-deterministic semantics, we've not yet touched it. So we are far from there. But we made a baby step to deliver our research to the industry. And now that we are aware of that problem, people are asking about those things. Like, how are you going to test non-deterministic behaviors? How do you do that at LLVM? And those many questions. So we are along the way, but far from there. Thank you.
I'm going to exploit my privilege to actually ask another one. So maybe another way getting partially at some of the things from Adam's question. You emphasized that a key design decision was to focus on a particular language and not make the tools overly general. So I guess moving forward, like how do you think about frameworks for language specification like MLIR or things like that? Is that a mistake? Should things really be much more narrow? Yeah, I don't know.
So a very good question. So yesterday with our workshop, Peter Tso, he had to give a talk remotely. He had tons of questions like that. Like, who's your audience? Academia, industry, entry-level students? What is your application? Like, or what language do you want to write? In your research paper or real-world application, product line language, everything is different. And when we have this, like, we have WASM specific and JavaScript specific thingy, then people ask like, that's then one for each language. What is there any lesson? Yeah, there is a lesson that we, again, believe in the benefits of formal semantics and the methodology that I discussed. And what we view this problem is, it's like a programming language. There are so many programming languages. So maybe we want to pick one ADA to do everything. Really? C and Rust are good for good performance. And OCaml and Haskell are good for functional programming. And JavaScript is really good for what is doing well, right? So every language is different. We think our approach, like Sail is really good for ISA instruction semantics, and K is good for if you want to check the concrete semantics really quickly. So they have different purposes. So we are more into actually helping or using in the real world industry problems. So they have different problems and different ways to solve them.
Fantastic. Oh, yeah, please.
Thank you for the great talk. And I have two questions. And the first one is to raise the fund for this mechanized language specification. How you tell government or company the effect of this work? It's not about directly earning money.
Very interesting question. Yes, thank you. We never asked for money, but so we are helping people, developers to lessen their difficulties in writing software. We are also helping people to use more safe and good software. So in that sense, we are well funded by the government in Korea. So we didn't think about it that much. Yeah.
And the second question is about this work can be extended to general software development. And it reminds me that some behavior-driven development or kind of work, but actually it is not quite popular well today. So what is the difference and how it can be adapted to general software development?
So I just told Zach that this is not for every programming language, so that's even bigger. But just to rephrase the question, I think that again we can emphasize the benefit and the beauty and the power of formalism. And if you want to develop some software, you'd better know what you are doing. You'd better know what your software should do. Then describe the behavior formally. Then your implementation is going to be highly likely correct. Thank you.
Hi, Andrew Myers from Cornell. Great talk, really enjoyed it. So your approach seems really effective, but I'm wondering about the notion of ground truth here. So you have your own DSL. This is sort of a follow-up to Zach's question, right? So you have your own DSL, and then you have a bunch of tools that are translating that into other things. So is the ground truth of the meaning of your specification now embedded in the code that does the translation into, say, Rock?
Right, very good question. The trusting core is, what is that? So we are actually working on meta theory of Spectac. That's one thing. And another thing is like we are testing our specification as well. Meaning that we describe that in the Spectac DSL, and out of that we generate an interpreter. That's just the same thing. We have multiple implementations by Google and other companies, and we use differential testing to test the behavior. So we cannot prove it yet, and I hope Philippa and Conrad and other colleagues can prove that, but that's our current status.
Thanks.
Okay, I think that we will go ahead. Thanks, Soo-kyung, again for a fantastic talk.
Thank you.
And now a word from the big boss.
Hello. So the coffee breaks will be served 3 places, the same 3 places I mentioned before, here and then 2 places above. So please distribute. Okay, so we provide coffee, cookie, and fruit. Oh, sorry? Oh, you can.
caching is open.
What if we just keep pushing the other buttons?
The other button.
I mean,
that is just
if you push one, push it again, so it
to go out to the phones. Oh yeah, here it is.
Hello?
Okay, hello. We're checking the mappings. Yeah, there are too many
Yeah, we just
things
need to
to
get
add.
this thing to work.
Yeah, so
So these two I'm assuming are those ones, right? Okay, yeah, fine.
Yeah, and right is that one. And so that's going to be, I believe, this one, the X.
Oh, okay.
Hello?
Oh,
there we go.
Thank you.
Check, check, check.
You get a mic now. I don't think we have two mics.
We have two, but we need two. It takes 30 seconds to extend the mic, so
Don't touch these buttons.
Okay. Oh.
Test, 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 test. 1, 2. Test, test, 1, 2. Got it then?
Test.
And then this is right and this is left. And
Depends on where your clock's set to. Yeah, it's on Seoul time.
Sit. All right, good. All right. All right, file in. The session is going to start here in a moment. All right, it's 10:30, so let's get started. Welcome to the Compilers 1 session. My name is Evan Chang. I'm from the University of Colorado Boulder. And here, it's my pleasure to introduce the first talk by Chris Fallen from F5 on partial evaluation. So take it away.
All right, thank you for the introduction. So my name is Chris Fallen, as was just introduced. And this is work that, so I'm currently at F5. This is work that was done while I was at Fastly, and work that was evaluated and written up in collaboration with my co-author, Max Bernstein, who was at the Recurse Center at the time. And so I'll be talking about partial evaluation in order to perform whole program compilation. So first, let's talk about why might we want to use an interpreter-based strategy for dynamic language implementation. So bytecode interpreters are a sweet spot in the design space between simplicity and production-ready performance. By this I mean that they're a significantly less effort to implement than a full just-in-time compiler with type inference and all the rest, but they actually provide reasonable performance that could be used in production. And so for this reason, many dynamic language implementations use just an interpreter-based strategy for a significant portion of their lifecycle. Also, interpreters are very portable. That's relevant. So to give some context for this project, about 4 years ago, I ported SpiderMonkey, Firefox's JavaScript engine, to run inside a WASM module. That is on top of a WASM-based platform. And this was used for a function-as-a-service platform. It was kind of a plugin or a request handler. Because SpiderMonkey has an interpreter tier, excuse me, this was actually quite straightforward. So So interpreters work, but they're a little bit slow. And so when one wants more performance, one might start to consider adding a compiler to native code. So typically in a just-in-time or dynamic language implementation, one would add several tiers. The first tier one would consider is typically called a baseline compiler. The idea here is that one has implementations for each bytecode. One simply splats those implementations one after the other, generates the code, so very simple, very fast. And then when one needs more performance, one begins to think about building an optimizing compiler tier. The way this will work, at least for a dynamic language, is that one wants to build type-specialized code. And so one does a type profiling pass, or profiles types as the code runs in lower tiers, and then combines these types with the individual implementations of bytecodes to produce one wholly optimized function body. Unfortunately, in the port of SpiderMonkey to WebAssembly that I mentioned, these tiers are not available simply because it's a new ISA, a new platform, and there was no implementation to generate WASM bytecode. Moreover, on this particular platform, it was quite interesting. JIT is fundamentally not possible. So for both security and for operational and management reasons, it was not possible to add new code to the system at runtime, right? And so the whole modality in which this JIT-based platform worked would not be possible to build on this platform. Instead, what we would need to build if we wanted more performance than the interpreter would be a full ahead-of-time compiler backend that's completely separate from the existing JIT infrastructure. Right, so building this is an enormous engineering effort, both initially and to maintain sort of in perpetuity. And so we asked ourselves the question, right, there's an opportunity to ask, is there a better way to build this? So let's consider what one does when one builds an interpreter and compiler tiers for a language implementation. When you write the interpreter, you write the semantics for every bytecode directly, and those semantics execute when the opcodes are reached. When you write the baseline compiler, you write code to emit the instructions implementing the semantics. Those instructions are emitted and then executed. When you write an optimizing compiler, you write code to emit the IR nodes implementing the semantics of each opcode, and those are optimized together, emitted, and executed. So these are three different encodings of the semantics for the bytecode. This can lead to all sorts of issues, subtle incorrectness errors as they mismatch. It's also, as I mentioned, a significant increase in the engineering effort, including ongoing as we add new features to the language. So the ideal would be that we generate the compiler from the interpreter. And right, all these different semantics are fundamentally expressing the same thing, just in different ways. So why not take the direct expression of those semantics in the interpreter and automatically derive the compiler tiers? This would give us a single source of truth. It would reduce engineering effort, both initially and as we maintain the thing over the long term. And it would eliminate mismatches by construction. So this idea has been around for a while, in fact, 54 years, I think. It's called the Futamura projection, at least when you do it via partial evaluation. It's called the Futamura projection. And the idea is that we partially evaluate an interpreter with the program that it's interpreting to perform a compilation, right? So the residual, the piece that can't be evaluated away, is a compiled form of the bytecode that was interpreted. So there are several items of past work that have made this practical. One of the most well-known probably is the truffle system, which is built on top of GraalVM, which is a Java runtime. This was published in our very own PLDI 8 years ago. The way it works is by taking a constant snapshot of an AST, an abstract syntax tree, and an interpreter for the AST, and inlining, and so constant propagating the AST into the interpreter, inlining the handlers for every node on the AST up to some boundary, and then that produces effectively compiled code. This works quite well when it works. Unfortunately, it requires rewriting the entire language runtime into this framework, right? So it wasn't really applicable to our use case where we had a large existing runtime. We wanted to stay close to upstream. We wanted to minimize maintenance cost. Also, as far as we know, it only works at runtime. It's unclear if ahead-of-time operation is possible. One of the other main approaches here is meta-tracing, or tracing in general. A good exemplar of this approach is the PyPy implementation of Python, which is built on RPython. And the way this works is that you have an interpreter over bytecode. You trace the execution of that interpreter over the bytecode, and you record the actions it performs. That's the trace. And then you compile that trace to machine code. And so this also works quite well when it works. It can see through a lot of abstractions. It's quite fast. Unfortunately, it requires rewriting the interpreter into the framework, just like Truffle. Also, it, even more fundamentally than Truffle, can only operate at runtime because it requires observing the execution of the interpreter in order to produce the trace. So our goal in this work is to build a solution that's fit for our needs, a practical full method ahead-of-time partial evaluation engine for existing bytecode interpreters, such as SpiderMonkey written in C or C++. And our contribution in this work is a tool that we call Weevil, or the WebAssembly Partial Evaluator, that does just that. as well as an adaptation of Spectac, the production JavaScript engine, for its interpreter tier to be partially evaluated into a compiled WASM code. So let's dive into how this might work. Let's take a very simple interpreter. This interpreter only runs one opcode. And let's see how we might apply standard compiler techniques to partially evaluate. So let's apply constant propagation. Let's say that we know that the byte at *PC, the opcode, is the constant add. So we can go ahead and plug that into the program, do the substitution, and then we can do branch folding. We know the target of the switch because the selector for the switch is a constant. And so we take just the body for the add opcode implementation. And so this looks like a compiled form of the add opcode, right? So great, partial evaluation works. All right, let's go back to that interpreter. Let's make it a little more interesting. Let's wrap the switch with a loop. So this is now an interpreter for multiple opcodes. And let's give it a program of two opcodes, add and return. So here's the control flow graph, or CFG, for that interpreter. There's the entry, there's the loop header, and then there's a switch over many possible opcode implementations, and then a back edge to execute the next opcode. So let's do our constant value analysis. We start with the known state PC equals 0. We can go ahead and do branch folding as before. We increment PC. We know PC equals 1 on the back edge. That flows back into the loop header. And now, as is typical for data flow analysis, we need to meet all of the in edges into that block. And so in the constant value lattice, constant 0, constant 1 meet to bottom, which means not constant, right? And this is actually accurate. This is true. In fact, we know here that PC is not constant. Stated plainly, PC changes every iteration. So we see that if we just take constant propagation and branch folding as our basis for partial evaluation, this is not going to work for any practical bytecode interpreter. So the first key idea in this work, one of the key ideas of Weevil, is that we use context sensitivity. So the idea here is that we evaluate each iteration of the interpreter loop in a separate context. And I'll tell you where these contexts come from in a moment. But by doing so, we keep the states from meeting. We keep the constant propagation from collapsing. So here we have essentially a separate analysis context in which we're seeing another view of the same interpreter loop. You can think of it as unrolling the loop and making a copy for every opcode, although we don't actually do that in practice. And so PC equal 1 flows into the next context. We know a constant PC for every static program point in this context-sensitive view. We can then do branch folding. And we have essentially the equivalent of a template compiler. We get the implementation for each opcode, and they're glued together in the program flow. So where does this context come from? Well, in Weevil, we require annotations in the interpreter, minor annotations. And the idea is that the interpreter author annotates where the context changes. So in this example, it's PC. It could actually be anything. Weevil is a general tool. But the idea is that as we do the constant value abstract interpretation and process each block, we can follow these intrinsics, and we can update the context as flow-sensitive state. And this allows us basically to drive the traversal dynamically through all the possible PC values. One really important thing to note here is that these are not load-bearing for correctness. So you could get these wrong, and the worst that would happen is the analysis collapses back to the runtime state, the not specialized state that we saw before. They're only to make the analysis work. So here's a more detailed example of the Weevil transform. Here we have a control flow graph again with the header, the opcode implementations, and the footer. The way the transform works is we take the interpreter CFG, we call it the generic function. We're specializing it for some constant input. And so we'll produce a specialized version of this function for that bytecode on the right. We do this with several memoization maps. So we memoize the context-sensitive block and value, SSA value ID to blocks and values on the right-hand side. And we'll see why that's important in a moment. This whole thing is work queue driven. So we basically just lazily follow all reachable code with this work queue algorithm. So for each block that we pop off the work queue, we partially evaluate that block with constant propagation. We track the context as part of the flow-sensitive state, as I mentioned. And then when we reach branches, we enqueue the branch targets on the work queue with the current that is maybe updated by intrinsics context. So I'll give an example here. We'll start with PC equals 0. That's our initial state. We go ahead and take the initial block. That's the entry to the function. And we'll specialize it based on the known opcode at that PC. We'll copy over the blocks for that opcode. We have an update context intrinsic. So when we see the out edge from block 6 back to block 1, we need to process block 1 in context 1 rather than 0. So we'll copy it over again. We'll copy the opcode implementation and constant propagate it for the next opcode. Let's say that the program that we're specializing on is a two opcode program, add and then go to 0. So an infinite loop around the add opcode. The really interesting thing here is that because we memoize the specialized blocks, when we process the branch target out of block 6, the back edge here for the PC equal 1 context, we actually look up and find the original block from context 0. So this is really important. What this means is that the bytecode control flow graph is preserved, right? This is not a trace compilation. This is not following some linear path through the bytecode and producing a linear stream of specialized code. This actually, lazily via the work queue algorithm, finds all reachable code and reproduces that control flow graph of the bytecode exactly in the compiled code. So this is a whole function compiler. There are more details in the algorithm that I won't, more details in the paper that I won't go through, details of how the algorithm works, how it interacts with SSA, et cetera. The last thing I want to tell you about is how we applied this to SpiderMonkey. So SpiderMonkey, as I mentioned, is Firefox JavaScript engine. It runs, as we ported it, it runs inside of a WASM module. And this is useful for function as a service and other plugin scenarios. And Weevil was specifically developed, at least initially, to do the AOT compilation for this engine. The way this works is sort of with a snapshot methodology. So we start with spidermonkey.wasm. That's the interpreter compiled to a WASM module. We load the JavaScript source into it, and then we snapshot the state of the WASM heap, and we dump that as a new WASM module. So it's a WASM module with an initial memory state that contains bytecode objects. Weevil then processes the snapshot, takes the interpreter, and partially evaluates it over that bytecode, appending new WASM functions to the WASM module. So that's all well and good. That gives us a compilation of the JavaScript bytecode. But one finally might ask, how is AOT compilation of a dynamic language possible, given what I said earlier about type profiling and the need for JIT? So the last thing I'll tell you about is that in the JIT compiler world, typically the baseline compiler layer actually doesn't depend on types. And so the way this works instead is that the bytecode is more or less one-to-one with the semantics of the source language. So there are polymorphic opcodes like add and equality check. And the interpreter uses something called, or the baseline compiler uses something called ICs, or inline caches, which are little type-specific stubs of code that are added at runtime for the actual type cases that are seen. And these are reached via pointers that can be updated at runtime. So they can be plugged in without actually changing the code. However, typically, in a native scenario, the JIT compiler will dynamically generate these IC stubs themselves. So it does require JIT compilation at runtime just to generate these little bits of code. So the key idea, at least with the IC sites here, is that the late binding of the execution semantics, so dynamic types tell us what to do only when we reach that program point, becomes late binding in the compilation strategy, right? We just have an indirect function pointer that we can update at runtime. However, as I mentioned, we need, at least in the current scenario, the JIT compiler to generate these stubs. And so what we realized was we could actually make this ahead of time by collecting all of the possible ICs ahead of time and compiling those before we ever run the code. So concretely what we do is we run SpiderMonkey's unit test suite, collect all of the ICs that it generates. This is nice for sort of social project organization reasons because you'll write a unit test if you add new functionality. So we collect this corpus, and then we Weevil this, we partially evaluate it alongside the JavaScript functions, and we simply have a lookup table to find these at runtime. So we can actually run all in specialized code with no JIT compilation. This is fully ahead of time compiled in all of our benchmarks. So I'll tell you about our benchmarks. Very briefly, we have the Octane suite, which is a standard suite for JavaScript engines. We evaluate it here with a generic interpreter with ICs, and then our tool applied in several steps. The speedup that we see over the interpreter with ICs, which we can take as a fair baseline, is 2.17x. If we take the generic interpreter without ICs, which was actually the state of the world before we started this entire project, 2.53x up to 4x. So this is quite a significant speed up. There's some remaining performance to be had because calls are a little slower on WASM than they are on native. So ICs are still slower than they could be, but this is quite good. And it is actually in production. So customers are using this today. There's a flag on the runtime built around SpiderMonkey that can be used to enable this. And so it's seen real use cases, it's stable, and it's providing real speedups. Finally, in the paper, we do talk about some results on a Lua interpreter and a Toy interpreter as well, to show this is general and not specific just to the way that SpiderMonkey works. Thanks, and I'll now take questions.
If you have questions, please step up to there. Good. Step up to the mic.
For the stream, 1 second. Wait for them to.
Okay. Does that work? Yes. Okay. Thanks. Right. Thanks for the great talk, first of all. I was wondering, so
in your analysis, when you have a loop, you kind of, each different iteration of the loop is a different analysis context, I think. Like, obviously, like if there's a while true loop that, like at some point you have to merge back, right? What's the heuristic to make that merge, and how does that work?
Yeah, so the thing I didn't mention in too much detail is that it looks like a standard data flow analysis with a fixed point algorithm. So we update the state into a given block in a given context when we see a new edge. If the incoming abstract state does not change, then we don't reprocess. And so we'll reach a fixed point just as a normal analysis would reach a fixed point.
All right, thanks.
Yeah.
Hi. Leonard from University of Montreal. Thanks for the great talk. I have some knowledge about basic block versioning, and it looks like this is kind of similar analysis. And one thing I know about basic block versioning is that it's hard to keep the context between function calls. So I'm wondering, how do you treat this case?
Yeah, that's a great question. So first of all, it is very much like basic block versioning. You can think of it as kind of orthogonal in the sense that we are specializing on PC as the context. BBV does type context, right? So they could actually be combined if you want. That's interesting future work. As far as interprocedural goes, we don't actually specialize across functions, so it's a very simple answer. So that is one requirement on the shape of the interpreter, that all of the pieces that need to be specialized or splat out per opcode exist in a single function at the WASM level. One could imagine doing some sort of interprocedural specialization where you say, I want a function pointer just for this other function I call in this context. Yeah, we haven't done that yet, but that would be interesting.
Thank you.
Hello, yes, check. Hi, Ralph Jung from ETH Zurich. So thanks for the talk. I was wondering, you mentioned you are using the test suite to gather these little snippets of like the actual implementations for all the operations. Does that mean there's some risk here that you're going to end up missing some?
Yeah, it could happen in theory. And so, in fact, so I glossed over, I said all possible ICs. There are some cases where ICs are dynamically generated based on, for example, the length of a JavaScript prototype chain, right? So if we don't have it, what happens is the cache IR, which is the IR for the IC, will still be generated. It will be interpreted by the cache IR interpreter during runtime, which is still faster than not having the IC at all. Yeah.
Thanks.
Go ahead. Last question.
Hi, Sungwon from NYU. I actually had the opposite question where, if I'm understanding things correctly, compared to something like a tracing interpreter, you have a chance of over-approximating, where you generate some code for a path that actually doesn't really get run for your specific application. So how much is the code? How much difference does there exist between the code size from like a tracing versus your system?
That's a really interesting question. So it turns out to bloat quite a lot, actually. So in our particular use case, that didn't matter much. We were compiling, we were memory mapping the code in. So if it's cold and never used, then that's fine. It does actually matter in a lot of cases. You want small code results. So one thing that could be done is the Weevil specializations are optional in the sense that the way the tool works is that it will do the specialization, then stick a function pointer somewhere to say, OK, it now exists. You could add some metadata to the compilation result to say, if it's not actually called, you can delete it as long as you null out this function pointer. And so you could do that and then have a runtime profiling pass, or as your system runs it, it could say, I actually have memory pressure, I need to shrink the code, and I can delete the things that weren't actually run. So that's interesting future work. Yeah.
All right. Thank you. Let's select Chris again.
Yes.
All right. So I'll go ahead and introduce. Next up, we have Lucian Popescu from the University of Lisbon.
Test, that's good.
And as soon as this slides up, he'll tell us about exploiting undefined behavior.
So, right, just a second. Cool. Hello, everybody. Thank you for being here. Today, we are going to talk about undefined behavior, or UB for short. What it is, why it exists, how the compilers exploit it, and most importantly, what happens if we try to remove it. I'll present the first study on the performance impact of undefined behavior optimizations. So, First, let's start with a real bug. Some of you may already be familiar with this Linux kernel example. At the first glance, everything seems okay. A pointer called tune is created, and if it's null, the function returns an error. However, there is a big problem with this code. The pointer is dereferenced before it is null checked. And what does that mean from the compiler's perspective? Well, dereferencing the pointer means that it must not be null, because otherwise the operation wouldn't make sense, right? And consequently, the if check is deleted, because the compiler already proved the validity of the pointer, so it doesn't make sense to make the check one more time. The result, a security vulnerability in the Linux kernel. Fortunately, it was quickly fixed, and the fno delete null pointer checks flag was added in both GCC and Clang to fix this problem. However, the key point is that compilers, this is not an isolated case. Compilers are designed to assume that our programs do not contain undefined behavior. So you might wonder, if UB leads to security vulnerabilities, then why would the standard allow it? And the answer lies in the design philosophy of the language, which is solely based on performance. We want the language to be as fast as possible so that we can get the most of our hardware. However, there are some problems with that. First, some operations don't have the same semantics on all hardware architectures. Take shift overflow, for example, when you shift an integer by 32. x86 uses only the 5 bits of the shift amount, while ARM zeroes the result out. Imposing a single uniform semantics would either, would result in inefficient code generation and would penalize the other architectures. The other problem is that proving memory safety properties is too hard in the general case. Take, for example, array of index. The compiler needs to prove that array is allocated, that index is in bounds, and that array is not null. So by making those cases undefined behavior, the compiler can assume that they never happen, and it becomes the responsibility of the programmer to actually check that those corner cases of the language are never hit. So to sum up, performance is the sole reason for the existence of undefined behavior. And to see that in action, let us take a look at this loop. The key detail in this example is that we are running on a 64-bit machine where the size of I is 4 bytes and the size of P is 8 bytes. So at every step, we need to do a sign extension for I from 32 bits to 64. However, this, as you can imagine, is bad because it's slow and repetitive. We would like to be able to do the sign extension only once at the beginning of the loop, and that's it. Essentially turning I and N into longs instead of ints. So this simple trick, this simple optimization brings a 2x performance boost on a simple micro benchmark on my machine. But the key detail is that this optimization is only possible if signed integer overflow is undefined behavior. And to understand why, let us take a look at this sign extension table. Sign extension is only possible if for values that do not overflow. As you can see, the final example is wrong. But since signed overflow is undefined, the compiler may assume that it never happens and the optimization becomes sound, allowing us to do the sign extension correctly. So we saw that this UB optimization is great for micro benchmarks. It brings a 2x performance boost with just a simple modification. But can the same be said about real-world programs? I mean, can the same performance boost be ported to real-world applications? And more importantly, can compilers evolve in such a way that they don't need undefined behavior to prove that this optimization is correct? So those are questions that we are trying to answer in the study. Signed integer overflow is not the only UB out there. There are many, many of them, but we group them in 3 categories. First, we have UBs which compilers directly exploit. For example, dereferencing a null pointer or dividing by 0. So because those things trap on most hardware architectures, the compiler chooses to immediately exploit them aggressively as undefined behavior. Next, we have UBs for which compilers offer stronger semantics like signed integer overflow or reading an uninitialized variable. Those in general produce bogus results, which then can be propagated through the program and enable other optimizations. And finally, we have UBs which compiler treat, which have more defined semantics, let's say, like strict enums and mem copying 0 bytes from null. Technically, they are undefined behavior, but compilers, if compilers optimize them too aggressively, they might break too many programs in real life, so they choose not to do that. So to sum up, we have aggressive UBs and we have more conservative UBs. But what we saw in recent years is that there is a growing trend in defining some of the UBs, like giving them stronger semantics. C++'26 will add a new type of behavior, which is called erroneous behavior, which is stronger than UB, and compilers are recommended to diagnose it. Like reading from an uninitialized variable would become erroneous behavior. C++C23 adds checked integer operations to help programmers avoid signed integer overflow UB. And the addition of the fno delete null pointer checks flag is also yet another example of how to give defined semantics to UBs. However, there is a problem. We don't know the performance impact of those changes. And I repeat, UBs are great for micro benchmarks, but do they behave the same from real-world workloads? And can the compiler evolve in such a way that they don't need UB to prove optimizations? We quantified the performance impact of undefined behavior optimizations. And we think it's also worth it to note that we only focus on performance. We don't take necessarily into consideration security implications or developer productivity implications, only performance. To do that, we developed the following experimental setups. We have 18 UB categories, which are controlled by compiler flags. We have 24 real-world benchmarks, which are performance-sensitive applications from diverse application domains. And we run those benchmarks on 3 CPUs, AMD, Intel, and ARM. These are the 18 flags that we gathered. We divided them in 5 categories, with pointers and memory having the most flags. We started with a copy of Clang 16, which already implemented 6 flags, like frapv, which gives defined semantics to signed integer overflow, and fno delete null pointer checks, which allows storing and loading from the null address. We also added 9 new flags in Clang, like fconstraint shift value, which protects us against shift overflows, and fdropAlign attribute, which protects against misaligned loads and stores. Since the intermediate representation of LLVM is not expressive enough, we also had to add 3 LLVM flags to directly control the behavior of the optimizer. Zero uninit loads does that. It replaces all loads from uninitialized variables with 0 loads. Next, I will show 2 examples of flags that we implemented. First one is from Clang, fconstraint shift value. This is the classical shift operation in C, which normally is translated to LLVM as a shift left instruction. However, the problem is that if B is greater than 32, this is UB. It will return a bogus value. So to protect against that, we add an extra instruction, an AND instruction, to make sure that B is also in the is always in the defined behavior range. So on architectures like x86, this doesn't have any binary performance impact because we are basically encoding the same assumption in the IR and in the assembly code. That is, use only the 5 bits of the shift amount. This is an LLVM flag, 0 uninit loads. This function clearly returns UB. And the interesting thing to see is that with and without the flag, the IR is the same. We have an alloca, a load, and the write instruction. The only thing that changes is the behavior of the optimizer with regards to the load. It will return 0 when the flag is enabled, so that we don't get UB. These are the benchmarks we used in our in our tests, as I said, we try to have a diverse set of application domains like audio-video encoders, text processing, compression algorithms, SMT solvers, and even compilers. We compiled over 7 million lines of code and used Phoronix test suite to gather this set of benchmarks. So next, let's get the results. First, I will present the binary size impact. As I said, we use 3 architectures, and we compiled the benchmarks with link time optimizations and without link time optimizations. We used the 18 individual flags plus all flags combined to see the cumulative effect. And all the impact will be computed relatively to a baseline, where all UB exploitation is enabled. So these are the numbers. On the x-axis, we have the shortened names of the flags. And on the y-axis, we have the relative binary size impact. In this plot, lower means better, because when a flag is enabled, it drops the size of the binary. So on Intel and AMD, you can see that the binary size impact is relatively minimal. That's because those are CISC architectures where few unoptimized instructions can be combined into a single instruction, basically meaning that the binary impact remains unchanged. But the same cannot be said for ARM, which is a RISC architecture, and every new instruction in the IR means a new instruction in the assembly code. For performance, we use the exactly same setup, and these are the numbers. This time, higher means better, because the performance increases. So in Intel non-LTO and AMD non-LTO, we again see a relative minimal performance impact. Those are widely parallel architectures where few unoptimized instructions do not add too much overhead. However, on ARM, this is not the same, because every new instruction adds overhead in the execution pipeline. However, the most important thing to see here is that by enabling LTO, we managed to recover the performance and even increase it in some cases. So this is a great thing, because having the UB flags enabled, that is disabling UB, and having LTO enabled, we managed to get the same level of performance. So we try to use other techniques other than LTO to recover the performance. We analyzed 12 cases and categorized them in 5 categories. The interprocedural analysis used by LTO allowed us to recover important pointer metadata used in loop analysis. In the second category, we found out that the loop vectorizer in LLVM is not capable of computing the number of iterations without UB. So for that, we added some runtime checks to see, to still be able to vectorize the loops. However, newer versions of LLVM can already do that, so that's a great thing. We also found some unrecoverable cases. We found some improvements. And yeah, there was a bug in the program. John the Ripper used uninitialized data, which increased the size of the binary when we used the -0 uninitialized loads flag, giving a -1% degradation. So to conclude, we saw in the beginning that compilers assume that programs do not contain undefined behavior. And as you may already know, and as we've seen in the Linux kernel example, that's not true all the time. So exploiting UB for compiler optimizations introduces and creates security vulnerabilities. But fortunately, in the recent years, we saw a growing trend of defining some semantics for some UBs. So the question remains, what is the performance impact for this change? And in this study, we've shown that for the cases that we analyzed, the impact of defining UB is minimal. And what's most interesting is that we were able to recover the performance using UB-free techniques. Thank you very much.
Okay, thank you. Kang Guk-ji from the UT Dallas. I think this is really practical and important problem. Thanks a lot for your research. I have two questions.
Yeah.
One is about about the hardware architectures that you covered. So I saw the Intel, basically x86. Did you explore the other architectures like ARM or the RISC-V or those kind of things? Second thing is that I've been aware that there was compiler passes, like for instance UBSEN, like that was designed to protect the programs from the security vulnerabilities with this. Did you include those passes for your evaluations?
Yeah, when designing the flags used for optimizations and when using the already existing flags, we wanted the performance impact to be somehow minimal. So as you saw in the -0 on init loads, we didn't set all the memory that was uninitialized from the beginning, so that we don't have an unreasonably big impact. So that's why we didn't use fsanitizer, because it would have added too much checks. So instead, we wanted to go for solutions that have reasonable performance impact. Okay, thank you.
Hi, Vadim Zaliva from Tufts. I have a. Did it happen for you after disabling some these UB checks that test will be failing, crashing? For example, an allied member reads on some architecture, I think on earlier ARMs, they trap. Is that happened to you, or all the tests passed with UB disabled?
No, we didn't see any crashes when disabling this kind of UB, meaning that the optimizations were not putting the code in a state that, I don't know, it would memory crash or do other kind of bad thing. So we just wanted to see how optimizations behave with regards to UB, either or not the code contains it.
Hi, Derek Dreyer, Max Planck Institute. Very interesting work. So did you consider multi-threaded programs or not? I wasn't completely sure.
Yeah, we considered multi-threads programs.
Okay, did you consider data race UB? Because with multi-threaded programs, right, data race UB is needed for allowing memory reorderings. So I was wondering if you tried disabling memory reorderings.
No, we actually didn't touch that part. And in the benchmark suite, we wanted mostly to focus on single-threaded benchmarks and only have a few multi-threaded, because it was easier to actually benchmark the code, because multi-threading also adds some noise, which we wanted to reduce to a minimum. So, yeah, that was.
So I guess, can you speculate on whether on the performance impact of disabling memory reorderings based on your work here, or would you really need to test that?
Yeah, I guess kind of needs testing, because I mean, that was the motivation for doing this study, because theoretically we could assume some things about how those optimization works, but without tests on real-world software, not on micro benchmarks, we couldn't know exactly.
Okay, thanks.
Thank you very much.
Great. Let's thank Lucian again.
Thank you.
All right. Our next speaker is Michel Weber from ETH Zurich. All right, and as soon as he's all mic'd up and ready to go, then he's going to tell us about relaxing alias analysis.
Nice. No idea what that is. I'm. Yeah, full. Now full screen, please. Nice, perfect. Oh, it's gone, and it's back. Okay, looks good. So, yeah, welcome everyone to my presentation. I am Michel Weber. This is work I did with Theodoros Theodoridis and Chandong Su at the AST lab at ETH Zurich. And so I don't think I need to tell you here at PLDI that programming languages and programs are interesting and cool. And in this talk, I want to focus on how we make them run, which is through compilation, through a compiler. So a compiler is essentially a piece of software that translates a program in a sort of high-level source language to a low-level assembly file, binary size, binary file, something like that. And of course, there are many binary files that have the same semantics as the input source program. So modern compilers try to achieve actual good binaries. Well, and how they do that is that they optimize their programs. They try to remove that code. They try to vectorize stuff, whatever. Now, some of these optimizations that we want to apply are not sound in general, so we need some way of guaranteeing that they are sound. This is done through an analysis framework, usually. This analysis framework derives program facts like 2 pointers don't alias, and then the optimization can take these program facts and, I don't know, vectorize some matrix-matrix multiplication or something like that. So now there's this intuition or assumption in the community that, well, if we have more precise analysis, so analysis that gives us more information, then we will have better binaries, right? And that's really intuitive because more information means more optimizations, and more optimizations means a better world, right? And here in this piece of work, we're really trying to understand whether that's really the case. We're trying to shift this perspective and ask this question whether more precise alias or more precise analysis in general mean better binaries. So for this work, we focus on one specific analysis called the alias analysis. And the alias analysis is really about understanding the relationship between memory regions that different pointers point to. For example, at least how it's implemented in LLVM, you ask for 2 pointers, pointer 1 and pointer 2. How is the relationship between their memory? And then the alias analysis goes off, does fancy computation, comes back and gives you one of 4 results. This might be a may alias result, meaning I wasn't able to derive any guarantees. I don't know really. We have the no alias results, meaning the 2 memory regions are guaranteed to not be the same whenever or for this entire program. Then we have the partial alias result. This is about overlapping memory regions and sub-objects and stuff. This is really rare, but I still decided to include it for completeness. And then we have must alias, meaning the 2 memory regions are guaranteed to always be exactly the same. And now how this is implemented, at least in LLVM, the version that we instrumented for this work, is that we have the optimizations. They do fancy stuff up there, and then they ask the questions, do the AI algorithms, the algorithms compute something, and then they give the information back. Good. So far, so good. So the question we're really asking here is, does more precise alias analysis mean better binaries? And now, to study this, of course, what we need is that we need to simulate several levels of alias analysis, essentially. And how do we do this? I think there are essentially 2 choices, really. You can go down through this lattice, and this is really hard, right? Because you run into all of these annoying issues that have to do with sound. It's like if you have a may alias and you replace it with a no alias, that might not actually be true, and then your program is not correct, but maybe non-deterministically not correct, and blah, blah, blah. It's an extreme headache. So we take the other choice, the, I think, smarter choice, which is go up. We just replace information that we have, no aliases, for example, with a may alias. So we're kind of taking away information from the compiler, and we see how does the performance of the binaries change. And this is really guaranteed to be sound, at least. I mean, conceptually, this is guaranteed to be sound, of course. There can be compiler bugs, but yeah, those never happen, of course. So how do we implement this? Essentially, we intercept the responses with this relaxation logic here, and then we can configure this relaxation logic for our different experiments to choose specific queries and bits of information that we take away from the compiler. And here, we decided to take away the second bit of information, changing a no alias to a may alias. Good. Going back to the high-level question, we know now how to do this technically. So let's ask more specific questions, and these are really our research questions. So our first question is, what is the impact of aliasing information? And this is really trying to compare the two extrema in this search space, this, extrema of all the information and no information at all. Then the second one is how much aliasing information is actually critical. So how much information does the compiler really need to still achieve the same result? Or if I were to formulate this the other way around, non-critical information is information that we can take away, we can give it, it doesn't really matter, we don't see an effect. And then our third question is how impactful are these critical alias queries? And this is really about understanding the space in between the two extrema. What happens if we give a bit of information here and take away there and yeah, see what happens. Okay, let's go through these. First one, what is the impact of aliasing information? The experimental setup here is very simple. Our relaxation logic just takes away everything. It relaxes everything to May aliases. This really corresponds to not doing any alias analysis whatsoever. And now we have this compiler version. So we use the Spec CPU 2017 benchmarks and we compare all information versus no information. And this is what we get. So how do we read this plot? On the x-axis, we have the different Spec CPU benchmarks, 12 or so. On the y-axis, we have the relative time. So this compares the geometric mean of 10 runs for both versions. And if you're at 100%, that means they're equally as fast. If you're above the line, that means taking away information makes the program slower. If you're below the line, and there are actually points below the line, it means that taking away the information makes the program faster. So what we see here is we have one extreme case, this NAB benchmark that has like 5.5% slowdown or so. Most of the cases are in between like 0 to 2% or so. There's even speed ups. So at least I think this aliasing information has little impact actually. Everything is surprisingly little, given that we believe that so many optimizations are actually need aliasing information. So this is the question to our first, or the answer to our first question. Now for the second one, how much aliasing information is actually critical? The experiment that we designed here essentially runs one compilation for every query, and in that compilation it takes this query away. So for the first one, we take away the first query, second one, we relax the second one, and so on. For the 100th compilation, we relax the 100th. And then we get a lot of binaries, and then we really do a byte-wise difference to the initial binary where we had all of the information. So the critical ones are the ones where there is a difference to be found in this final binary. Good, so what are the results? So how do we read this from left to right? The first thing is the number of queries, the numbers of bits of information in general that the compiler needs to compile all of Spec CPU 2017. There's around 5.5 million requests for aliasing information. Of these, 3.5 million are precise, so they are no, partial, or must, which are also the interesting ones for us because these are the ones that we can actually relax. Right, for a May alias, we can't do anything. And now of these 3.5 million, there is only a little bit more than 100,000 for which we saw a change in the final binary. So that's around 3%, which I think that's a crazy result. It means that 97% of the aliasing information that is requested by the AI algorithms doesn't end up having an effect on the final thing that is generated. So I think what we can say here is definitely that much aliasing information is actually not being used by the compiler, as we can see. Now, let's go on to the third question. How impactful are these critical alias queries? And to answer this question, the experiment we designed is that we essentially handed a coin to our relaxation logic, and on each query, it would just flip that coin. And then with 50-50 chance, it would relax the query or it would not relax the query. So here we ran 10,000 runs of this, this randomized alias analysis compiler version for every compilation unit. And then we had a lot of binaries. We measured their binary sizes. And in this next plot, I will show you the minimum, so the smallest binary that we achieved for every compilation unit. So how do you read this? On the x-axis, we have the around 1,600 compilation units for this benchmark. And then on the y-axis, we have again the relative time. So comparing the relative size. So we are comparing the size of the smallest randomized thing with the initial one. And we see that, of course, for many of them, there is actually fairly no real impact, it seems. But then there are some extrema that are kind of crazy. So we got a 40% reduction in binary size by taking away aliasing information, which I think was very surprising. And this is really not a trivial program. This is, or a trivial compilation unit. This is the variable length integer decoder of one of the compression benchmarks. So it's actually a core part of the functionality of that benchmark that we were able to reduce by so much. Now, I would love to press my button and show you the same results for speed. Unfortunately, we computed that doing this experiment for speed and running all the binaries would take something like 2,000 years. So we didn't end up doing that experiment. But we still, given that everything is randomized, we just gave it a shot, ran a couple of things. And what we found is that we couldn't evaluate everything. We found one case in particular where we found a 20% speed up by taking away aliasing information, which I think is another crazy result in this work. And then, of course, we went and investigated, both this the speed up result and also this size change. And it turned out for the size change, it appears that taking away aliasing information means that some dead store elimination is not triggered. If that dead store elimination triggers, so with aliasing information, we have more phi nodes, and then simplify ZFG can't understand the data flow and everything anymore in the program and doesn't apply as well anymore. And similarly, actually, in the speed up case, what we found is that it's again a dead store elimination that is not triggered, and then simplify ZFG that doesn't remove an entire basic block from the IR. And if that basic block is there, so if you take away the information, then this changes the code layout of pretty much everything. And that seems to lead to this 20% speed up. So it seems that the layout is just more cache-affine. Cool. So I think we can answer this with the critical queries. They can actually have high impact. Even though it's rare cases, they can have high impact. Good. So let me reiterate the results quickly. What is the impact of alias queries, of aliasing information? Well, it turns out it has surprisingly little impact, at least the two extrema. Then, how much aliasing information is critical? Well, much aliasing information is actually not utilized by the compiler, at least by this version of the compiler and in its current state. And then, how impactful are these critical alias queries? Well, it turns out that by having the aliasing information, the compiler is actually losing quite a bit of potential that we could have exploited. So let's get back to the high-level question. Does more precise alias analysis mean better binaries? Well, I think we can say now it's quite a bit more complicated than that, in fact. And I really want to stress here that this is not an issue with alias analysis or aliasing information or something like that. I think it's more about how the compiler uses that information. And I, at least to the best of my knowledge, I think this is the first work that actually analyzed this, at least in this fine granularity of actually looking at specific queries and not just comparing different AA algorithms. But what do our results mean for the compilers community? I think that rather than focusing only on improving alias analysis, which in itself is definitely important, and we should do that, right? We should have better AA algorithms and everything. I think we should try to identify and then improve on the critical information, so the information that really matters, and then that the compilers should also get a bit better at actually utilizing the aliasing information, not just 3%, and also not missing these extreme speed-ups in the corner cases. So thank you very much. I'll now take questions.
Oh, go ahead.
Hi, great work. Just a quick question. Have you also considered categorizing the impact of these information based on which passes are consuming it? Like instead of dropping the information altogether, dropping it for a particular pass?
Yes, we have. Let me just quickly find that. So what we see here is first we have the different passes that actually request aliasing information. Then we have number of precise ones, number of critical ones, and then the percentage. And we really see that it matters a lot. The pass is really, really important.
Okay, all right, thanks.
Hi, Jieju, George Washington University. So could you elaborate on what alias analysis algorithm you tried? Because alias analysis algorithm can be really expensive, so that is critical to provide different sorts of informations.
So this is really built on LVM 17.0.6.
So LVM's own alias analysis, the basic one.
So there is multiple alias analysis algorithms in that version. I think that's basic alias analysis. There's some metadata, type-based stuff. There's several versions. We really try to not look at the AI algorithms themselves. Though I think this is a limitation of this work, that I think sometimes criticality can really depend on the other information that you have available. So if we had the perfect aliasing information, maybe 3% is not correct.
Yeah, thank you.
Nathan Beckman, Carnegie Mellon. I'm trying to reconcile this great talk with my experience where alias analysis has a huge impact. I'm wondering, have you looked at other architectures than an out-of-order superscalar? Because I think having a giant LSQ with all the structures to support speculative execution are maybe part of what's hiding the potential impact here in the compiler.
So we really only evaluated this on one specific version, CPU, which was I think it's an AMD EPIC CPU, I think. I could have to check the paper. We really didn't look any further.
That might be another area to take this kind of work. Thank you.
Thank you for the suggestion.
Hi, I'm Jengan Lee from KITE. So I guess your message is that we should try to utilize alias information better, and in other words, I guess you're saying that. Then my question is, did you find I guess you looked into certain LLVM optimizations, and did you find any cases where you thought that for this optimization, alias analysis could be utilized better?
So I can't tell you for specific optimizations, but I can tell you that what we found is that sometimes really sets of information together lead to optimizations. And this is something that the current AA framework in LLVM doesn't really understand. So I think that's where we could actually improve, by understanding these sets of information, essentially.
Thank you.
I think we're going to have to cut off questions here. I know there's a lot of excitement, but Michel will be around to talk.
Yep.
All right, so the next talk is by Benjamin Quiring from the University of Maryland. And he's going to tell us about webs and flow-directed well-typedness.
Should this be mirroring right now? Great. Cool. Yeah, so this is Webs and Flow-Directed Well-Typedness Preserving Program Transformations, a nice long title. I'm Benjamin, and this is joint work with my advisor, David Van Horn, and my other mentors, Olin Shivers and John Reppy. So let me first tell you about flow-directed program transforms, because that's what this talk is about. So I'm going to use a case study of dead parameter elimination, which is a transformation you might want to do in your compiler that eliminates parameters that aren't used. When you do that, you have to eliminate the corresponding argument. So if we define a simple function f that has a dead parameter y, if we know where f is called, then we know that we can delete y and the corresponding argument that we pass to that. Yay. But if we move to a higher order setting where we like to write code, things get a little bit more complicated. So instead of having one function, we have two functions, and now they functions that it's constrained with because it shares call sites. And it also involves you knowing where those call sites are. And we just saw a talk on this nice partition of the analysis versus the compiler sort of interacting. So a flow analysis is the thing that goes and finds the information and gives that back to the compiler, and then the compiler is going to go do optimizations based on that. So this idea of constraints is one of the central ideas of the paper, and is something that we call webs. So for any program that you might want to compile, you can construct a bipartite graph between the functions and the calls, where an edge exists if it's possible that a runtime call can be, or that call could call that function at runtime. So the webs of the program and the webs of this graph are the connected components of the graph, and I'll color them here. And webs are important because they're the unit of transformation, which means that if you transform one element of the web, either a function or a call, you have to transform all elements. For example, if we transform function 1, then you have to transform call 1, which means you also have to transform function 2 and call 2. So assuming that we have some analysis that can find this information for us, find these connected components, we can annotate our internal representation with them so that we can go and write compiler transforms that consume this information. So it's very simple to do that. I'm going to give myself a set of what I call web identifiers, which is this meta variable u, which refer to concrete webs like 1 and 2. And on every function and every call, I'm going to annotate those with a web. And you can think of these webs as being representatives of sets of functions and calls. And these annotations are subject to the constraint that at runtime, if you're at a u annotated call, it has to be invoking a u annotated function. And that's the crucial piece. I call these the web constraints. That's the crucial piece of soundness information you need. So if we revisit the higher order program example, but we annotate it with webs, we can do this transformation again. So this time, since we have the web information available, we know that if we modify one function in the web, we have to modify all of them. So the first thing we're going to do is inspect all functions in the web to make sure that they both have the dead parameter, and indeed they do. And then we can follow that up with a secondary pass over the term to actually delete the dead parameters and the dead argument. And that works great, and we can use our annotations to guide that. So if we were to write a piece of code to do that, it would first consist of a transformation that traverses over the entire term and checks to make sure things are dead. And then we'd follow that up by a secondary pass, excuse me, a secondary pass that modifies all functions and all calls inside of that web. And in general, if you do these flow-directed or web-based program transformations, you're going to have a first check that's going to traverse the program to check some condition or compute some information about each web. And then you're always going to follow that up by a traversal to actually do the rewrite, two separate phases. So the next question is, how do you actually find these webs? And a classic approach is to use something like my advisor's abstracting machines framework, which is based on abstract interpretation. But if you care about efficiency, this can be really difficult to maintain and indeed to even make efficient. And if you have complicated semantics, that could also complicate your life with designing the analysis. And when it comes to typed languages and doing the actual transformation, you have a couple other challenges. For example, you don't just have to modify the term, you also have to modify the types. And since terms flow through types, you have to track how that's going on and modify the types accordingly. So if in this x parameter, we modified some function that flowed through this type, then we'd have to figure out how to transform that accordingly and track that during the analysis. And that can be done, but it's just extra work. That's kind of annoying. The second issue, and this is more critical, is that the flow analysis is often more clever than the type system, than the underlying type system. So I have an example here to demonstrate it. I define a choose function, which returns one of two elements, depending on a Boolean. And in the program, we always invoke this with true, which means in particular that H is always going to refer to F. It's always going to get the first thing from choose. And so our web just consists of this one call and this one function, which means it's perfectly fine to delete this dead parameter. But if we do that, then we're left with F and G, which have two different arities, and choose still says that it could return either of them, even though that's technically not possible at runtime. But the underlying type analysis is having an issue with that because they have different arities, and there's no way to reconcile that. Well, unless you did some extra clever things with G. So I'm going to present a very simple type-based approach that's going to be really easy to implement and quite efficient. And we're going to see that it's quite efficient, or it's quite effective in practice as well. So it's super, super simple to do. You're going to take your annotated language, and in addition to annotating functions and calls, we're also going to annotate types. And when we modify the typing judgments, we're just going to make sure that the annotations line up between the functions and the arrow types, and between the calls and the arrow types. So we can see these, you have to have the same annotation. So the annotations on the arrow types are essentially carriers of proof that the function annotated with a certain web is going to match the annotation at the call site where it's eventually invoked. And that's the entire analysis. It's that simple. So for inference, it's also super easy. You're going to take your term and annotate it with fresh identifiers everywhere. And then you're going to type check the program and collect which of those identifiers have to be the same. And then you're going to merge them all together with something like a union find, and then
reality, you have a big chunk of revert rules that you want to apply. At some you don't want to store it multiple times for efficiency reasons, and that's more relevant for bigger terms, but so we store it just once and then reference it multiple times. Cool. And now what we just do is we take any rewrite that we have and just apply it in the eGraph. Let's say the first rule we have is a multiplication by 2 can be replaced by a shift by 1. And we see that we have a times 2 in the eGraph, so we want to apply it there. And when we've done this, we see that the a times 2 is not actually gone, so it's not a greedy rewrite, but we've rather added an equivalent way of saying, okay, this is also equivalent to a shift 1. So by this rule, we've now put both of these things, both of these nodes, into an equivalence class or e-class that now represents both of them together, which means from now on we will not differentiate between a times 2 and a shift 1, and they will just be considered the same, which makes this more compact. Cool. And now we really just do the same process over and over again, apply a rule, improve, apply a rule, etc. And in the end, we'll see that the initial term that we put in there, represented by this division operator, is now actually in the same equivalence class as a, which means we're done. We've actually done the optimization. Perfect. Now, the problem is this gets a bit harder when you have bound variables in your language, right? So a bound variable is really just, you have a binder, like a lambda, for example, that's introducing a local variable like x, and then this x is really, the meaning of x makes only sense in the body of that binder. And so the important property for bound variables is that the names you actually choose for the variables don't ever really matter. So you can always just rename them, and we'll see that this is something that eGraphs really struggle to understand to some extent. And I want to show this as an example. Consider the two terms, f of xy and f of x prime y prime, which are pretty much the same, except that they have different names of variables in them, right? So structurally, these are really the same terms. You can kind of, if you analyze them, you'll see kind of, you'll make the same conclusions, just that the conclusion will have x prime instead of x and y prime instead of y. So whatever you know about f of x and y, you can translate that knowledge directly over to f of x prime y prime, and it's really structurally the same thing. But when we see that we store this in an eGraph, we'll see how it's actually stored separately. So this knowledge that these are structurally the same term is not really exploited. So we actually pay with kind of storing it twice, storing a copy, and also analyzing it twice and like doing operations twice on it, which is costly, and we don't want to do that. And even worse, some of the rewrite rules we might apply might run into naming collisions, which then require us to actually do renamings. And as we've seen before, these renamings are exactly what creates copies, and that blows up the eGraph in size. That's unfortunate. So the typical trick to avoid this is to just say, okay, let's not do names, let's just do the Brown indices, then we don't have all of these problems, hopefully. And just a quick reminder how the Brown indices work. So we want a way to reference from the variable to the binder, right? That's the whole job of the Brown indices. Typically, we do this just by names, by just saying, well, the variable the variable y is representing, is pointing to the binder y, same thing for x. But in the Brown, because we don't want to have names, we rather say we just count outwards. So that means because y is the innermost binder, it's the Brown index 1, and because x is one more outside, we have to skip one more binder, it's the Brown index 2. So this term in the Brown notation looks like this, and wonderful, we've gotten rid of all the names. Perfect. But now, because the Brown index just count outwards the number of binders, if the number of binders changes because the revert rule is adding or removing one, we actually have to correct that binder. Sorry, we have to correct that Brown index, right? So we have a rule that adds or removes a binder. The Brown index needs to be shifted to actually correct for that offset. Typical example for this is beta reduction. That's eliminating the function binder, the lambda, that's actually being called. So you're kind of off by 1 if you don't correct the index now. And that's a problem because this index shifting, this correcting the Brown index, is again creating a copy because it's really similar to a variable rename that we've just seen before. So it doesn't really solve the problem that we had. And that's the key problem. If you repeatedly do index shifting because of the rules, you explode the eGraphs the same way, and it looks like this. That's the problem we want to solve. All right, now I want to see how we solve that. We solve eGraphs.
the very basic idea is we want to represent terms that are just equal up to renaming variables by the same parameterized e-class. And we want to parameterize these e-classes by the free variables that we have in them. And we want to make an example, like the same example we've seen before, for this conventional e-graph, which has this kind of copy of f of x and y and f of x prime y prime, we've just seen before. And the first thing we want to do is that these 4 variables that we have at the bottom, they're really structurally the same. So we want to represent by one object, by one parameterized e-class, which looks like this. Right. And as you can see, this parameterized e-class now has a header where we say this e-class actually depends on a variable v that you have to plug in. This is what we call a slot. That's why it's slotted e-graphs. So you have to kind of, whenever you reference this, you have to say what v is supposed to mean, and that differentiates between the different kinds of variable, x, y, x prime, y prime. Right, and this is just the general variable enode that's supposed to mean, well, I am the variable v. Right, and now, because we want to also represent f of x and y, we again have to convert that to a parameterized e-class, which now, because it has 2 free variables, x and y, should also have 2 parameters. We arbitrarily choose the names a and b, doesn't matter, and we get this e-class. So this, again, represents f of x and y, and f of x prime y prime. It's just one enode, the f enode, and because both of children of f are just variables, we have to point twice to the variable e-class. But in order to differentiate which variable we actually want there, we have to invoke the variable e-class by saying what v is. So in the first case, we say, well, we want the variable a on the left, and we want the variable b on the right. This is what these annotations on the edges mean, right? This has to match up with the parameters here in the variable e-class. Cool. And now, in order to make the intuition for that a bit more clear, I want to get back to what a conventional e-class is, first of all. So a conventional e-class really just is an equivalence class of terms. So it's supposed to represent a bunch of terms that are just equal. And this is slightly different from a slotted e-class because there's this extra level of parameterization. So what a slotted e-class is really a function that takes in some names, a, b, and then gives back an equivalence class using only these names. This means that if you call this with different inputs, you actually generate different equivalence classes, and this is kind of automatically spanning up infinitely many different equivalence classes. So something that would need to store manually otherwise, and is now kind of generally characterized. Cool. Now we can look into some more examples and some more features and challenges of slotted e-graphs because there's a couple of interesting edge cases. So I want to start first of all, start with binders. And I will start with the identity function lambda calculus as the kind of simplest canonical example, which looks like this if you draw it in a slotted graph. So you already know the bottom thing, that's the variable class, because we want a variable. But the new thing is this thing, which is a lambda binder. What it's doing is it's introducing a local variable, a local slot, x, and then because the body of the lambda is also just the variable x, we use this slot to then invoke the variable e-class with it. And that's pretty much already everything. One thing to point out is that this e-class does not depend on x as a parameter because we don't want lambda x dot x and lambda y dot y to open different equivalence classes, right? So this is supposed to be the same thing, alpha equivalence. So if you don't have the parameter, what this really means is that it's automatically covering all the renaming versions all at once. Because it's like if you change the name, it's not supposed to open a different equivalence class. So they're all covered in there automatically. And we'll see another case where this is going to be interesting in the next slide, which is the case where we multiply variables by 0, which is, well, we know what happens then. Whenever we multiply something by 0, it's going to be 0. So what we want to do is we want to merge the 0 e-class at the bottom with the x times 0 at the top, because they're equal, right? We just proved they're equal, so we should merge the classes. But it's kind of weird because x times 0 does depend on the parameter x, but 0 does not. So we have to kind of make a choice now. Should the final class actually depend on x or not? And we argue with that because x times 0 is equal to 0. It should not actually depend on x, and it will look like this. But now you might be a bit confused because the x is still there. Like the x is now nowhere defined, it just floats around there. But this is actually kind of the same we've seen in the previous slide, where if the slot is not part of the parameter list, what it really just means is all the renamings covered in one. So because whatever you multiply with 0, it's 0, this is automatically covering all the renamings of x times 0, which makes a lot of sense, I think. And yeah, so that's that. Now we come to the third feature, or the third interesting case, which is the case where we have the addition of two variables, two different variables. And well, we know if we have a plus b, we know that it's equal to b plus a. There's this symmetry. And so what this means, we want to merge the kind of the E-class representing a plus b with the E-class representing b plus a. But the problem is, well, they're already the same E-class, right? The generalized E-class is kind of covering both of them. So how do we merge the class with itself? What we kind of want to say is we want to say that this E-class should be equal to itself if you change the order of parameters. That's what we want to express somehow. And so we do exactly this. And we have this permutation group at the top, which is sometimes there, and often it's just one element. But this really just means that however you call this, whether you call this with AB or with BA, it's the same equivalence class that gets generated. So it's not actually opening different classes. So again, this class is really just a function, and then it has both versions, A plus B and B plus A, in them now. Cool. Now I want to come to the evaluation. We have 3 case studies, and I want to first of all start with the Rice array language. On the left side, you can see the grammar for the language, and it's pretty much lambda calculus. We just have a bunch of symbols that have kind of special meaning, but it's pretty much lambda calculus. On the right side, you can see how this looks in the implementation, and I think it's quite convenient. You can basically just translate the constructor from the left and put it to the right. One thing to point out is that, yeah, we have a special bind thing to say when you want to actually introduce a binder. But otherwise, this is like very similar to what egg is doing, and yeah, not much new, but it's quite convenient to define binders. Same thing for rewrite rules, where if you have here the LaTeX version of the rewrite rules, you can more or less kind of just write them the same way. Here you can, for example, define eta reduction. You have to be a bit more explicit with the kind of function application, because kind of function application is implicit in lambda calculus, so you have to write app here, which is maybe a bit annoying, but I think that's okay. And yeah, you can also do the side conditions, as you can see at the bottom. Right. And even for rules that are a bit more complicated, because they introduce a lambda, like you can see here, you can just write it, and it just works. So there's no problems like, oh, I have to shift the indices, or what variable do I actually choose? It doesn't matter. You just invent the variable, and it works. Don't have to think about it. And I think that's quite convenient. Cool. But now let's actually look at some real data. So at the top, you can see kind of a family of rewrite problems, which you can kind of blow up by making the number of function parameters longer and longer. And at the x-axis, we see exactly that, kind of the number of function parameters. And on the y-axis, we can see the time and memory that egg and slotted take to solve this problem. And egg is using the Brown indices in this case. And yeah, we can see that for this particular case, slotted does not really care if the number of function parameters is growing. And it's really hard on egg to Brown, because this particular problem is generating a lot of index shifts that are really hard to handle if you use the Brown. Yeah, and so we see in this case at least that's very, very efficient, very compact to use slotted. Yeah, let's get to a more real-world example where we have kind of more bigger, interesting programs from the STQL case study, which comes from database theory. And here on the left side, we see a bunch of examples, a bunch of programs we want to optimize. And you can always see in the white, we have the egg, the Brown baseline, and in gray, we have the slotted one. And the first thing I want to point out is that the number of iterations for slotted is consistently lower, right? And that makes sense because egg to Brown is investing a lot of iterations just to shift indices, which is happening a lot, and yeah, well, cost iterations to do. And so because this is just not happening, yeah, you just can do stuff in few iterations. Equivalently, you can also see that the number of nodes in E-classes is much lower in some cases, or it's always lower, but sometimes much lower, which makes sense because we kind of represent different things that are equal up to renaming now in one. So all these different copies are now compacted in one in the slotted implementation. Right, but you can still see in some cases that we still have slightly higher memory consumption than egg. And that makes sense because we pay some extra by having these slot annotations everywhere, right? That's an extra level of parameterization that costs stuff. You have to actually, that's an interaction you have to pay for. And if you're not getting something out of it because the de Brown is, in this case, not problematic, you're not winning anything. But you can also see that in some cases it is very much worth it. And you can get an up to 50x improvement on the memory cost. And in some cases, even, we do saturate with a rather small and efficient graph, whereas the baseline with the Brown is kind of getting bigger and bigger, and it's seemingly not going anywhere. Cool. Then the last case study, which is a quality saturation-based lean tactic that has a slotted and an egg backend. And yeah, what we can see here is that The slotted implementation tends to produce shorter proofs because, again, we don't have to do index shifting, and that's really something that seems to be the majority of the proofs if we have a lot of binders. And also, we have found a fancy example where we terminate in 1 second, and it takes a lot of time to not solve this problem, actually, which I think is very cool to have found that. Cool. Then finally, I would like to invite you to have a look at the paper, where we, first of all, define the slotted egraph data structure and talk about its algorithms a bit. But also what we did is we formalized a notion of congruence modular renaming, because egraphs normally work with congruence, and we need to extend this to understand kind of the notion of variables that we're interested in, modular renaming. And right, finally we have the case studies in more depth, and yeah, that's pretty much it. There's the paper and the implementation on GitHub. Have a look, and yeah, I'd like to hear your thoughts, so that's my mail. Thanks.
Questions? Someone?
I'm Herman Shi from JIA, and we are using. Thank you for your fantastic talk. We are currently using Egg in our production code base, and it has ad hoc treatment of bound variables. So I am really definitely give a try to it. And one question is that does thread egraph suppose relational e-matching or egraph?
Okay, so the kind of e-matching that we're using is the question?
Pardon?
The question is which kind of e-matching we're using?
Yeah.
Yeah, so we're really using kind of the most boring e-matching you can think of that we just kind of directly convert to slotted. So it's really normal top-down e-matching without any fancy optimizations. So yeah, the e-matching is not very competitive, but I think Nate is actually implementing a better version right now that's based on the one from Egg, but it's not using the relational yet. So not the typical database egg-log style. It's not that yet.
Is it on the I couldn't get it. So is it possible with this framework?
I think it should be, but I don't know. Like I
Okay,
didn't
so,
implement it yet. So
but not bad. Could be.
I don't see the problem. I think it should be possible, but yeah, we'll have to see.
Okay, thanks.
Yeah.
Thank you. Very exciting work. So I wonder if you have comments on, like you said, like the paper will mention about like imagining and rebuilding, but I wonder if you have intuition for example, if the imaging for the solitary egraph is more expensive, and as for rebuilding, I can imagine like rebuilding will involve some, you need to find correspondence between the variable names between two e-classes to merge them. And I can imagine it's a delicate procedure, like it may be incomplete. I just want to know like what's your intuition on the rest of the operations of the e-graphs.
Yeah, I see. So I feel like what's happening is that you can basically take the normal algorithms, but you have to kind of always do a bit more in the kind of inside when you always have to kind of, and then multiply this renaming on top of it to actually get the names right. But I feel like the structure of the overall algorithm really stays the same. And like, it's basically the same algorithms, but because you've mentioned rebuilding, there's one more notion where you have to kind of think of, like when you notice that a slot is redundant, which we've seen in the case where x times 0 equals 0, that you have to kind of propagate this upwards a bit. So there's kind of multiple notions of rebuilding now, because you're not only propagating equalities, but also you have to propagate that you're not depending on some parameter anymore. So kind of there's some new kinds of propagations happening in rebuilding, but I think algorithmically it doesn't really change that much. So
I see. So maybe one very specific example, say if you have variables AB, FAB, and BA, FBA, like would you merge these two together during rebuilding? Because like it seems one is an alpha renaming of the other.
So so generally, what we do is we have this kind of shape computation where when we have f of AB and f of BA, these will just be computed to f01 and f01, both of them. And then so we kind of split the names from it and give them a naming independent representation. And we just, like that's before rebuilding, that's happening all the time. So whenever we put something into the e-graph, the slotted e-graph, we will always get rid of the names first and have a naming independent representation that's kind of enumerating where the names were, and then having separate for that the renaming. So this is really something that's happening kind of very early in the process before rebuilding. Separate it.
I see. Thanks.
All right. I think we had a very exciting talk. So thank you very much, Rudy.
Thanks.
Yeah. And it's lunchtime, so opportunity to talk about things with all the speakers. Great.
Okay. Hello, everyone. Thanks for joining the security session. I'm Thomas, and I will be chairing the session from EPFL. So we will start from with a talk on differential privacy by Marcus de Medeiros. He's now at AWS. And all the talks are 20 minutes. There was no strong guidelines on the length of the talk versus the question, so we will be around 16, 17 minutes for the talk, and then the rest for questions. Thank you. The floor is yours.
All right. Thank you, Thomas, for that introduction. I'm Marcus. I'm a PhD student at NYU and a research intern at AWS. Today I'm going to be telling you about SAMCERT, our project for doing verified differential privacy in Lean. Okay, imagine you're a statistician. You can picture that your day job amounts to collecting data from public and private sources, organizing and computing over that data, and finally, generating some statistics and decisions based on your data, which you send out to the public. So given that your data may be private, you want to ensure that your statistics don't accidentally release any information that you don't mean to. For example, you might work at the US Census Bureau. It could be okay to release the maximum income reported by a zip code, but not the income reported by each address. Okay, now in a perfect world, every statistic you release would only disclose the aggregate information about your data set that you meant to. However, and I hope this isn't a shock in the security session, but the world is far from perfect. Attackers have found very clever ways to learn a great deal of sensitive information using only unintentional data leaks in innocuous-looking statistics. So going back to my example, knowing the maximum income reported in a zip code also tells an attacker that somebody with that precise income does live in that zip code. This, on its own, can be enough to identify them. By leveraging automated constraint solvers and correlations with public knowledge, attackers have managed to target and re-identify individuals even in real-life data sets which use traditional anonymization techniques. Okay, so what can be done about this? Well, privacy researchers have defined this notion called differential privacy, which establishes a bound on the amount of information that an attacker can learn about your data set given any statistic. While these re-identification attacks are remarkably effective, it turns out that they're also very brittle. And so by adding the right amount and the right kind of random noise to your statistic, you can ensure that even very strong attackers will learn very little about your true data. Okay, so that's great, right? Problem solved? No, sadly. There's still, 16 minutes left here. Well, everything I've said so far is true on paper. That, of course, doesn't necessarily mean that it's true of your code. So on the slide, I have the Laplace distribution. It's a continuous probability distribution that you might want to draw samples from in the process of making your statistic private. And you can implement a Laplace sampler using traditional floating point techniques. On this scale, your distribution will look fine. However, in the early 2010s, a researcher named Ilya Mironov discovered that when you zoom down to the bit level, you see that some values are sampled with the incorrect probability and other values never get sampled at all. Mironov used the gaps in this distribution to mount a re-identification attack, which affected several of the commercially available differential privacy libraries at the time. Now, since then, many of them have patched this exploit, and many other exploits have been found. But the point I really want to impress upon you here is that in differential privacy, even tiny deviations from the algorithm that you've analyzed on paper can severely affect the security of your entire system. At AWS, we offer a service called Clean Rooms. Clean Rooms lets our customers compute over and privately share statistics about their data. So naturally, we want to deliver them the highest degree of security that we can. To that end, we decided to verify some of the components of Clean Rooms related to differential privacy. So here's our problem. We want foundational verification. We don't want to, for example, assume that floating points are an accurate representation of the reals. We want to make use of the large body of existing theory in differential privacy. Our job is to not come up with new differentially private algorithms, but have high assurance implementations, the things privacy researchers have already figured out. And finally, we want an implementation which our privacy team will be able to integrate into our existing services. And of course, because this is AWS, this means our implementation has to be efficient at scale as well. Our answer to this challenge is SAMCERT. SAMCERT is a differential privacy library written and verified in Lean. It uses the large body of verified mathematics provided to us by MathLib in order to mechanize even recent privacy research. And finally, the compiled code that we get out of SAMCERT is competitive enough in terms of performance to be used and is currently deployed at AWS. Okay, so for the rest of this talk, I'm going to walk through the components of SAMCERT from the ground up, and I'll highlight what we think makes SAMCERT an effective way to get these concrete privacy guarantees in practice. So to start off, the real beating heart of all differential privacy is the ability to generate specific kinds of random noise. So we're going to begin by formalizing the semantics of a probabilistic programming language. A probabilistic program is one which, when executed, draws a sample from some probability distribution. There are many ways to represent these languages, but for us, we're going to use what's known as a shallow embedding into mass functions. This means that in Lean, we represent all of our probabilistic programs as Lean functions from a type to the real numbers. And this represents the probability of sampling any given point. To construct these mass functions, we're going to define a small DSL, which consists of 4 basic constructs. The return operator sample is a mass function which samples a single value with probability 1. The uniform byte operator samples uniformly from the first 2 to the 8 natural numbers. The bind function is a monadic bind, which allows us to sequence 2 random computations. Finally, we have a while construct, which is defined mathematically as a limit and allows us to simulate the effect of executing an unbounded probabilistic loop. Okay, so despite the simplicity of this language, we found that it was enough to encode the kind of sampling algorithms that we found in the literature. For our application, the programs we want to verify are all small, stateless, first-order programs, which nevertheless have security proofs which are quite mathematically involved. Okay, so what I want to stress here is that when we write code using our DSL, what we're really doing is describing a particular mass function to Lean. This means that in SAMCERT, we can encode programs, specifications, and proofs all in the language of plain Lean terms, and then we can make use of Lean's well-established techniques for mechanizing mathematics to get the program correctness proofs we're after. I'll give you an example. So in differential privacy, you often want to sample from this distribution. It's called the discrete Gaussian. The discrete Gaussian was developed in the early 2020s as an alternative to the continuous distributions I was talking about earlier. So the formula I have on the slides is a little scary. It involves, I don't know, transcendental numbers, big sums, division between reals. But there's also a very clever algorithm developed by Keynote, Kamath, and Steinke for sampling exactly from this distribution. Okay, so what we do in SAMCERT is we translate this function, or this program, into a mass function by writing it in our DSL. We can turn the specification into a mass function by writing down that formula. And then finally, our verification challenge is to prove that the mass functions for our program and for our specification are mathematically equal. Again, this is a hard problem in general, but we can lean on the fact that we've embedded ourselves in a very rich mathematical landscape, and we can use the math afforded to us by MATLib to mechanize the proof from the Keynote, Kamath, and Steinke paper as well. Okay, a couple more words about this shallow embeddings point. We found time and time again that the modularity afforded to us by this proof technique was very useful. Once we've proven that a program and its specification are equal, it means that we're able to use them interchangeably throughout the rest of our code base. So for one, this means we get functional modularity for free. We can always rewrite a program into its spec in any Lean code which uses it. It also means that for proving program properties like termination, normalization, and support, we're able to prove them about the specification instead of proving them about the program. So it can be easier to just analyze the PMF of a spec rather than trying to come up with proof rules that work with loops, for example. Okay, finally, this means that we're free to switch between different optimized versions of our program. And we do this in SAMCERT. Late in the development, we found an alternative way to sample from the Laplace distribution. And so we were able to add on dynamic switching between these different sampling algorithms because in Lean, mathematically, they're all equal. We didn't have to redo any of our security proofs. Okay, so we've built up this language for expressing and reasoning about probabilistic programs. Now we want to start talking about privacy. As I alluded to before, a differentially private program is one which produces a randomized value from a database such that the output is not too sensitive to the contributions of individuals. More concretely, a program is epsilon differentially private when for any 2 databases that differ by 1 row, the resulting probability distributions will be within epsilon of each other. Intuitively, when epsilon is small, an attacker would need a huge number of samples in order to determine which distribution the program is sampling from, and therefore which database contains our true values. Okay, so you might notice that there are some air quotes on the slide here. And so while it is true that privacy researchers, generally speaking, agree of this type of framework, there are a lot of variants for what within epsilon is supposed to mean. So on the slide, I have a selection of them, but don't worry, there are even more. And they all provide slightly different privacy guarantees, slightly different composition theorems, and there's many different conversions found between them. It's quite a situation. Okay, so despite this, we noticed that at a high level, there's a common collection of features that these definitions tend to share, and that a lot of differentially private programs tend to rely on. So in SAMSER, we collected these features together into an interface we call abstract differential privacy. The interface has three parts. For one, it parameterizes by a proposition of one real valued parameter, which is meant to define how you measure the privacy of a noisy query over a database. Our interface requires that your definition for differential privacy obey a set of rules, in particular adaptive composition, post-processing, and the constant rule. And then finally, our interface requires that you have to have some way to make a query over integers private. So in particular, we require that for any integer valued query over a database that has an upper bound on how sensitive the function is to changing individual rows in the database, there must exist some noise distribution so that your query plus that noise is epsilon differentially private. In SAMSER, we've instantiated this interface with the two variants that we most care about at AWS. That is pure DP with noise drawn from a discrete Laplace operator, and zero concentrated DP with noise drawn from the discrete Gaussian. There are other variants of DP, which we are pretty confident fit into this framework, but we just haven't mechanized them. And the proofs that these DP systems satisfy these bounds are mathematically quite involved. So in particular, the zero concentrated differential privacy proofs involved like Jensen's inequality and Fourier analysis. Using the math that we found in MATLib, we were able to replicate these proofs from the literature, which saved us a lot of thinking. Okay, to finish up this section, I'll just quickly show you what this interface can do. On the slide, I've got a small program which builds a histogram out of your data and then makes it private by adding noise to the count in each bin. Now, I won't get into the proof in too much granularity here, but if you kind of go through it step by step and apply the rules from the interface, you end up with an abstract privacy bound, which applies no matter which instance you use. I can speak more to the pros and cons of this afterwards. I'll say that it's nowhere near a complete proof system, but we found that because so many of these definitions share these common features, you're able to generalize some of the proofs that you might see in the literature, and get guarantees that apply for all of these different variants. Okay. So finally, we've developed this theory of differential privacy in Lean. We want to actually deploy it out in the world. You'll recall that we've shallowly embedded our programs into this type of mass functions. And so in Lean terminology, this type is non-computable. It's just a function from a type into the real numbers. The Lean compiler doesn't know how to get a binary out of these functions, and it definitely doesn't know how to interpret them as probabilistic programs. But you'll also remember that our programs were not just general or just arbitrary mass functions. We decided to write them using this little DSL. Okay, so this carves out a subset of these mass functions, which are distinguished by the characteristic that they do have a known sampling algorithm. So how do we make use of this? Well, the 4 terms in our DSL were chosen not just because they were straightforward to reason about mathematically, but also because they tightly correspond to the terms in an imperative programming language. So in SAMSER, we're able to use the Lean foreign function interface to attach a C++ implementation for each of these terms. And this means that Lean can then compile PMFs that we write in terms of this DSL into genuine randomized programs. I mean, in Lean terminology, we're able to remove the non-computable marker once we do this. Even once you add back in all of the Lean boilerplate you need, this amounts to around 50 lines of trusted C++ code, which mostly amounts to ensuring that you apply the right functions to each other in the right order. And it's well within what we consider acceptable from a security standpoint. OK, so what does this 50 lines get us? Well, at the beginning, I asked you to imagine you're a statistician. So I hope at the end here you'll enjoy a graph. Here we've got the performance of our discrete Gaussian sampler compared against the publicly available implementations that we were able to find. Our extracted code has performance which is competitive with these publicly available libraries. And of course, our implementation is substantially more robust because it's derived from a verified implementation. Not to put too fine a point on it here, but the code that we're running to produce this graph is currently deployed as part of clean rooms. OK, I think that's just about my time. So thank you for your attention, and I'd be super happy to take any questions.
Any questions? Should go to the mic.
Hi, thank you for the very nice presentation. So you started the talk by showing that sort of the discrete Laplace has some floating point error and that loses the guarantees. But your lean system formalizes the samplers over real numbers. When you extract the C++ code, are you careful about the floating point errors? Are you using arbitrary precision, rational arithmetic? Can you clarify that gap?
Yeah, so our samplers that we extract are over the integers. They're not over the real numbers. So we use the discrete distributions, and so we avoid using floating point numbers in that case. The type of our PMFs is t to the real numbers, but we interpret them as a randomized value of type t. So we don't have to interpret the real numbers in order to execute them. We do think that floating point calculations could fit into this framework. I mean, probabilistically, it's fine. They're countable and discrete. But we haven't done any of that work. We'd be interested to in the future. Does that answer your question? Or?
I was maybe wondering that the probabilities are real numbers.
Yes.
Right?
Yeah.
So it's true that it's a discrete Gaussian over the integers, but
yeah.
the individual probabilities are reals. They're irrational.
That's exactly right. That's exactly right. So the sampling algorithms we use, they all use rational arithmetic. Mm-hmm. There's no interpretation of reals in that case.
I see. And then all of the other operations in the DSL, maybe if you add numbers or divide them, etc., you are also not suffering from numerical error?
Exactly. They're all exact.
All exact.
They're all exact.
Very
yeah.
good. Thank you.
Thank you so much. So in this slide, at the last bullet point, it is stating that this is deployed at AWS.
Right.
How much can you disclose what kind of real-world application there is a demand for the DP? And then in what scale did you address the problem? Thank you.
Yeah, sure. So there's not much I can talk about, mostly because I wasn't the one who did I worked in Lean. I didn't do the crazy stuff of actually getting it out there. I know that the sampling algorithms, our implementation of those are definitely deployed. And then I think the idea is over time to get higher assurance for the rest of the differential privacy suite, but I'm not sure that those are in use right now. Yeah.
Hi, thanks for the nice talk. About the C++ extraction, basically. So just from the snippets you showed, that basically looked like you're taking the pure Lean program and embedding it into I/O. Could that have been a meta program in Lean as well?
So yes, and that's what we did at first. But when you use a meta program, you also have to translate all of the rest of the pure Lean code as well, right? Like if I do integer, well, okay. If you wanted to go within Lean, yes, I think that could be a meta program, and that would be sort of interesting. We used a meta program at first to go from Lean to Daphne for other deployment reasons, and then we ran into issues where we had to do meta programming that the Lean compiler was already doing, like compiling Lean edition to Daphne edition,
right.
which was quite a nuisance. But it could be interesting to go Lean to I/O Lean.
Yeah, could even be faster than the applied codes.
Yeah, cool.
Thanks.
Good suggestion.
Okay, let's thank our speaker again.
Is it okay?
Yeah, perfect. Okay, so the next talk is about exploit generation across Node.js packages, and the presenter is Philippe Marques, and we are ahead of time, so you have even 10 seconds to breathe before starting.
Thank you so much for the presentation, Thomas. So hello, everyone. My name is Philippe Marques, and today I'll be presenting our work on automated exploit generation for Node.js packages. This is actually joint work together with my colleagues at Ineshkide and CMU. So let me begin by introducing Node.js. Node.js is an open source runtime that runs JavaScript outside the browser. This makes it ideal for writing scalable server-side applications. And plus, Node.js is hugely popular. It ranked the most used web framework in the latest Stack Overflow developer survey. And it also plays a key role in modern full-stack architectures. And plus, it's been adopted widely across the industry. Node.js also has a rich package ecosystem. Its primary package manager, NPM, is the most widely used in the world. Currently, it hosts over 2.5 million packages. As a result, most Node.js applications today actually rely on these third-party packages. These packages, as a recent study highlights, a critical concern, these packages are often vulnerable. In fact, the GitHub advisory database has issued over 3,900 advisories affecting NPM packages. And these vulnerabilities can have serious consequences in practice. So over the years, we've actually seen several high-profile attacks targeting these NPM packages. And these cases highlight how one bad package can actually affect thousands of packages downstream. So, motivated by these risks, many tools have been developed to detect vulnerabilities in these NPM packages. And these tools have achieved some success. So many can actually detect a large portion of known vulnerabilities. However, they all suffer from the same fate. So they have high false positive rates. This means that developers are actually forced to manually inspect and triage each vulnerability to discard the false vulnerabilities. What this does is, over time, it leads to frustration and a loss of trust in these tools, ultimately resulting in poor adoption and, most importantly, many vulnerabilities remaining unfixed. And so, our goal is to improve the precision of these tools without sacrificing recall. So, to achieve this, our approach is to automatically generate a proof of concept exploit. So, by doing so, what we do is that we show that the vulnerability is both real and reproducible. This actually makes vulnerability reports more concrete and actionable, and actually helps developers quickly validate and also prioritize the issues. However, actually automatically generating this proof of concept exploits is difficult and comes with a major set of challenges. So first, the first challenge is that the exploit must actually invoke the function where the vulnerability actually lies. So current approaches only succeed when the vulnerable function is directly exported by an NPM package. But in many real-world cases, the vulnerable function is only reached after multiple interactions with the library. So here's an example illustrating this. The vulnerability is only called after the last method call. It's a pretty basic example with a trivial payload, but current tools cannot generate exploits for this. Secondly, scalability is crucial when dealing with many important packages. So current tools will either try to execute all the dependencies, which is often too expensive, or they simply ignored it. And both approaches have drawbacks. So either they have poor performance or missed vulnerabilities. Finally, current tools only focus on generating simple exploit payloads. So they don't support configuring payloads to fit specific patterns that may be required by the underlying code. So for example, consider a vulnerability where the payload must be injected inside a return statement that will be evaluated by the eval function in JavaScript. So actually, to succeed, the payload will need to be wrapped inside something like an anonymous function that will be executed immediately. Again, no existing tool can generate this type of exploit. And so, for these reasons, we've created Explo.js. Explo.js is a novel automated exploit generation tool that is capable of generating complex text drivers that can trigger vulnerabilities deep within a package. Explo.js also scales efficiently even when many important packages are involved. Plus, Explo.js is also able to compute these non-trivial payloads tailored to specific sensitive things. So currently, Exploit.js only supports 4 types of vulnerabilities: path traversal, code injection, command injection, and also prototype pollution. And our evaluation demonstrates that Exploit.js outperforms existing tools, generating 300% more exploits than fast, and also 500% more exploits than Node-Medic Fine. Exploit.js has also discovered 44 new zero-day vulnerabilities, and these include 3 CVEs and 1 GitHub security advisory. Let me now walk you through the design of Exploit.js. So we'll start with a motivating example. You can see the vulnerable package here on the right, or maybe your left, and the exploit over here. So actually, don't worry about understanding all the details of the vulnerable package. Let's just focus on the exploit and how it works. So the first thing the exploit does is it actually requires the vulnerable package. Then it creates a new instance of this file transfer class. It prepares some data, and then it defines this user object with a host property and also a specially crafted dir property string. Finally, the code will execute this run method with our user object, which, due to improper sanitization, will flow into the exec function, which is actually a known vulnerable command injection function. So the payload that we injected to our dir property string, which is passed by our user object, is actually a typical command injection payload. So it will actually attempt to create a file named success in the file system, which is actually a common technique used to signal that arbitrary command injection has been achieved. And moving on to the architecture, the way that Exploit.js generates these types of exploits is actually through a 2-stage pipeline. So the first stage is the exploit template generator. It essentially starts by taking an npm package and produces these symbolic exploit templates that will serve as the starting point for exploit generation. And then in the second stage is the exploit template resolver, and we try to find the concrete values, such as the concrete payload and also function inputs that make the template fully executable and try to trigger the vulnerability. So we start in the exploit template generator, and its first goal is actually to automatically determine how to interact with an npm package. So the output of this stage will be called a vulnerable interaction scheme, or for short, VIS. And as shown on this slide, a vulnerable interaction scheme is essentially a chain of function calls along with the required argument types that sets up the conditions necessary to trigger the vulnerability. With the VIS, we can now compile it into an exploit template. And essentially, an exploit template is an executable symbolic test where the inputs to the functions are symbolic values. And its purpose will be to drive a symbolic execution engine to explore the program and discover how we can trigger the vulnerability. If you see, this actually solves our first challenge in generating a test that can actually try to reach the vulnerability. So that brings us to stage 2, the exploit template resolver. So in this stage, we will begin by performing lazy symbolic execution of the templates we've created previously. So actually, the lazy symbolic execution is what will allow us to perform the exploration of the paths without actually running any of the third-party code. So crucially, this will avoid missing potential vulnerability and allows our analysis to scale, which consequentially solves our second challenge, which is the scalability in the presence of many imported packages. So finally, when the execution path successfully reaches a vulnerable sink, symbolic execution will produce something that we call a symbolic outcome. And a symbolic outcome summarizes the detected vulnerability by telling us 3 things. So the sink that we reached, the conditions that were necessary to reach it, or simply the path that was taken, and actually the symbolic inputs that trigger the vulnerability. using this symbolic outcome, we can now create an SMT query. And this SMT query is responsible by encoding the path constraints needed to actually reach the vulnerable code, and also the constraints that will ensure the well-formed-ness of our payload. So this is actually a very simple example where the symbolic input that reached the exact function with unsanitized inputs. So we can simply sequence an attack to the current command and ensure that it is well-formed. So while this attack actually uses straightforward attack pattern, Explode.js is parameterized to actually allow for writing more sophisticated attack patterns. And consequently, this actually allows us to solve the third challenge that we presented. Finally, we then pass this SMT query into an SMT solver, which, if it is satisfiable, will return a satisfying assignment. So, using this assignment, we can now instantiate the symbolic, the exploit template into a fully concrete exploit. To this end, in the exploit template, we simply need to replace the symbolic values with the concrete values from the model. And lastly, what we need to do is actually execute the concrete exploit and observe the intended side effects. So in this case, what this means is, for this type of exploit, we simply verify that a file named success was actually created in the current file system. So let's now look at how Explode.js actually performs in practice. So we evaluated Explode.js with respect to 4 main research questions, but in this presentation, I will only focus on the first 2. So how effective is Explode.js at generating exploits? And can Explode.js find zero-day vulnerabilities in real-world NPM packages? So to evaluate Explode.js, we actually used 2 well-established vulnerability datasets that were actually used to evaluate previous related work. So we used Vulkan and Secbench. And because these datasets actually contain real-world CVEs, they provide a representative and also realistic benchmark for assessing these automated exploit generation tools. So when evaluating effectiveness on the ground truth datasets, we show our recall and also our exploit rate. And when inspecting each of the vulnerability categories, we see that Explode.js consistently outperforms existing tools across every vulnerability category. And overall, Explode.js generated exploit for 46% of the vulnerabilities in the dataset, which is 4 times the exploit generated by FAST, and also 6 times the exploit generated by Nodematic. Then, we actually ran Explode.js on a dataset comprising of 32,000 popular NPM packages, and we started out by detecting 291 symbolic paths that reached the sink, but Explode.js was only capable of generating 125 exploits. So out of these 125 exploits, only 46 were confirmed to enable malicious actions. So what I mean by this is that these 46 exploits actually triggered behavior that was not originally intended by the original package logic. Out of these 46, 2 had already been reported as vulnerabilities, and we responsibly disclosed the remaining ones. And to this date, this has resulted in 3 CVEs and 1 GitHub security advisory. So, in summary, we actually propose Explode.js, a novel tool for automatic exploit generation, targeting Node.js packages that can generate complex test drivers, even when the vulnerable function is not directly exposed by the module. It scales efficiently even in the presence of many imported packages, and that is able to compute non-trivial payloads tailored to specific sensitive sync context. In terms of results, as I've just said, it generated exploits for 46% of the ground truth datasets. That's 300% more than FAST and also 500% more than Nodematic Find. Beyond the benchmarks, it was able to discover 44 previously unknown vulnerabilities with 3 CVEs and 1 GitHub security advisory, having already been assigned as the result of our disclosures. So finally, if you're interested in the deeper technical details, I encourage you to check out our paper. In the paper, I actually go beyond what I could cover here today and include the algorithm we use to compute the vulnerable interaction schemes, the formalization of the lazy value semantics, a brief catalog of the exploit attack patterns that we support, a more detailed evaluation, including the performance benchmarks, and also a candid discussion of limitations and avenues for future work. Thank you all for listening.
Any question? You should go to the mic. I don't know if it's a question or if people are, yes.
Hello, Konstantinos Kalas from UCLA. Very cool work. I wanted to ask, could you give us some example of an interesting and more complex attack pattern?
I could give you one right now, but it's a very brief example. When you consider, for example, code injection, you could have, or at least something that we found experimentally is something, for instance, you have an object and then you do a property access, right? You do a dot or a member expression, you have a member expression, you have a dot and then nothing else. So you actually have to complete this type of expressions, right? So we could write an attack pattern, something that says you actually have to have a syntactic construct that makes this first expression valid, and then you could sequence actually an attack.
I see.
Something like that.
And also for this, for the attack patterns, you have to, the user has to also specify how to verify that, that there was successful exploit in the end for its pattern, right? Or
I guess not really, because it depends. So Exploit.js actually first detects the type of vulnerability, right? So you write an attack pattern. For instance, the one I said was for code injection. But actually, Exploit.js detects the type of vulnerability in the code. And when the exploit runs, what is intended is to verify the side effect of the vulnerability that it detected. So if it was code injection, what we expect is also as command injection that the file is created on the file system. So you have to write the attack pattern such that the payload does what it's expected to do, right? So
thank you.
It's a bit hard-coded that.
Oh, cool. Okay. You mentioned that there's 4 classes of vulnerabilities that your tool is able to detect. Do you have some insight as to like how this compares to all the vulnerabilities out there? Like, is this representative? Are there like large classes of things that this doesn't work with, or?
I mean, these were the ones that mostly focused on the detection part. So we had previous work in PLDI last year that focused on detecting this type of 4 vulnerabilities, which we found to be the most representative ones on Node.js. Right, so we focus on those. We could do maybe for redos and support some other type of vulnerabilities, but it was hard enough already for this one. So, sure. Yeah, thank you so much for the question.
Maybe I have one more question. So you reported 44 bugs you found, but then 4 CVEs. Is it because multiple are the 3 CVEs and 1 notice? Is it because some of them were redundant? Is it some of those bugs were redundant? Why is the mismatch between?
Sorry to interrupt, but actually some like package maintainers and developers, they said, okay, we acknowledge this is an issue, but we don't actually expect that people use our library this way. And so we're not going to actually say this is a vulnerability unless you give us an example of a package that actually uses this in a way that could be exploited. So they essentially don't believe it is something that is exploitable.
Let's thank our speaker again. Yeah. Oh, and Felipe said that he is looking for an internship next summer. Okay. So our next speaker is Matthew Kolozik, and we will actually hear about constant time in 2 talks in this session. But for this one, it's about robust constant time. So then we will ask the following: what is not robust about the definition? I believe that you are on the industry job market.
Yes.
So the floor is yours.
Hello, I'm Matthew. I just graduated from UC San Diego, and this is my work on robust constant time cryptography in collaboration with a number of co-authors. So I'll give you the introduction to constant time cryptography. So as we all know, cryptographic code underlies pretty much everything about security in anything internet or distributed at all. And broadly, we can think of cryptographic code as we have some like message encryption and there's some secret key. But crucially, when this code is actually running, we have it running on actual software and hardware. So we want to make sure attackers can't steal our secret keys even if the cryptographic code itself works. And to this end, we need to worry about things called side channel attacks. So this is, for instance, if this encryption function for 2 different keys ran in different amounts of time, then an attacker who can measure how long the function takes to run can figure out which key was input. And the security property related to this is what's called constant time. So if the encryption function worked like this, then it would not be constant time. However, if for all inputs, all secret inputs, the runtime or sort of these side channels were the same, then this code would be constant time. And a really nice thing about constant time is it gets us a bunch of design principles. So this is a very simplified version of some actual code from the libsodium library. And constant time has these rules of thumb that we can follow. So you do things like don't branch on secrets, don't use secrets as pointers, and only use constant time operations. And together, this ensures that your code is constant time. And so this code is constant time. It won't leak secrets through side channels. But I want to draw your attention to this line here, this mem0, which appears in the actual libsodium, and it has nothing to do with constant time. And before we get to this, I want to remind you of sort of a lesson, a mantra in cryptographic code, which is don't roll your own crypto. And we see throughout history that when people try to sort of write their own cryptographic algorithms and protocols, it's very difficult and you tend to get it wrong. And what this leads to is that the reality of cryptographic code is that it's written as libraries by sort of cryptographic developers and then used by the rest of us. So that is, cryptographic code doesn't just look like this nice little encryption function. It is a function being used in an application by those of us who do not write cryptographic code. And this means that constant time, the model of classic constant time, is these keys are just treated as arguments to cryptographic function. But the reality is these keys live somewhere in the memory of the application itself. And then security of the whole system depends on application behavior too. So a buffer overflow within your application that can access those keys is still access to those keys even outside of timing behavior. And the thing is, cryptographic developers are thinking about this. So that line, that memory zeroing from libsodium is making sure that a stack overflow on a stack overflow doesn't leak this secret information value. And in particular, libsodium uses throughout the library a bunch of secure memory clearing for these temporary secrets. Further, they provide a bunch of guarded heap allocation APIs to ensure that these secrets can be protected at rest. So you might say, just write your applications in Rust. This means that we don't have to worry about buffer overflows and things. However, in the modern era, we also have to worry about things like Spectre and speculative execution, which sort of break all of our assumptions of memory safety, and also, to the side, ruin many of our rules of thumb about building constant time cryptographic libraries. So with classic constant time, we have a security property that captures there's no side channels in the crypto functions, but this doesn't capture the larger picture. So we propose instead that the security property that you really care about is what we call robust constant time. That is, the library must be secure when linked against an entire application. And by switching to this setting, this lets us model different attackers. So are there read vulnerabilities? Do you care about Spectre? Is there a concurrent thread who might be observing what's happening? And by doing this, we can sort of capture which things a cryptographic library should be concerned about. And further, we use this to design a compiler that lets us sort of pull these security concerns out of the library itself and automatically protect cryptographic libraries. So in the rest of this talk, I'm going to talk about how we actually define robust constant time, look at how we model speculative execution and constant time for this project, and then finally talk about our robust constant time compiler. So robust constant time. So we've got 2 parts. We've got libraries and applications that need to fit together. So to model libraries, we just say, first we start with an API, so the set of functions that the library provides, and a set of secret contexts. So these are the keys and secret information that you want to keep secure. Libraries then implement these APIs and can use these secrets and contexts. On the other hand, the application simply uses functions from this library API. And in our model, we use a block-based memory model, which gives us a way to model sort of overflows as access beyond the edge of the block. Further, we build a model of memory protection instructions, which we're going to use to build secure compilers. To define robust constant time, we then start with a library that we want to ensure is secure. We consider all applications and pairs of keys, so we must consider any application this library can be plugged into. And then the whole program plugging in must have the same traces, so must have constant time behavior. If so, this library is robustly constant time. But I want to focus in on this for all applications, because the reality is cryptographic libraries are used in many different application contexts, C applications, Rust applications, etc. And this means that you might have different sets of assumptions about what's going on in the application. Are there read gadgets? Are there write gadgets? Are we on a speculative processor? Is there a concurrent thread? So we don't want this sort of broad for all applications, and instead want to model different attackers as a restricted set of contexts that we care about. And in particular, we're going to restrict based on assumptions about how the application behaves, as we talked about earlier. And in particular, these are going to capture actions that the application can or cannot do. And in the paper, we instantiate for several particular application assumptions, including memory unsafe attackers, which can read or write out of bounds and are essentially unbounded attackers, having read gadgets, which can only read out of bounds but can't take these sort of more active attacks, and then memory safe attackers. So these are applications like Rust. We further model both speculative execution and concurrent observers as sort of a separate class of attacker models that are going to be related to having read gadgets. Formally, these are properties about the application, but the problem when modeling this is that applications have a hole where the library goes, so we can't actually run these. So our idea then is to capture assumptions in the application as something that must hold for all well-behaved libraries. That is, we can separate our trace into a back and forth between application and library, and for instance, memory safety, that is that there's no out-of-bounds behavior in the application. We require that there's no out-of-bounds behavior, but then we may assume that the library behaves properly and then that our trace continues accordingly. Capturing robust constant time for memory safe attackers then is simply for all applications that are memory safe for all well-behaved libraries. We have this constant time property, and our other properties defined similarly. Speculative execution, on the other hand, requires a little bit more complicated model. And for those who don't know, speculative execution is sort of a more recent attack vector where modern processors in running speculate on which branch to take. So for instance, if we have this bounds buffer check, this is generally going to be the case that most indices that are checked are below the length of the buffer, and so this code generally takes the if branch. However, if an attacker can influence, like, okay, we're going to pass something outside the bounds of the buffer, the processor will speculatively start executing code. It's like, okay, we're typically taking the if branch, so let's just start running that. And the problem is, eventually the processor will realize that the guess was wrong and roll it back, but traces of this path, the sort of erroneous execution where we read out of bounds, still remain. And the problem with this is that it breaks all of our assumptions. We can't necessarily rely on applications being memory safe anymore because speculatively, they probably aren't. And to deal with this, we captured a notion of speculative robust constant time by defining a high-level speculative semantics for our language and capture sort of a broad essence of Spectre and speculative execution with a speculator. So this is going to let us capture different versions of Spectre. So for instance, the classic Spectre v1 attack where we do this bounds buffer bypass, or bounds check bypass, what's going to happen is the speculative model lets you sort of guess the speculator, the attacker, guess the result of an expression. So here, you would guess false, or sorry, guess true for this, and then continue running, even if the index is out of bounds. Versus for Spectre v4, store to low forwarding, we can capture with the exact same mechanism, where it is simply guessing the prior load value and continuing as though a previous write had not occurred, and then continuing forward. Speculative robust constant time is then just robust constant time in this attacker model. So lastly, we use these ideas to build a robust constant time compiler. And so this is coming from, there's lots of different attackers, and this leads to a lot of different protections. Unfortunately, there's no one fast solution. And what we found is that current libraries are making basically one choice of an attacker that they're concerned about. So libsodium has these memory zeros, but there's a sort of closed issue where someone points out, oh, this is missing a memory barrier, a fence, that would be needed to make this speculatively safe. And they go like, okay, Sure, that's true. But if we did that, then we would protect against Spectre, but many people don't care about that, and it would slow everything down. So coming from the PL world, we know that we have a solution to this, which is like, let's pull this choice out of the code, and instead build a compiler where you get to parameterize what your attacker model is. And we build this on LLVM and Clang. This way you can choose what you're protecting against based on where you're deploying. So to sort of high level go over this, I'm going to talk about our read-only attacker mode first. And so the sort of high level of how this works is we're going to start by allocating all of the secrets in a protected memory region. Then when we're going to be actually running the cryptographic code, we're going to switch to a protected stack so that we only allow access to protected memory while we're running within the library. Then when you return to the application itself, we're going to switch back to the program stack. But this ensures that all secrets are kept basically only existing while you are running within the library. And this is separate from constant time itself, so the constant time of the library is sort of orthogonal to our protections. In speculative mode is very similar. We just also must do things like fencing to prevent speculation crossing these boundaries. And in this case, you must bring your own speculative constant time. In the paper, we show how to prove a Robocop secure by building a logical relation that semantically interprets traces and proving that each of our parameterized compilers gives the respective robust constant time property. Lastly, so we implement this compiler in LLVM and Clang, and we measure using the SuperCop benchmark suite what the overhead is on approximately 500 algorithms. And we find that the median overhead for both our read-only and speculative protections is about 0.13%, so very low cost for these algorithms, and 75% of our overheads are below 2% for the read-only protections and 4% for speculative, where the fencing sometimes causes a slightly higher slowdown. So thank you. That's our work on robust constant time cryptography, and you can find this paper at the link below.
Any question?
Hello. Yes, thanks a lot for interesting talks. So, but I have one aspect that I have to argue with you is that Spectre being considered to be the recent or contemporary, because I'm from the security domain, and then this has been very popular for the last decade, and then most of those were addressed, or unnecessarily, we don't necessarily agree upon this. This will eventually resolved by the hardware vendors, right?
Yes.
So, so my question here is that outside of this kind of like ongoing issues or past issue, can you give us more generic threat model where your research can find a context?
Yeah, so I think that I agree that like ideally we fix these like speculative attacks in hardware, and there's been lots of pushes. However, there is still significant amounts of like deployed hardware that cannot be fixed. People are continuing to find sort of new side channel and speculative exploits. So I think that like software techniques for ensuring protection against these are still like useful and important until these are sort of like, we figure out as a like overall community how to like permanently fix these speculative execution. But I think a key here in this work is exactly also in line with this, which is that like not everyone should care about like doing these speculative executions. We don't want to bake them into every protection, which is why we parameterize by different attackers, so that you're like, okay, I don't actually care. Like I'm on hardware that deals with Spectre appropriately. I think that like the people that might be exploiting this aren't going to be going to that level. And so we want to ensure that our security sort of takes into account the different possibilities for what you might be concerned about, and that you can sort of operate faster in cases where you do not care about these things.
Maybe I have a question myself related. So in your speculative model, you consider branch as a source of speculations. There are a lot of other works that try to expand that speculation mode to more. For example, when you have a return stack buffer, you might not just speculate on branches, but on any return of function or call of functions. Could you extend reasoning about robust constant time in those kind of scenario as well?
Yes. And so we specifically model speculation at like a higher, so like I showed the example with branches, but it's really just the speculative model is that a speculator can just guess there's like a microarchitectural state abstractly, and then the speculation oracle can guess the outcome of any expression and start sort of running as if that expression had that outcome before checking. So that can be things like what the return of a read is, what a memory address is, branches, the target of a call, and we talk about all these in the paper. So yes, it's a very broad speculation model.
Yes, so when you motivate your work, you also mentioned there might be other threads running. So is there some idea related to concurrency that you are considering?
Yeah, so I didn't talk about this in the talk, but in the paper. And so there, when you're worried about sort of a concurrent thread, a number of cryptographic algorithms will sort of do the intermediate work within sort of an output buffer. So you might use the ciphertext output buffer to do the intermediate rounds as well. So you don't have to reallocate space. And when you're operating in a concurrent threat model, you have to, if that is in unprotected memory, then that is, an attacker can observe the intermediate values there. So what we have to do there is actually allocate all of those, a copy of all those buffers internally and copy in and copy back out to ensure protections.
So what about operating system level concurrency? I mean, do you have to build a secure enclave, try to isolate?
So here, the memory protection we use is through Intel's memory protection keys, and so that protects from concurrent. So that is a thread local memory protection, so the access is only available in the current thread. So that handles that.
Any other question? No? Well, thanks to the speaker. We are actually running ahead of schedule. Yes, maybe we should sync up with the schedule, not go ahead of time.
Hello? Okay, great.
Maybe we have a problem, and then it's a spot. Oh, no, we don't have a problem.
Okay. And where's the show?
We'll run 1 minute ahead of time, so let's wait 1 more minute. Okay, so the next talk is by Owen Connolly. Owen is an undergrad, so he's looking for a PhD. He's going to apply for PhD in the upcoming cycle. And we will hear about not defining constant time, but proving constant time in the context of a verification framework in ROC. Thank you.
Hello, thank you for the introduction. Yeah, so I'm going to be talking about mechanical verification that compilers preserve cryptographic constant time. So I'll begin with a quick review of what I mean by constant time. So we say that a program accumulates a leakage trace as it runs, consisting of branches taken by the program along with addresses of reads and writes to memory. So for example, this guy on the left here, we say that the leakage trace of this consists of a store at address A, followed by a load at address B. And the thing to note here is that the addresses go in the leakage trace, but the values loaded do not. And this guy on the right, well, we just leak a 1 or a 0 corresponding to the program leaks a 1 or a 0 corresponding to the direction of the branch when it runs. All right, and then we say that a program is constant time if its leakage trace is independent of any secret values held by the program. And the point is that if a program is constant time, then an adversary cannot learn any of the program's secrets by reading the leakage trace. So the project that I'm going to describe here, we wrote a proof in Rock that a compiler for a C-like language is constant time preserving, where by constant time preserving I just mean give it a constant time program as input, you get a constant time program as output. And the point is that we can use this compiler theorem to compose it with theorems saying that source programs are constant time to obtain final theorems saying that individual RISC-V machine code programs are constant time. So past work has shown how to prove that compilers preserve constant time, including this work with Jasmine and CompCert that I have on the slide here. And some very recent work has actually shown how to prove that compilers preserve a speculative notion of constant time. In contrast, we do not worry about speculation. So what do we do then that is new? So all the past work just works with compilers where the source and target languages are deterministic. And this is because it's not so clear initially how to even define a reasonable notion of constant time for non-deterministic programs. So our work gives the first notion of constant time for a language with compiler-resolved non-determinism, where what I mean by compiler resolved is that we have some non-deterministic construct that is present on the source level of our compiler, but it disappears on the target level. Like our example that we'll talk about here is memory allocation non-determinism. You have things like non-deterministic stack allocation on the source level, but this does not appear with machine code. And so to make it feasible for us to write constant time proofs about non-deterministic compilers, we find it very convenient to state constant time in a simplified, unconventional way using no hyperproperties and a non-traditional style semantics that I'll talk about later. So pictorial summary of the project here. So our source language, Bedrock 2, is a subset of C with simplified memory semantics. We just say that pointers are machine words, and memory is a map from machine words to bytes, which is nice. And Bedrock 2 has all the important things that you see in C, like loops and functions. And interestingly, for our purposes, these non-deterministic constructs of stack allocation and runtime input-output. So the idea here is that we can write a source proof in Rock that a source program is constant time, and then compose that with our compiler theorem to obtain a final theorem saying that the RISC-V machine code output by the compiler is constant time, where so that our trusted code then of our final theorem is only the formalization of RISC-V semantics and the leakage traces on the RISC-V level. All right, so I want to talk about specifications saying that compilers preserve constant time, but I'll start by just talking about specifications of functional correctness for compilers with non-deterministic languages, because it turns out that's interesting. And to do that, I'll start by talking about a nice way of writing down semantics for non-deterministic languages. So this has been called omnisemantics in past work. So the main difference between this and usual big step semantics is that instead of talking about programs running to final states, we talk about programs running to postconditions. So for a postcondition Q, we say that program P with initial state S runs to the postcondition Q if the program always terminates without crashing in a final state satisfying the postcondition. Or we can think of postconditions as sets of allowed final states, in which case we just say it should be an element of that set. So this is a variant of weakest preconditions semantics, which hopefully you've heard of. So the main difference between this and usual approaches to weakest precondition semantics is that we define this down arrow, or PS running to Q judgment inductively by rules analogous to traditional big step semantics. And this is very nice because it allows us to write nice inductive proofs by induction on this judgment, just like as you would write proofs by induction on a usual big step judgment. And so why am I talking about omnisemantics? Well, the reason we care about it here is that it makes compilers proofs easy, as the slide says. So I'll begin by reviewing the case for non-deterministic languages. So with traditional big step semantics, we can write a forward spec when the source and languages are deterministic. And this just says that if you have a source execution, then you have a corresponding target execution. Going from source to target is why we call this forward. And with omnisemantics, the corresponding specification you write is that if the source program runs to a post condition, then the target program should run to a related post condition. So clearly this is just saying that the compiler preserves specifications, which is, so it, the compiler is functionally correct. Now with usual big subsemantics, with non-deterministic languages, compiler specifications get a bit more complicated because you need a backwards specification saying that any possible target program execution corresponds to some related source program execution. On the other hand, with omnisemantics, we can still have the same specification, and this is still meaningful. So we just say that if the source program admits a certain post condition, then so does the target program. And yeah, so clearly this means functional correctness. And so the reason I'm talking about this is that people, forward specifications are nice. They're easy to prove by induction on the source program judgment, deriving the target program judgment as you go. On the other hand, the backwards specifications are a bit not so straightforward to prove by induction on the hypothesis because, well, how do you do induction when you have the output of the compiler C here? You somewhat have to do something like invert the compiler C, and that is hard. So in summary, omnisemantics gives us an inductive definition of this program running to this post condition, which it allows easy forward compiler proofs. And this is particularly relevant for what I'm talking about now because the Bedrock 2 compiler proof that we extend in this work to say things about security properties uses omni-big step semantics, which is this down arrow judgment I have here. All right, so having finished reviewing relevant past work, I'll go on to new stuff that we did here. So beginning with a formalization of constant time for deterministic programs. So for a deterministic program P, we'll write spub to denote the public part of an initial state of the program, and I'll say what it means for P to be constant time. So the conventional way of stating this is that P is constant time if for any two initial states with the same public parts, these should lead to the same leakage trace of the program. So this is, should be intuitive, exactly straightforward formalization of our informal notion of constant time. But this is a hyperproperty, meaning that it relates two different executions, one starting with the state S1, one with the state S2. And hyperproperties are generally difficult to reason about, and in particular, particularly relevant for us here is that it's unclear how to state a hyperproperty with omnisemantics just because, oh, what do you say that the post condition should be? So we are interested in what I'll call a single copy definition, which is just a definition that only references one execution at once, rather than referencing two, as this definition up here does. So an alternative and equivalent way of formalizing constant time is to say that P is constant time if there exists a function f that takes its input, the public initial state, and gives you the leakage trace of the program. So these are obviously equivalent, but I emphasize the difference just because the second will be much more convenient for us because we can state it using omnisemantics with a single post condition of the program. So here's an example of writing a specification, a constant time specification of a program using omnisemantics. So here we have a swap program, takes 2 pointers, swaps the values of the pointers. We'll say that the pointers themselves are public inputs, whereas the values stored at the pointer, at the addresses, are private. And in that case, we have this specification here. So just to explain the syntax here, we say that this program is running to this set of possible final leakage traces. It's a singleton set consisting of the result of applying the function f to the public data here, which is the pointer A and the pointer B. And so the key point here is just that the final leakage trace here depends only on pointer A and pointer B, and in particular is independent of these values A and, or the values stored at the addresses. And we can straightforwardly prove specifications like this just by instantiating the function f appropriately that is claimed to exist. And by looking at swap, we can see, well, what is its leakage trace in terms of A pointer and B pointer? Well, we load at A pointer, load at B pointer, so on. Okay, now things get slightly more interesting when we have non-deterministic programs, and we would like to say what it means for them to be constant time. So our definition of constant time for deterministic programs requires that for every initial state there should be at most one corresponding leakage trace of the program, right? And so non-deterministic programs are not going to usually satisfy this definition because if you branch on any non-deterministic values at all, then you'll have multiple possible leakage traces per public initial state. Nonetheless, I claim there are non-deterministic programs that we might want to call constant time. So we have this toy login function here, takes an input, checks whether it is whether the password input is correct, and now the leakage trace of this login function is going to be non-deterministic because the leakage of this lookup password function depends on the input to it. And this is a runtime input that is we model as being non-deterministic. So certainly this is not going to meet our definition of deterministic constant time because the leakage trace is not going to depend on public initial state. So we have a straightforward definition of this, exactly what you'd think it'd say. We say that a program is constant time if the leakage trace of the program is a function of, well, now it gets to depend on not only public initial state, but also any public inputs during the execution. So again, just saying that leakage trace is a function of public values. And so we can straightforwardly write a specification of saying that the login function is constant time. So again, explaining the syntax here, this set here is a set of final possible tuples of input-output trace accumulated during the execution and leakage trace. So we're saying that the IO trace should consist of a username being input, a password attempt being input, and then something being output. And we're just saying that the leakage trace here should be the function f of the username that is input. In particular, it does not depend on the password attempt A or any secrets that might be stored in the memory M. Now, where things get quite interesting is where you have compiler resolved non-determinism, like our memory allocation non-determinism that we mentioned earlier. So consider this program, which is, it looks harmless, it does nothing. So this swaps two values in an allocated array. So I certainly want to call this constant time. It looks quite harmless from a security point of view. But it does not meet our deterministic definition of constant time because the address S is non-deterministic. According to our Bedrock 2 semantics, we say that memory allocation addresses are non-deterministic. So yeah, will not meet our deterministic definition of constant time. So how do we generalize our notion of constant time to say that programs like stack swap are constant time? So a bad idea would be to treat this in the way that I just showed you to how to treat runtime I/O. So we could keep a log of memory allocation events, and then we could write postconditions saying that, well, since surely the memory allocation addresses should be public data, the leakage trace could depend arbitrarily on memory allocation events kept in this memory log. So the problem with this is that for bigger programs, postconditions would get extremely complicated if maybe you have memory allocations interleaved with loops and function calls and whatnot. And a more fundamental issue is that it's unclear what a compiler theorem would say about the memory allocation log, precisely because it is compiler resolved non-determinism, right? So it's not preserved by the compiler. For the case of runtime I/O, well, we just say the compiler should preserve that, but here we can't do that. So in our paper, we explore two generalizations of constant time to say that stack swap is constant time. One is to say, well, compiler resolved non-determinism causes problems, so let's get rid of it, and determinize memory allocation in a somewhat unobtrusive way. And another approach is to formalize a notion of leakage trace modulo compiler resolved non-determinism, so that we can formally say that constant time programs are those for which leakage trace modulo compiler resolved non-determinism is a function of public values. And yeah, so in our paper, we show that both of these approaches work out nicely, and we use both of these approaches to prove that the Bedrock 2 compiler is constant time preserving. We also prove that these two notions of constant time are equivalent in a very strong sense, but we note that there are some interesting differences between the compiler theorems you would prove in these two approaches. And yeah. And that is all I have to say. So I'll take questions now if there are any.
Thank you. Any question?
I have a question about the constant time semantics. So there are many cryptographic algorithms which are not strictly secret independent. They leak a very small amount of information about your secret, and that's not considered a vulnerability. One example is rejection sampling. You take a secret and a counter, and then you produce some random seed deterministically based on your counter and the secret. And then you do some operation with the seed and see if it succeeds. And if it fails, you take another seed and try again. That's rejection sampling. And then your execution time would leak the information that you attempted that many times before you succeeded.
I see.
And that's a secret dependent. But that's usually not considered to be a vulnerability. So in PL terms, this means in the middle of these algorithms, you often have to say, we can declassify some amount of your secret state into public state. So do you think it's easy or challenging with your new constant time semantics to specify, say, in the middle of algorithm, it's okay to declassify part of your secret state and make it public so you can leak that information safely?
Yeah, so I'm almost certain that I understand what you're saying. And so you're saying that is it okay to leak some function of like thing that initial state that you would usually consider private,
yeah.
Right? So yeah, that's easy to express using this. All you say is that, say that the final leakage trace only depends on this function of the private data that it doesn't reveal very much.
I see, thank you.
I have maybe a question myself. So you define a new definition for constant time, and at the same time, it seems like it's related or close to the definition that people use. It's just that it's more convenient for omnisemantics. In the omnisemantics papers, there is equivalence between omnisemantics and other traditional kind of semantics. Have you thought about proving that your notion of constant time correspond to a hyperproperty kind of constant time on the other semantics?
No, I've not bothered, but it seems like it would be easy to prove.
Okay.
Yeah.
Hey, Rohan from Stanford. I was wondering if you could just explain a little bit more about the difference between the bad idea and the option number 2, because kind of reading them, I don't think I was able to kind of discern the subtlety of why one of them is a good idea and one of them is a bad idea.
Yeah, so I guess this option number 2 here, it certainly can be viewed as a variation on the thing that I've called a bad idea. But yeah, I guess it turns out to be somewhat subtle how you formalize this notion. And also the difference I had in mind between what I have here and the bad idea is that here we are doing it in a systematic way. Whereas with our approach with the runtime I/O was to just kind of write ad hoc specifications one by one. But it's important to do it in some systematic way and have a general definition of this leakage trace modulo compiler resolved non-determinism so that you can write an appropriate compiler theorem about it, saying that this is preserved when you push it through the compiler.
Okay, thanks.
Yeah.
Maybe one last question. So it seems at some levels that your strategy is not really specific about constant time. It's about leakage of any trace, or preservation of any trace, because you don't really have a notion of time on the source, no time on the target. They're all about a trace of events. Have you thought about generalizing it for other kind of hyperproperties, not about time, but about other kind of security properties or something?
I have not thought about that much, no, but I definitely agree with you that there seems to be very little or nothing about this approach that's specific to the notion of time, and it would be very interesting to explore generalization to other things.
Okay, thanks. Thanks. Oh, no, there's one more question. Yay.
Hi, I'll ask one question. So, not being super familiar with all this constant time stuff, I wonder how that definition differs from non-interference?
Yeah, so I think it's very similar. The difference being that I think with constant time we have this extra data of the leakage trace, and you're saying that that's independent of secrets, whereas generally with formalization of non-interference that I've seen, you just talk about, say, private parts of memory or some state that's already in the computer, and you just say, well, this final private part of the memory should not depend on the yeah. You say what it's. Or did that answer your question?
Not quite, to be honest, because you're like two initial states. Is the state not memory?
Oh, yeah, so absolutely. So here with constant time, we're saying that the final thing that the leakage trace does not depend on private values, whereas traditionally with non-interference, you'd be saying, oh, the private memory does not depend on, sorry, the public memory does not depend on private values.
But I'd also like to suggest that you can see this as a special case of non-interference when you work with an instrumented semantics that maintains this leakage trace and then otherwise treats it as any other state that you might see in old school non-interference.
Okay, let's thank our speaker again. So everything is right. We are slightly late again. So our last speaker will be about circuit optimization. Raghav Malik is, I believe I know that he's looking for a postdoc. Is it correct? Yes. And will tell us a bit about synthesis, or at least optimizing some specific kind of circuit using some new tricks.
All right, yes, okay, sounds like I'm audible. Great, all right. Hi, I'm Raghav. I'm currently a PhD student at Purdue. And today I want to talk to you about this technique called arithmetic lookup tables, and in particular, how we can use these to optimize circuits in the context of homomorphic encryption. So this is work that I did with my collaborator Vedant, and my advisor Milind. Okay, so if I'm going to tell you about homomorphic encryption circuits, I should maybe start by giving you some background on what fully homomorphic encryption is. So fully homomorphic encryption, or FHE, essentially refers to any encryption scheme that allows us to evaluate functions directly over ciphertexts without having to decrypt these first. So the usual sort of setup for this is we've got two parties, we'll call them Alice and Bob, and maybe Alice has a couple of inputs, x and y, and she wants to compute some function f over x and y. So she wants to get back like some computation of f of x, y. Different homomorphic schemes have different ways of thinking about what we really mean by function, but for our purposes, for now, we'll think of functions as being represented by some kind of circuit that we want to evaluate. And then by encrypted data, I mean like ciphertexts. Okay, so the way that this protocol proceeds is Alice starts by encrypting her inputs using some homomorphic encryption scheme. She can send the ciphertext over to Bob, who can then use the homomorphic capabilities of the scheme to compute some function f of x, y. In particular, Bob gets back an encryption of f of x, y, and then he can send this encryption back to Alice, who can then decrypt it with her private key and do whatever she wants with the result. Now this sort of setup is very useful because Bob never actually gets to see the values of x and y, right? So Bob knows that he's computing some function f, he knows that it takes two inputs, but he doesn't know the actual values of x and y. And so in particular, this is very valuable for cases when, like, let's say, companies want to perform computations on like private user data. So for example, like Microsoft uses this in Microsoft Edge, password monitor. They sort of use this to like detect when your password has been leaked without sending your password over the wire in plain text to these like databases of leaked passwords. Okay, so homomorphic encryption is kind of a useful thing that we might care about. But the big problem here is that this actual encrypted computation is incredibly slow, right? So in particular, computing over ciphertexts can be like several orders of magnitude slower than just doing the same thing over plain texts. And so really what we want to do in this paper is ask the question, can we make this faster, right? Can we actually help Bob by making his part of the protocol a little bit more efficient, help him like compute this function more efficiently? So the particular contributions that we make, first of all, we developed this notion of an arithmetic lookup table, and sort of show how we can think of this as like a new programming abstraction for certain kinds of homomorphic encryption schemes. And then we show how you can actually build a compiler that knows how to use this abstraction to generate smaller and faster FHE circuits. So if I'm going to tell you about our new abstraction, let's start by talking about the old abstraction. As I mentioned before, there's a lot of different FHE schemes out there. The particular one that we're going to use in this talk is called CGGI. The letters here stand for like the names of the people who came up with the scheme, but that's great. So the traditional CGGI programming model sort of assumes that our ciphertexts are encryptions of bits. So this is like encryptions of ones and zeros. And the sort of workhorse of computation here in the scheme is the ability to evaluate arbitrary logic gates over these bits. So with these capabilities, maybe it's kind of clear how we can proceed. We take whatever function we want to compute. We use standard like Booleanization techniques to turn this into one big Boolean circuit. And then we just evaluate the circuit gate by gate over our inputs. Now, optimizing this circuit or like making this run faster, since the only thing we can do is like evaluate one gate at a time, optimizing the circuit really just means minimizing the total number of gates. And it turns out this is essentially what existing like Boolean FHE pipelines do, right? So they start with some function, they compile it down into Boolean circuits, and then they optimize these circuits. Now, obviously, like, okay, so the thing we want to do is minimize circuit size, right? Build circuits with as few gates as possible. This is not a new problem. VLSI people have kind of been thinking about doing this sort of thing for decades. And so it's maybe a little bit surprising that like we have any valuable insight to offer here. Like what do we know that they don't, that they haven't figured out since the 1960s or whatever? And the answer is kind of, we know something about this space that they don't know, which is that this abstraction that I presented to you is kind of a lie, right? I mean, or this is an abstraction over what's actually going on under the hood, but it turns out that if we like peel back this layer and we look at what's actually happening in the scheme, we can do a lot better. So now let me tell you about the real CGGI programming model. Instead of thinking of our ciphertexts as encrypting bits, we really want to think of these as encrypting small integers modulo like some small number n. So usually n is like 4 or 8, right? So your ciphertexts are like encryptions of integers modulo 4, let's say, or modulo 8. And now we don't have bits anymore, we have small ints. And so instead of thinking of the computation as being like evaluating a logic gate, we want to think of it as being this operation called programmable bootstrapping. So programmable bootstrapping gives us two sort of capabilities. The first is that we can arbitrarily add and subtract ciphertext as much as we want. And in particular, this means that we can compute whatever linear combinations we want over these ciphertexts. These combinations are linear over like z mod n, right? So it's still working modulo n. And the other thing that programmable bootstrapping lets us do, which is really the cool part, is indexing into a fixed size lookup table. So the size of this lookup table, or the number of rows, is determined by the modulus. So this is like a table with n rows. And what we can do is take a ciphertext and look up the element in the lookup table that corresponds to the value being encrypted by that ciphertext. And it turns out that with these two operations, we can sort of recover the abstractions that we had before. So in particular, now if I want to evaluate some kind of logic gate, I start by expressing it as a truth table. And then I take my inputs. I take this linear combination using powers of 2, so like 4x plus 2y plus z. And then I use that linear combination to index into my truth table. So zooming in on this a little bit, I've got a truth table for like this 3-way XOR. So let's say I start with the input 0, 1, 1. So x is 0, y and z are both 1. I can take my linear combination. So 4x plus 2y plus z is 0 plus 2 plus 1, which is 3. And that tells me to look in the third row of my lookup table for the output. Now, here we chose to use 4, 2, and 1 as the coefficients for our linear combination. And so we sort of implicitly made the decision to think of our lookup table as representing a truth table for a logic gate. But it turns out that we don't have to use these coefficients, right? I can take whatever linear combinations I want. I can add and subtract as much as I want. And so it turns out that if I let myself pick different coefficients, I get something that's strictly more expressive. So let me give you a little bit of intuition maybe on why this is more expressive before we dive into the details. So consider this example of a mean, consider this construction, I guess, right? So we've got 7 inputs here. All of my coefficients I'm going to set to 1. And so really what I'm doing is adding up 7 inputs, or 7 ciphertexts, and then using that sum to index into this lookup table. Now, if the lookup table has a bunch of zeros and then a 1 in the bottom row, it turns out that the thing that this computes is a 7-way AND gate, right? The only way for me to get the output of 1 is for all of my inputs to be 1. If anything is not 1, then I'm going to get something that's yeah. So this computes an AND gate. Okay, and so what we've done here is take 7 inputs, or a 7-input gate, and we've represented this with a single lookup table that only has 8 rows. So if you think back to like what our truth table abstraction would have required us to do, is with 8 rows, we would need multiple AND gates, right? With 8 rows, we can represent a sort of truth table that has 3 inputs, and so if I want to AND together 7 values, I need 3 different AND gates. Alternatively, I could try to think of this as one giant lookup table, so like 128 rows for 7 inputs. And you know, we could build a 128-row lookup table, but it turns out the encryption parameters you need for that are kind of ridiculous. So that's generally not something you want to do. In contrast, this arithmetic lookup table, which is what I'm calling like sort of having arbitrary coefficients here. If I allow for arbitrary coefficients, I can evaluate this entire function just with one very cheap gate. Now, it is also worth noting that normally, like using all 1s for your coefficients is really bad because it means that you can't distinguish between the input 1, 0, 0, 0, 0 and like 0, 0, 0, 0, 1, right? These are in general, two different inputs, but if all of my coefficients are 1, they end up mapping to the same row of the lookup table. But it turns out that in the case of AND, we actually don't care about this difference, right? AND is very highly symmetric. It doesn't care about what order its inputs show up in. And so in some sense, it has like these redundancies or these symmetries that we can sort of compress away and turn this like 128-row function into an 8-row function. So let me maybe elaborate on that point a little bit more by trying to build a lookup table for this other function. Now, I mean, drawing 128-row lookup tables is kind of a pain, and it takes up a lot of valuable slide space. So for now, we'll do this example in the context of a 3-input function that we want to represent with a 4-row lookup table, but just trust that the same sort of story holds for different values of 3 and 4. Okay, so we've got this function, x0 and x1 implies x2. Now remember, traditionally, with our truth table abstraction, we would need 8 rows, right? Three inputs, 4, 2, and 1 are our coefficients, so we need 8 rows. But just like before, we have this like symmetry, right? x0 and x1, the function doesn't really care about distinguishing these. And so in some sense, we're wasting a bunch of rows distinguishing between different like inputs that only differ in what x0 and x1 are, even though f doesn't care. So for example, like 0, 1, 0 and 1, 0, 0, these are 2 inputs that the only difference is sort of swapping these first 2 inputs, but we're sort of, our coefficients are like, you know, wasting a bunch of time trying to, or like a bunch of effort trying to put these into different rows when it doesn't matter. And so really what we want is to find coefficients that map indistinguishable inputs into the same row of our output lookup table. So for an example that doesn't work, let me explain the visual abstraction here a little bit. Normally we've had like one output going corresponding to every row. In this case, we have multiple outputs going to a single row, and so each box sort of has, or sorry, multiple inputs going to the same row. So each box sort of holds like the set of all inputs that map to that row of the lookup table. So here, if I set all of my coefficients to 1, it turns out it doesn't actually work. Because, for example, this third row, like 0, 1, 1 and 1, 1, 0 will both end up, like these are 2 inputs that'll both end up in the same row, but they're supposed to correspond to different outputs. And so there's not like a nice answer of what output I should actually put in this row of the lookup table. But if I pick a different set of coefficients, 1, 1, and negative 1, it turns out that everything kind of separates cleanly, and now every row either has all greens or all reds. So every row has a well-defined output. All right, so clearly the coefficients matter. The next question is maybe like, given some function, how do we actually determine whether there is a set of coefficients or like what these coefficients look like? And the answer is like, in some sense, kind of boring. There's a lot of formalisms for this in the paper, but briefly, we start by framing this entire thing as an ILP problem, and then we ask an ILP solver to synthesize these coefficients. And so in particular, the ILP solver can either come back and say, yes, here's some coefficients I found, in which case we know how to build this arithmetic lookup table for the function, or it comes back and says, I couldn't find any coefficients, in which case we know that like this function is not expressible. Maybe it's not symmetric enough, maybe we need more rows or whatever. So now that we know how to express functions, how do we actually use these to build circuits? Well, we start with an ordinary Boolean circuit, right? So you can start with whatever program you want. You can use whatever Booleanization techniques you want to turn this into a Boolean circuit. And it's worth noting at this point, we are free to apply like the full spectrum of like all the work the VLSI people have done to optimize our Boolean circuit as much as we want. Of course, these optimizations will stay in the realm of this like Boolean gate abstraction, but we can apply whatever optimizations we want. And now we notice that we've got like 2 adjacent gates. And if we were to merge these, the total size of the circuit would get smaller, right? I went from 3 gates here to only 2 gates, even though this new gate is now computing a more complicated function. And in particular, like there's a problem here, which is that like this merged gate now has 4 inputs, which a priori needs like 16 rows if we think of our things as being truth tables. And so this merge is really only legal if the solver is able to find coefficients to represent this merged function. So with that, our merging procedure is we start with some circuit, we pick a gate in the circuit, and then we check to see if this gate can be merged with every single consumer. Right? So we ask the ILP solver if each of these merges is possible. If they're all possible, we perform all of the merges at the same time, and we iterate, either until we run out of gates to try to merge, or just like for a fixed number of iterations. Now, obviously, that step right there involves a bunch of calls to an ILP solver, and so this can be like very expensive and take up a whole bunch of time, especially if like, let's say you've got 10 merges to try, and like the 9th one fails, and you've like wasted a bunch of time figuring out coefficients for the first 8. So the paper has a bunch of heuristics and stuff that we like optimizations that we layer on top of this to help us like guess what things are going to be easier to merge. All right, so with that, maybe I can talk about some results. So the one question that we sort of wanted to answer here is like how effective is this new abstraction at actually letting us represent circuits with fewer gates? In particular, how much can we like shrink circuits? How effective is this like shrinking procedure? So we took a bunch of common benchmarks, some like adds and multiplies, and some like MPC stuff like set intersection and private information retrieval. We compiled these down into Boolean circuits. We applied some standard circuit optimization techniques. And then on these optimized circuits, we applied this merging procedure from the previous slide. And we found that merging lets us sort of reduce the number of gates by up to like 50%. Obviously, small circuits is not the only thing you care about. You care about fast circuits. So we did actually go ahead and like execute these generated circuits against an FHE library, against OpenFHE. And we found that the actual speedups correlated very strongly with the reduction in the number of gates. Which is sort of what you expect, because even though each gate is now computing a more complicated function, the underlying mechanism that it's using in CGGI is sort of the same. And so we don't expect these merged gates to be any slower. All right, so even with all of these like ILP solver optimizations and stuff like that, obviously like this compilation procedure is still going to involve calls to an ILP solver, and so it's going to be kind of slow. And so there's a concern like how well does this actually scale up to bigger circuits? So we tried playing this trick where you take some big circuit, you find some kernel that's repeated a bunch of times. So the orange things here represent like sub-circuits that exist within this larger circuit that are maybe identical. And I can try like pulling out a single copy of this kernel, optimizing it with the merging procedure that I described earlier, and then just like plugging this optimized thing back in. And so now I'm able to optimize this entire circuit without actually having to visit every single gate. And maybe this lets me like build a nice efficient library or like scale up to bigger programs. So the obvious question here is like, how well does this work? So we took a matrix multiply. We tried kernelizing it in a couple of different ways. And briefly, what we found is that different ways of kernelizing still give us like very comparable speedups to what our original thing gave us. So maybe the takeaway is that like kernelization is pretty good, and this helps us like apply this technique to larger programs as well. So in conclusion, the CGGI scheme traditionally models FHE computation using this Boolean gate abstraction, but we found that by changing our abstraction, we're able to represent gates that couldn't be expressed before, right? Once you fix a lookup table size. And in particular, we showed how a compiler can use this new arithmetic lookup table abstraction to generate smaller and faster circuits. With that, maybe I can take questions.
Hi, great talk. I'm Ajay from MIT. I have a question. So you used a metric of the lookup table size as an optimization metric, but is there a strong correlation between lookup table size and performance? Because some coefficients might be easy to compute, like 4 to 1 is just a bunch of shifts and adds, or even just concatenation of bits. But if it's like 3, then you have to do a multiplication.
Yeah, that's a very good question. So regarding the lookup table size, the size of the lookup table is something that, maybe I should have explained this better earlier, but the size of the lookup table is something that you sort of determine when you set up the encryption. So you set it up to say, okay, I want my ciphertext to be zmod 8, and so now I'm restricted to 8-row lookup tables no matter what, and I can't go bigger. If I wanted to go bigger, I would have had to like change the entire encryption to encrypt zmod 128 or something. The other thing about like different coefficients being easier, this makes a ton of sense when your things are actually bits, and so you have access to these bit shift operators. But it turns out that even when we're doing 4-2-1, we're still doing like x plus x plus x plus x plus y plus z. And so we're not getting like any real benefit from these coefficients being powers of 2, because these are integers and not bits.
I wonder if you could explain more about the setting here such that you expect you have a computation graph with redundant instances of the same computation, like allow you to get some benefit out of the kernelization optimization. In normal software, we would hope the compiler got rid of that redundancy and already only ran that computation once. So what's different about this setting?
Yeah, so the redundancy is in sort of the shape of the computation, not the actual computation. So maybe if I explain this kernelized benchmark a little bit better. We have a matrix multiply. In every iteration of the like innermost loop of the matrix multiply, you're doing an addition and a multiplication, right? And so you can pull out this addition circuit and this multiplication circuit and optimize these and plug in the optimized circuits, or you can essentially unroll your entire loop, get one giant matrix multiply circuit and try to optimize that whole thing. So kernelization is sort of, I mean, you can think like every time you have a loop, right? You can try to optimize the loop body, or you can unroll the loop and try to optimize the whole thing. So that's morally what's going on here. I don't know if that answers your question.
Yeah, thanks.
Maybe I have a question as well. So in logic synthesis, there has been a lot of work on standard Boolean optimization. And what they typically do is they create databases of all the LUT4, or they want to implement them. So they avoid recomputing the same thing multiple times if they see the same pattern multiple times. And I was wondering, in your case, can you give us an hint on how many of those, if I look at LUT4, for example, how many of the LUT4 would be implementable with an arithmetic lookup table of some size which is smaller than the number of rows than LUT4? In a sense, how do you pick the R and how much compression you get, and what is the space of Boolean function to arithmetic lookup function reduction that you get?
Yeah, so I don't have actual numbers on this, but I can like give you some intuition. So first of all, regarding like how you pick the R, the number of rows is something that you sort of pick when you set up the encryption itself. So this is not in general like a configurable parameter. This is like the strength of encryption that I want in some sense. But so the standard set of parameters that people use in the literature gives you like 8-row lookup tables, for example. And it turns out that with 8 rows, obviously every 3 input function can be represented. Almost no 8 input functions can be represented. So you're sort of like living in this range between 4 and 7. It turns out most 5 and 6 input functions have enough symmetries that they can be compressed down. 7 inputs is tricky.
Okay. Any other question? No? So we thank the speaker again. And Raghav is looking for a postdoc, if anyone is. So I think it's the end of the session. Yep, it is. So we have a break now, 20 minutes, up to the next session.
Hey, do you have a USB-C to HDMI adapter? Or?
I'm not sure. I think not here. I can ask in the chat. USB-C to
HDMI, yeah.
Okay. Hello. So pardon the interruption. So some of you may have seen the PLDI schedule, but actually we are now having a short social event for student PLDI attendees. So could you please give me a little attention? So, well, in PLDI we get to meet a lot of students from all around the world, but unfortunately we don't really get to talk to each other. Well, some of us are just shy, so some of us just, well, actually don't know how to approach each other. So, well, that's why this year we have, as a social event here, I prepared a tiny event so that student attendees can get to know each other a little bit more better. So, okay, so, do we still not have data? Why no adapter? So.
I don't know if you can. Maybe can you try another device if you have another device or
no.
laptop or.
Yeah, I don't have my Mac, so I.
Do you have friends or use their laptop?
Huh?
Can you use their laptop? Because yeah, if you need that, I think you should ask in advance because no, I don't know.
Yeah, well, everyone was using this, so I don't have it. Okay, so. So first, to start, I would like to divide students into some groups. So, well, I really wish I had slides, but, well, okay, so the bottom line is you take the alphabet transliteration of your name. So, for example, my name is Seunghyun Nam, and, well, in my name and including first and last name, I have 13 characters. So mod 30 by 10, and then you get group 3. So, like this, can I get some volunteers from each group? So if you're naming alphabet, length of naming alphabet, mod 10 is from 0 to 9, please. I would really love to ask for cooperation. Could you? If you, so I would like to get some volunteers from each group. If I would really like to ask, please. Huh? Yeah, from each group. So your group is the length of your name in alphabet, mod 10. Huh? Actually, so I have this group sign. So, well, actually, I would like each one of you from group to, well, actually take this paper. So, if you would. Oh, so which group are you in?
I am 0.
You're 0. Great.
Oh, like taking the sum. Oh,
yeah, then you would get to gather some other group 0 students.
Oh, okay. 5.
You're group 5. Great.
Okay, so you're taking like a sum. Okay.
Yeah, I counted all the letters there. It's like for you about 13.
Okay. You are group 5. Sorry, I really wish I had that slide. Group 2. Oops, here you go. And you are group 7.
Yes.
Have you prepared, or is there a way to obtain pens?
Oh, yeah, I have some pen. Oh, just a second. Oh, sorry, just a second. If you need some pen, then you can take some of these. Yeah, if you need a pen, you can take any of these. You're on group 4? Okay. Group 3. Group. Group. Wait. Group 4. Group 3. There you go. Group 1. Thank you. Anybody from group 8? So we still have this group 8 sign left. Yeah, so it's mod 10 8 is 8, so it may be 8, 18, or 28. I'm not sure if this exists. Oh. Also, we are missing group 6 too. So anybody from group 6, group 8, and also we are missing group 9. So anybody from group 9? Oh, there you go.
He's the director of my I don't know.
So anybody from group 6 or group 8? Oh yeah. Well, I guess some studios have actually gone out. Oh, man, this is awkward. Okay, so while I'm waiting for volunteers from group 6 and group 8, let me explain this quick reference manual for student attendee. So, well, what you see right here is, well, you get to fill, each one of you get to fill the paper, and well, this giant blank is actually you get to draw your own micro poster of your research or some research that you are interested in. And after that, then you get to share your research interest or your recent research with your group member. So is it clear? So to the drawing board, I guess. Okay, so once each of you have this quick reference manual, then you get to fill in this manual, and in this giant blank, you get to draw a micro poster of your research or your recent research interest. If you need pen, I have some extra over here. Here you go. And after you have filled your QRM, then you get to share it with your group member. Okay. Oh, sorry.
So there's name and name?
Yeah, well, I expected more Korean students around here, but
I didn't know what this means.
So Hangul is actually Korean alphabet. So so your name is Popescu Lucian?
Yep.
Then it would be
Start the session because it's exactly 4 o'clock. So my name is Alex Patanin. I'm going to be chairing this session on big, red, clean algebras with tests, I suppose. I didn't come up with a name, but we have 4 nice speakers lined up for us today. So Mark Moller is the first speaker, as you can see, from Cornell. He'll be talking about, well, I'm sure you will repeat what you're talking about in a minute, so I'll just let you go ahead. Thank you.
Oh, there we go. Hello, everyone. I'm Mark. I'm a PhD student at Cornell, and I'm also an intern at Galois this summer. So if you're interested in Galois, please come talk to me. And I'm excited to tell you today about active learning of symbolic netcat automata. So in the networking domain, we can think of the routing policy installed at the various switches as just a program. And that program is distributed in some sense, but in another sense, it just takes packets as input, it filters or perhaps updates fields in the packet, and then produces output packets. But we can just think of that as output of the program. Okay, and as a program, of course, it's very easy to create bugs that are routing behaviors we don't want. And so we might have some verification questions that we want to ask about the programs installed, the routing policies installed on our switches. In particular, an easy one is, are all the hosts reachable from every other host, for example? Okay, and a way to do this is you write down a precise specification for the thing you want to check, and then you do some verification query to say, does the policy in place implement this completely? And netcat is a DSL for specifying routing policies that has the main benefit that everything can be compiled down to an automaton, and then doing these verification queries amounts to doing automata equivalence, and that answers this question for you. I will say that because it was developed at Cornell about 10 years ago, it's also a big red cat. That is the joke there. Okay, and what if we have, there's a main problem with doing this analysis sometimes, and that is what if in our network we have some unknowns. In particular, we might not know the precise implementation of all of the switches we run. Maybe we got it from a hardware vendor and the internals of how the switch isn't completely clear to us, or even we have a configuration but we're not sure of the semantics. I might want to investigate that to be sure of the behavior of my network. Or in another situation, I might not yet have a precise spec, but I still want to build a model of my own network for the purpose of understanding its behavior. Okay, so to be clear about what I mean, I'm interested in this question, can we build a model of the network by observing traces through it? So in particular, we're not going to be allowed to look at the switch configurations, or the program text, if you will. But we can send packets from the hosts and observe the resulting trace through there. I'm assuming that we have some network telemetry, such as traceroute or something along those lines, to observe the behaviors actually being exhibited by my network. Okay, and this sounds like there's a long line of work on active learning of closed box systems, where you're really thinking of a single system most of the time. But the way this works is that a learner sort of hypothesizes that the closed box system is modeled by a DFA, and the L-star algorithm, famously due to Englund in the 80s, basically gives you a way to systematically query strings, like is this a valid string by the DFA driving the system? And the thing will say yes or no by observing its output. And then you update some data structure and make progress on determining what the DFA is this way. So the updates to your data structure will give you more strings to query. And you query these strings and observe their behavior, and you iterate on this and update your behavior. And eventually, it gives you a way to conjecture a DFA. And when you do that, the formal model that Englund devised said that the teacher will give you a counterexample. And so, okay, in this case, some string that your hypothesis misclassifies that is the wrong behavior of the system. And then you update your data structure and keep iterating. And eventually you terminate when you get the exactly correct DFA. Okay, great. In fact, LStar has already had some success in networking, but it's really been focused on end hosts. So these were projects where they were able to derive the DFA at the core of an end host implementation of TCP, SSH, QUIC, by basically querying traces that corresponded to packets and then deducing how the end host implementation of these protocols worked using LStar. So because of this success, we had the hypothesis that this technique would work for entire network behaviors, that is, across multiple switches. Okay, so my solution here is to adapt LStar to netcat automata. And the picture works exactly how you think, that instead of a DFA in there, there's a network under test. And now the strings that before were sort of a formal alphabet correspond to a series of packets that represent a trace through the network. And by proposing one, I really mean seeing if this is a behavior of the network by sending a packet and seeing if I observe this. Okay, and then I get yes or no answers to that. And at least for our formal framework, you can query, this is a cartoon of a netcat automaton, and again, you get the no, yes if you're correct and you terminate, or no in a counterexample. Okay, and we can talk about the realism of the conjecture in a bit. Okay, so one key challenge I want to point out about this process, that is of trying to do LStar in this richer domain, is that in DFAs, transition symbols, well, you have the transitions labeled by concrete members of the alphabet. And if you were to just naively translate this over to netcat, the packet space is enormous, and already the machines you build are going to be enormous for the same reason. Okay, so I have an insight about this, which is that you can try to represent the packets symbolically. And I presented a paper of ours with Jules, who you'll see in a moment, and others last year at PLDI, where we do indeed represent transitions symbolically, and this works great. But the trick here is really to thread it through the learning process and come up with conjectures under this scheme, and that was one of the big challenges of this work. Okay, a second key challenge here, and I think in some ways this is the bigger one, that netcat is great about representing update behavior for packets. And again, to explain what I mean by that, I want to use the example of DFA, just like we did in the last slide. And that is, if we have a DFA like this, and a short string AB, well, I can run this string, and you know how to do this. I read the A, and I get to Q1. And the point is at this point that when I look at the symbol that's next, the B, it doesn't matter how I got there. I could have gotten there by a series of A's or even a B. But independent of the first move, the B is how I get to Q2. But that property isn't how netcat works. Netcat is about updating the previous symbol. So to give you an example, and here's a little netcat program that's sort of motivated by this real-life drawing. It's the same one we saw before. If I'm at, what this transition says is that if I'm at switch A, and if the destination is host 3, then this particular forwarding policy says that I should send that packet out on port 2 to make progress towards 3. And moreover, the point that I was trying to make was that if the last symbol we saw was the first packet, so it's just a triple in this case, that I'm at switch A and my destination is 3, and I was on port 1, this transition is denoting the update of the port, the physical location of the packet on the device, but this dependency is on that previous packet. And so it's not the same situation as the DFA. And of course, LStar relies heavily on this independence of the successive symbols, whereas in netcat, we really do need to model this update behavior. And that's one of the main challenges of designing the learning algorithm. I have an animation out of order there. Okay, so the naive answer to this is just to build the DFAs. And what I mean by that is that the update behavior of the packets really, the previous packet could just be modeled by state, right? I'm saying that there's this complicated relationship between successive packets, but I can just roll all of that into the state space and build essentially what's a large DFA and run L star. The problem, of course, is that the the problem, of course, is the enormous state space blowup that results from doing this technique. Okay, so if I just do this naive solution, there is a way that this all works, but it creates a large intractable machine. A better answer is to build a fragment of this naive machine based on only the observations that I've seen so far. So as the learning process develops, there's only a few packets that I'm seeing, and so I build basically a fragment of this machine that doesn't make sense. It's a partial, it's partially defined, whereas L-star would have me exhaustively explore the space. Here I just build the fragment. And then I generalize it to a full symbolic automaton by essentially looking at the evidence that I have and building those symbolic transitions based on the positive and negative example traces. Okay, so then I have this full symbolic automaton. And the point was, and this is where the animation was out of order, I apologize for that, that this brings us back to my original goal, which is now that I have a complete symbolic automaton, I can compare it against specifications using our verification queries from the beginning. Okay, so we built all of this in an OCaml implementation. The artifact is findable through the paper link. And I benchmarked it on the topologies from the Internet Topology Zoo. So there's a set of 260 or so topologies, and they come from primarily ISP backbone networks. And what we did is we laid a simple forwarding policy on top of these switches and tested reachability queries we ran the learner on these forwarding policies, and we were able to learn the policies in place for the entire network for between half and 2/3 of them. But this is the first tool that we know of that does this, and so we're pretty excited by these results. That's within a 30-minute timeout, and this gives you an idea of the membership and equivalence queries as things scale. Note these are log-log axes. Okay, there's a lot more in the paper. In particular, the naive solution that I described that I was saying was essentially DFAs, it's a little bit more subtle than that, and I'm calling it a naive learner, but actually it took us a fair amount of effort to get there. And so the fun theorem we prove is that we do learn a uniquely minimal solution, even though it's practically large. It's unique for the representation and smallest, and we do that through Myhill-Néraud theorem. That's along the lines of what Dexter Kosin proved for automaton guarded strings more generally. Okay, and then the way the algorithm works, there's this subordinated symbolic transition learner for the transitions. That's what I was saying. Sort of generalizes the few packets we've seen to a complete symbolic transition. But this is actually useful in its own right when you only care about the input packets and the output packets they produce. If you don't care about the full trace behavior of the network, then our subordinate learner is interesting and able to solve this problem for you already. Okay, and then finally we prove correctness of the symbolic automaton learner, which is to say we prove termination because we conclude by reaching a yes answer to the conjectures. That's correctness. Okay, and then a couple remarks on future work that I'm interested in. The symbolic version of the automata do not have unique state minimal forms, and so there's an interesting question of, for a given application, which one would be the most useful one to learn. That is to say, you could have different symbolic transitions at various places in the automaton, and for your application, it may matter what those look like, and you have some choices as the algorithm goes that we more or less make arbitrarily, but that could have some interesting answers. And then finally, I'm interested in the question of what if we don't have full network telemetry? What if some packets are not observable to us or have missing information? Could we still make progress, and what guarantees could we give in a setting like that? Okay, and at that, I will take questions.
So maybe best if you come up to the microphone so that we can record it for the posterity. Thank you.
Hi, Chris Kazanghino, Jane Street. I wondered in your empirical evaluation whether there were particular characteristics of networks that made them hard to learn, or whether there was just scale purely.
I see, that's a good question. I definitely saw a relationship to scale, and so I will say that was the biggest factor that I noticed. I would have to do some more investigation. It's an interesting question. Thanks. As to what would make networks harder to learn.
Hi, Mark. Jules Jacobs from Cornell. Could you show the graph with timing again?
I can.
So I just wondered, how long would it take to solve the largest topology zoo?
That's a good question.
Because you have a very nice line here.
Yeah, you're saying I should, if I just draw the line, where would the crossover be? Yeah. I don't know. I'll have to get back to you on that. That's a good question.
Cool. Anyone else? I have a silly question. So if I'm working for a switch company, I use P4 and I have my very custom for whatever company I'm working for ways to know the tables and everything like that. And I kind of look at this, high level stuff, and I want to sort of learn as a developer within a network switch company, how can I verify what is happening with me with the custom router stuff, some P4 language which you can understand, but what would it take to bring it down to sort of practical explanation for me as a,
in terms of, I guess I missed the part that you...
How do you see it if you were to explain it to a network switch, I don't know, is it network switch engineer or someone who works on this? How can they use this? What would make it practical for them?
How I think of this work is a way to guide your testing in a way to guide you towards having a complete understanding of your system, and that model that you build would tell you all of the behaviors of the thing you wrote down.
Despite some proprietary ways of looking up the switch tables or routes, because this is going to be dependent on the company?
I say despite that because ultimately the model we build will be based on the behaviors that actually you observe. And so in some sense it's ground truth regardless of the proprietary design of the switch itself.
Okay, that's fine. I think we are good on time now, so we can finish. Thank you very much. Thank you very much.
No. There we go.
Yep, all good.
Perfect time, 20 past. So now we have Jules Jacobs from Cornell. We will have another paper that's not from kernel later in the program, but don't worry. But I understand now big red cats after the first speaker, so thank you. So please carry on talking about the, still I guess, the similar issue as the previous talk.
Yep, that's right. Yeah, I'm going to talk about StackCat, which is similar to Netcat, is an extension of Netcat. And this is joint work with Nate and Jana, who are here, and with Tobias, Dexter, and Lily, who are not here, I think. And if you want to play along, you can use this URL. So what is StackCat about? Well, let me first tell you about the network model that we are talking about. So Mark already talked about that a bit. But here you see a network and a packet traveling in a network. And what is a packet? Well, a packet is just a fixed collection of header fields. Here on the bottom you see that it has a source address, it has a TTL, some other fields. And we also consider the current location of the switch to be part of the packet, but it's not a real field that's stored in actual bits of the packet, just for us to keep track of where the packet is in the network, and to uniformly treat the location with the actual data. So in this model, a switch looks at these header fields, modifies them in some way, and sends the packet out to a neighbor. And that's all a switch does. So a switch is a very simple finite state thing here. And then Netcat is a language to model these kind of networks using PL techniques. So what is the idea? The idea is to write a simple imperative program for the behavior of your network, where the local variables correspond to the header fields in the packet. So here you see you have an input packet here, and a simple program that transforms this packet, produces an output packet in its local variables. And this way, we can model many things that switches do. For example, a match rule in a switch can be modeled using an if statement. An action can be modeled using a variable update. Multi-hops can be modeled using loops. And then verification can use techniques for program verification. And in particular, since programs are very simple here, we can do automated verification because everything is decidable. And the key question, the key verification question that's answered here is whether two programs are equivalent. And many network verification questions can be reduced to that question about programs. Okay, so why are we doing things beyond Netcat? Well, the thing with Netcat is it can only model packets with a fixed number of fields. And each of these fields also must have a fixed number of bits. So that means that you cannot model variable length data. You cannot model packet parsing. You cannot model certain protocols that use arbitrary amounts of data in the packet, such as source routing, where the entire path that the packet is supposed to take is stored in the packet payload. It can also not handle tunneling, where a packet is encapsulated, because that also extends the size of the packet. So this paper is about addressing this limitation and going beyond this finite state model to an infinite state model. So that is what StackCat is. So the only thing we do is we model an extra field in the packet, the last field, which contains a payload which is variable size. And the key thing here is that this extra field is treated as a stack. So we can push new bits onto it or pop bits off from it. So as I said, we know from Netcat that we can reduce network verification questions to program equivalence. So what we want to build here is a model for this variable state packets where we still have decidable equivalence. So here's an animation of what these kind of networks look like. So everything is the same as before, but you see here the last field, the payload, is being modified and some bits are being pushed onto it or popped off. And those bits can, of course, be stored in header fields. It's just an arbitrary program, but it can only treat the payload as a stack. So here's what the actual language looks like. It's more or less like regular expressions. Here, the first line in the grammar is just the ordinary regular expression constructs, plus the two constructs for Netcat for assigning a packet field and testing a packet field. And then we have two additional constructs for pushing and popping onto the stack. And with these two operations, we can model this extra field, which lets us model all these extra protocols. So let's see what the stack operations do. Well, push is very familiar. It just takes an input stack, puts a new number in front. Pop is a little strange because you see pop here also has a constant argument. That's maybe unexpected. So pop here acts as a non-deterministic operation that either succeeds or fails. So if the stack's current top is the actual number, then it pops it off. Otherwise, it non-deterministically fails. So here you see in the bottom, if the top of the stack doesn't match, it fails, so the program behavior is the empty set. And if the stack was empty, it also fails. Okay, so we have this language with regular expressions, but actually this is just a core language in which many familiar constructs can be modeled. For example, an if then else statement can be modeled as a non-deterministic choice, where you either test that some field is, for example, 0, and then do p, or you test that some field is 1, and then do q. You can also encode while loops using clean algebra star, where you say, okay, while the field is 0, keep repeating this, and then at the end of the loop, field must be 1. Using these concepts, we can also model interaction between header fields and stack. For example, here push of a Boolean field f can be modeled as first testing if the field is 0, then pushing 0, or testing that the field is 1 and pushing 1. Similarly, pop can be modeled the same way. Since pop acts as a test, we can test if the top of the stack is 0, pop it off, put it in a field, and do the same with 1. Note that this can be expanded into n-ary length for fields that can store more values. So what is the semantics of all this? Well, the semantics is simply a familiar small step semantics, where the input state is an input packet with fields and a stack, and the semantics of the expression then steps this to a set of output packets, all with a stack. And then if the set of output packets is empty, the packet is dropped. If there's one packet in the output set, it's just a deterministic step. There can also be non-deterministic steps for modeling multicast, for example. And the denotational semantics of this is very nice and simple. So sequential composition in the language is just relational composition. Non-deterministic choice is just union of relations. Cleany star is just reflexive transitive closure of the relations. And then the basic operations, they have the usual semantics that you would think of. So what is the key verification question? That is the semantics of one expression equal to another? So in Netcat, it is somehow clear that this question is decidable because everything is finite state. So you can just enumerate the entire packet space and compare automata. And this is p-space complete because comparing NFAs is p-space complete. But for Stackhead, this is not very clear because we have this unbounded state space. And so it's not very clear that this question is even decidable. But it turns out that it is, and in this case, it becomes X-space complete. So in the rest of the talk, I want to give you some intuition for the difficulty of this question and then how this is solved. So here I list 3 basic Stackhead equivalences. So the top one says if you first push a value and then pop a value, this is equal to doing nothing, just the identity. So if you push a value and then try to pop off a different value, then this is a failing program. It's the same as just deterministically failing. And then the last equivalence is maybe a bit more interesting. So if you pop a value v and then push it back, this is almost the identity, but not quite, because if the input stack didn't start with v, it would fail. But if you add in the identity on the left, then it does become the identity. Okay, so here's maybe a more interesting equivalence. So here you see on the left, you can push any number of a's, and then pop any number of a's. Turns out this is the same as either pushing a number of a's and then popping a number of a's. So why is this? Because if you push some number of a's and then pop some number of a's, the net effect is always to either having pushed some or popped some, depending on whether you did more pushes or more pops. So here you can do a puzzle and see which ones are equivalent here. But I hope this works. But we have a tool for this. So now I do need to move my mouse on this screen. So here you see 2 expressions. On the left, we say we pop any number of 1s and then push a 1. On the right, we push a 1 and then push any number of 1s and then pop a 1. Turns out that these expressions are not equivalent, and our tool can tell you why. So here it gives a counterexample both ways. for a transformation that can be done by the left but not the right, and vice versa. And I think I can type here. So we could also, for example, put a star here, and now it does become greater than the other side. And if we put another star on the right, you see that these programs are equivalent. Popping some number once and then pushing one is the same as pushing once and then popping once. Okay. All right, so how does this tool work? So it works in 3 steps, basically. The first step is, the 0th step is to take your program and convert it to an NFA. So this is, you're all familiar with this. But because of the header fields, it is a little bit more involved. I will go into that in the next slide. And then we do 3 normalization steps on the automaton. And at the end of the day, it will be true that if 2 programs were semantically equivalent in the denotational semantics, then the automaton will be language equivalent. So they will accept the same words. But that's only true in after step 3. So let me go into step 0. How does that work? So in step 0, we use small step semantics, where we only take into account operations on the headers, and we keep the operations on the stack as labels on the transitions. So that means that the state in this small step semantics only stores 2 things. 1, the state of the header fields, 2, the current expression that we are executing. And it turns out that if you step this way, you only reach finitely many states. So you get a finite automaton generated by the operational semantics. And on the edges of the automaton are the push and pop operations that you do. So now we have an NFA, maybe a large NFA, where the labels on the edges are push or pop, or epsilon. So then the next step that we do is we try to cancel out matching push and pop operations. So if somewhere in the automaton we see push v, and then the next step will be pop v, we can insert an epsilon edge to shortcut this. So instead of actually doing the push and the pop, we could instead just directly go to the resulting state. And formally to do this, we have the rule above where we insist that there is an epsilon edge between the push and the pop. And separately, we maintain that we maintain the reflexive transitive closure of the epsilon edges. So this way, by exhaustively applying these rules, it stabilizes because we're only adding epsilon edges to the automaton. So eventually, nothing more gets added, and then we have step 1. Then after step 1, we will intersect the automaton with the language pop star, push star. So that means that we throw away all the strings in the automaton that have a push coming before a pop. We only keep the ones that have pops before pushes. So intuitively, what this does is it removes inconsistent push-pop operations, and it also actually removes consistent push-pop operations. And the reason that's okay is because we did it step 1, where we inserted a shortcut edge for them. So now we have an automaton that is even more canonicalized. But it turns out it's not quite enough. It's still not true that 2 automata are language equivalent if the expressions were semantically equivalent. So for that, we need step 3, which is a bit more complicated. And basically, the idea here is to start running the automaton from the inside out. So we start at a position in the automaton where on the left we have a pop operation, and on the right we have a push operation. Note that after the previous step, all strings are of that form. They have some middle part where we go from pops to pushes. So we look at that point, and we execute the automaton from the middle out in synchronized pair steps. So now instead of having 1 operation on the label, we have 2 operations, a pop on the left and a push on the right. And if we are at the end on the left, we have a special done marker, the same on the right. So now that we have the automaton in this shape, we can add self loops to the start state, intuitively representing which part of the stack was not touched by the program. So initially, the stack would have some number of values on it. And these self loops represent those parts that are not touched by the program. After we have done this step, it turns out that indeed, 2 expressions are language equivalent, even only if they are semantically equivalent. So a common question that comes up is, isn't it just visibly pushdown languages? It turns out No, this is quite different, because in visibly push-down languages you have restricted stack behavior, namely visibly push-down behavior. So in Staccat, there is no restriction on the stack behavior. Any push or pop is allowed at any point. On the other hand, in visibly push-down language, you have a separate input tape, but in Staccat there's no input tape, there's only the stack. So the input in Staccat is sort of what is stored on the stack before you start running your program. So that is the initial packet that comes in. So that's the initial packet is not on a separate tape, but it's on the same stack. In fact, if you were to add an extra input tape to Staccat, it would make the whole equivalence undecidable. So we can't do that. Okay, so what about the difficulty of solving this problem? It turns out that if you don't have any header fields, this problem is equivalence problem is p-space complete. If you have header fields, it becomes x-space complete. And one of our previous reviewers gave an idea for a very elegant reduction here from regexes with squaring. So if you look at the actual performance of our tool, there are sort of two regimes. One regime is without header fields. Those are the lines at the bottom, and then it goes reasonably fast. If you do add header fields, it becomes very slow. So one future direction here is to treat the header field symbolically, like was done in previous work, and try to speed this up. But how to do it is not super clear. So then another thing that's in the paper is a complete axiomatization. So on the left here we have the three axioms that we saw in the beginning. It turns out that we were not able to prove that these axioms are complete, meaning that if two expressions are equivalent, then you can prove that using these axioms. So instead we replaced the third axiom with an ugly axiom, which you can find in the paper, and now we are able to prove it. So challenge to you is to prove it for the left set of axioms. So what I talked about is a new model for unbounded packet processing with decidable equivalence. And to make this actually work for real-world networks, we would need a more familiar surface syntax, a symbolic algorithm to treat the header space symbolically. And ideally, we have completeness proof for the nice axioms. That's it. Thank you very much.
All right. Does anyone have any questions? Oh, well, Umang, if you can come up because of the recording. Oh, you will. I mean, you go first too. Thanks. Yeah.
Hi, Chris Casangino, Jane Street. As a non-expert on automata, your algorithm with the 3 steps basically looked like black magic to me. Are these steps like standard in this literature, or did you just come up with these out of thin air, or I don't know?
Yeah, out of thin air, yeah.
Thanks.
Great talk. I'm Umang Mathur at NUS, and I have a similar question. I acknowledge that it is black magic, but I'd like to sort of untangle some of the magic. Is there a more declarative understanding of what this operational procedure is doing? Like, okay, here is a language, step 1 is XYZ closure of that language, and then step 2 is this other kind of closure. Is there a...
So it is a bit difficult because so the problem here is that step 2 only makes sense if you have done step 1. So step 2 doesn't make sense on any regular language. It only makes sense on the languages coming out of step 1. So that's one difficulty. Another difficulty is that step 2 through 3 is changing the alphabet of the language totally to this paired alphabet. So that also doesn't match the traditional ways of doing reductions in clean algebra. So
yeah. So I don't think clean algebra will have an answer to what I'm looking for. I'm looking for an answer which is language theoretic or automata theoretic. So for example, could it be that maybe step 2 is some homomorphic image of step 1, that sort of thing? That step 2 is really a homomorphism of the output of on top of the output of step 1. Is there something like that?
So the way the correctness proof works in the paper is just reasoning about the operational behavior of the program. So it would be interesting to see if we can make that nicer using something like this, but we haven't done so. We just grind through the proof manually.
Okay, thank you.
Thank you very much. Sean? Perfect. It's still 40 past, so still perfect timing. So we now have Sean from Cornell University, still talking about, oh yes, the microphone. Still about clean algebras, but now with a slightly different setting, so please go ahead.
Thank you. Yeah, so clean algebras, but no test this time, sorry guys. And the real question that I'm gonna get at the heart of today is this interplay between two things, probability and non-determinism, which are both fairly straightforward, but when you put them together, they don't like each other. Okay, so just a quick overview of probability. You probably all know what probability is, but I'll just lay it out in our context here. We're thinking about probabilistic programming languages, and the idea is you want to be able to reason about probabilities, you want to construct probabilistic models and perform inference, right? So these have been of interest to logicians for a little bit, but recently came back into vogue with the advent of big data machine learning. You have these massive data sets, and it's not feasible to do anything deterministically. You want to do things probabilistically. And the way we want to think about state in a probabilistic program is you have some possible states of the world, and you think at every point in the computation, you are in some distribution over these states of the world. So your current state is really a probability distribution, and every action you take updates a distribution, right? So you take any state you could be in, that has its own distribution of the next states you can proceed to. So you get a distribution of distributions, and you flatten that into a single distribution with the probability monad. Okay. Similarly, for non-determinism, non-determinism is this idea you have multiple different things you can go to, multiple different next steps you can take at any point in time. And so we usually represent that with the power set. You have a set of possible states you can be in. And at any point in time, you look at all of the states you could be in, you look at their next states, and that gives you a set of sets, and you flatten those using the power set monad, right? So you have these two fairly basic constructs. You might want to say, okay, can we come up with a model that incorporates both of them? You want probability and non-determinism. And the short answer is no, you can't. And it's not that people haven't tried, but there's actually a pretty strong mathematical reason why this is difficult. To take two such monads and combine them in a very nice way, you have to satisfy these rules called the Beck axioms. And you get what we call a Beck distributive law. But in the past 20 years or so, so this is a result that first appeared in this Varrock and Winskell paper, but they attribute it to Gordon Plotkin in Personal Communication. And it shows that there's no Beck distributive law between the probability and power set monads. And what that means is that if you want to combine them, you have to do some kind of complicated things. Many different workarounds over the years. A lot of these, you have to incorporate more complex data structures. You need to worry about things like convex closures, or you add additional data structures to keep track of when is the last time I made a non-deterministic choice and what choice that was, so that the next time I make one, I can go back and resolve it. So this is all kind of clunky and it's not very nice, but it turns out that there is a way to get around all of this. And that is by using this Beck distributive law between the probability and multi-set monads. This is again something that's been folklore for a bit, but didn't really appear in the literature until 2021, and showed up that in then a paper by Bart Jacobs, and then also by Dash and Staten in the same year. And okay, I should briefly talk about what a multi-set is. A multi-set is like a set, but you can have repeated elements. So a common analogy is you have a bag of marbles. You don't care what order the marbles are in, it doesn't matter. And you can have multiple marbles of the same type. You can have multiple red marbles or multiple blue marbles. All you care about is what marbles are in your bag. But really, these are just functions from a base set, the set of all possible marbles you can have, to the natural numbers, how many of each type you have. And that's the way we're going to be thinking about them for most of the time. We're going to call the multiplicity of an element the number of times it appears. And the main operation for multisets we're going to be concerned with is this multi-set union or pointwise sum. If I have two bags of marbles and I dump them all into one big bag, the contents of the new bag are exactly the pointwise sum of those original contents. And in this framework, we can describe the distributive law in a pretty straightforward manner. So what this does is it takes a multi-set of distributions and it gives you a distribution over multi-sets. And the way it works is, let's think about each distribution as a biased coin or a weighted die. You have a bag full of these weighted dice. You roll each one, you get outcomes each time, and you put all of these outcomes into a new bag. So at the end, you're left with a multi-set, And this entire procedure induces a probability distribution over those possible multisets. And that's exactly the result of this distributive law. Okay? So in particular, in this example, we've got two coins, one fair, one weighted. And these two outcomes in the middle, one red, one blue, are indistinguishable because we don't care which coin flipped to which result. We just care that we get one red and one blue. Okay, so for the rest of the talk, I'm going to introduce a model of automata that uses this idea, the distributive law, to incorporate both probability and non-determinism. We're going to talk about the corresponding class of expressions. I'll give you a brief overview of semantics for both, and then we'll talk a little bit about a cleaning theorem at the end. Okay, and there is another word that appeared in the title of this talk in the previous slide that I haven't mentioned yet, and that is this idea of angelic non-determinism. So a lot of times people think about non-determinism demonically, which is where the non-determinism is resolved by some sort of outside adversary. You can think of something like an actual adversary or maybe like a scheduler, right? Something you as a programmer have no control over. And this is good for reasoning about things like worst case behavior, but yet it requires these really complex workarounds that I mentioned before. Instead, the way we're going to approach non-determinism is angelically. So non-determinism is under the control of the user, the programmer. And this is especially useful for reasoning about things compositionally, as we will like to do in the future. Okay, so let's go ahead and talk about automata. And loosely speaking, you can think of an automaton as a weighted label, or sorry, not weighted, a labeled directed graph. And our states in the automaton are going to have 4 different types. So you can have probabilistic states, where the next state you can be is given by some probability distribution. You can have non-deterministic choice states, where the next state you can be is an element of a multiset of different states. You can have action states. So each of these is going to be labeled by some input character, and their successors are going to be a single state each. And then we have terminal states. They're going to label skip and fail. And these loosely correspond to, or they pretty tightly correspond to, acceptance and rejection in your standard automaton. And we're going to impose one more restriction, and that's a productivity assumption here, which says you can't have any loops without action states. And what this really does is it takes away these sort of, if you have loops of only probabilistic and non-deterministic states, you can just run in these loops forever and not produce anything meaningful. So we just take that out of the system entirely. And there's a pretty nice interpretation of the operational semantics using this agent-based model. So we want to think about an agent driving around the automaton and recording all the action states you visit, right? So you start out at the start state with an empty string. And depending on the type of state you're currently at, you do one of several things. If you're at a probabilistic state, you sample the next state from that probability distribution and you move there. And you keep the same output as you had just now. At a non-deterministic state, what you're going to do is you're going to duplicate yourself into one copy for every element of that successor multiset. Okay? So you can have multiple copies, and you can also have multiple copies at a single state. At action states, what you do is you move to the single successor, and then you write down whatever letter you just saw, right? And you put that to the end of your current output. That's the list of directions you've seen so far. And skip and fail states, you stop computation, and if you're at a skip state, you return the output string you've written, and at a fail state, you don't do anything, you just reject. Okay, so a couple of interesting things about the behavior of agents. At any point in time, you can have multiple agents on the same state, and all of these agents should behave independently of each other. In particular, that means 2 agents at the same probabilistic state should be sampling the same probability distribution, but doing so independently of each other. And because you can have multiple agents at the same skip state, that means you can have strings that are accepted with multiplicity, not just yes or no. So the languages in this case are going to be multi-sets of strings rather than the traditional sets of strings. And you can talk about really fine-grained behavior. You can talk about acceptance multiplicities and correlations between acceptance multiplicities for different strings. And finally, the semantics of our automaton are going to be given by this elements of this space, the distributions over multi-sets of strings. Really finite multi-sets, but we won't worry about that for now. Okay, so this space, distributions over multi-sets. It is an uncountable space. You can have continuous distributions, and we'll see an example of one of those in a bit. But it's a pretty nice probability space still. It's a standard Borel space, and it's isomorphic to this infinite sequence space. And because of the productivity assumption, we have a couple nice takeaways. For one, any really long computational path has to visit a lot of action states, and this is really a pigeonhole argument. If you have very few states, there has to be a gap between adjacent states, which is very large, and then you have to have a repeated state, which means a cycle of no action states. Multiplicities can grow exponentially with string length. This is roughly the argument is if I have one copy that splits into 2, by the time they both get back, they'll split into 2 each, and you have exponential growth in terms of the number of times you repeat. More importantly, this allows us to define the semantics of our automata co-inductively. And what I mean by that is roughly the semantics of a particular state can be determined by looking at the semantics of its successors and combining them in the appropriate way. Okay, so for skip and fail, you don't have successors, so you're really just either stopping and accepting right away or accepting and doing nothing. That's those point masses there. For action states, you append your current state, your current output, you append the action that is on your current state to whatever you would get at your successor, and that's that operation there. Probabilistic states, you just take the mixture of the distributions of your successors. And in non-deterministic states, you do something a little funky. So if you think about a non-deterministic state, you have a multi-set of successors. And so their semantics will be multi-sets of distributions over multi-sets. So what we do is we apply the distributive law to convert that to distributions over multi-sets of multi-sets, and then apply the multi-set monad operation multiplication to collapse those two multi-set monads into a single multi-set. And so I don't have the full proof in the slides here, but we can show that this is all well-defined. This is there's exactly one way that this works, and this arises at the fixed point of the appropriate contractive map. Okay, so we're going to switch gears a little bit and talk about expressions now. And these are roughly going to be the equivalent of regular expressions for our automata, but we have probability and non-determinism to worry about. So a lot of these constructs are going to look very similar to the ones we just saw for automata, but we're going to have a couple new things here. For one, we're going to have variables. And so we're going to have to deal with fixed point expressions, and in order to have fixed points, we're going to need to encode those with variables. And we're going to have this semicolon, the sequential operator, or sequential composition operator here. That's something that is handled implicitly by the automata with the way that the arrows work, but it's something you need to do explicitly for expressions. And we're going to have two additional restrictions here. So one is basically the same productivity assumption as we had before, except that now we just have to have all of our fixed point loops be productive. So all fixed points have to have guarded instances of the fixed point variable. And the second is a linear recursion assumption. And this one is maybe not so obvious, but this is really the same assumption that differentiates regular expressions between context-free grammars. So free variables have to occur in tail position. That means they can't have anything immediately following them. And in particular, that means for sequential composition, we can't have any free variables in the first term. Okay, and we can define semantics for expressions as well. Semantics, because we have variables in our expressions, we need to define semantics with respect to an environment. But everything is kind of what you'd expect. The first couple are basically the same as they were for automata. When we look at a variable, you just say, what is the value of that variable according to the environment? And the others are a little bit technical, and I don't know if I have the time to get into that today, but I will assure you that everything is well-defined. The full proofs are in the paper. And they all, again, the semantics arise as the unique fixed point of the appropriate contractive map. Okay, so switching gears again. This is something you've probably seen in sort of an undergrad theory of computation class. Kleinius theorem, which states that DFAs, NFAs, and regular expressions are all equivalent. They produce the same languages, and moreover, there's a way to translate between instances of one to the others. Right, so why is this nice? Well, that means that we can reason about these objects of computation, the regular languages, from both operational and denotational standpoints. But moreover, there's sort of this heuristic argument where if I can compute the same thing from multiple different angles independently, it kind of speaks to the idea that maybe this is like something nice to be thinking about, something like is sort of not necessarily the right thing, but something that is reasonable to think about. And so over the years, people have been working on Kleinius theorems for more complicated automata and expressions. But up till now, and correct me if I'm wrong, but we think this is the first Kleinius theorem for models that include both non-determinism and probability in a compositional manner. Okay, so this model of automata and expressions that I've shown to you here, they're actually equivalent, and we have a procedure that you can translate between objects of one type to objects of the other. So as an example, we have this automaton and this expression here, and these both correspond to this process where I just take a fair coin, and instead of heads and tails, it's going to be A and B, and I'll just keep flipping it. And every time I flip it, I'm going to write down what I see. And eventually, I get this infinitely long string, but if I look at all of the prefixes of that string, that is a set of strings. And if I take the uniform distribution over all of those strings, I get exactly the semantics of both this automaton and this expression. Okay. And generally, we can do this for any such automaton and any such expression in our language. Okay, so a couple of closing remarks. We have this new class of automata and expressions that have both probability and non-determinism. Give you a brief overview of the semantics for each. Again, there's a lot more details in the full paper. And I've outlined the Kleene theorem, which shows that these are actually equivalent to each other. So in the rest of the paper, there's a whole bunch of other stuff. There's all these proofs that I kind of skipped today that are they're a bit dense, but I think hopefully are fairly approachable. There's a coalgebraic theory, which is we can view automata as instances of coalgebras for the appropriate functor. And it turns out that the usual final coalgebra diagram is not the right way to be thinking about these. We have a metacalculus, which allows us to reason about these operational behaviors in a more denotational style. And we have a whole bunch of equational axioms, which are all proven sound. We're working on showing completeness. But yeah, if any of this sounds interesting, feel free to reach out to me and, or check out the full paper.
All right. Yeah, please go ahead with the questions.
Hi, Robert Rand, University of Chicago. Really interesting talk. I was somewhat confused and also just interested in, you talked earlier in the talk, and it didn't seem to come up that much again, about angelic non-determinism. And I was concerned both about you described that as sort of the user picks as opposed to, maximally worst bad outcome where the adversary picks. And that seems like you could just model it using an if statement if the user is picking based on existing information. And also I was wondering more broadly, like, I understand demonic non-determinism because I want to be prepared for the worst case. Why do I care about angelic?
Yeah, so I think the main thing is angelic non-determinism exists within the programming language itself. So it exists as a construct of the language. And I guess the way we like to think about angelic non-determinism is you're really doing all the possibilities at once. And you end up resolving it by taking sort of the best of those outcomes. But with the agent-based interpretation, you really send one agent to every possible outcome. And all of those get sort of, and at the end, when you collapse everything, they're all represented in your final distribution.
So is it useful? Are there applications?
Yeah, so we're sort of laying the groundwork here. We don't even have the tests, as I mentioned. So that's one thing that we would like to do is add tests. And once we have tests, you have the basics that you need for a simple imperative programming language. And so in the paper, we also have an example where you can model this sort of network security example and calculate probabilities, taking advantage of this distributive law using the probability and non-determinism together.
Thank you.
Hi, thanks for the nice talk. I was wondering if the productivity assumption is fundamental, because in Markov chains, for example, it's fine to have epsilon loops. So I wondered if you can give some intuition whether it's fundamental here and why.
Yeah, so that's a really good question. And so we have a way to get rid of loops that are only probabilistic choices. And the idea is you just collapse it to what are the probabilities that I exit at each point. It seems that it's also possible to get rid of the productivity assumption in general and deal with least fixed points instead of what we have are unique fixed points of contractive maps, but that's something that we're still working on.
All right. Do we have any more questions? No? I would have actually asked you to go through that example that you said where you mix the attacker and the defender, because I still actually found it a little bit odd in the paper too. But we only have a minute left, so maybe offline. So thank you very much, I think. So I think we're doing quite good on time at 5 o'clock. For the last talk, we have Yifei Huang, who is not from Cornell University. This is from Rice and University of Southern California. So please go ahead.
Thank you for the introduction. And today we're going to talk about another extension of the regular expression, the so-called semantic regular expressions. So we're in the CAT session, so I believe most of one people in the room are actually know regular expression better than me. Like it's a very powerful tool for pattern matchings, but there are like these kind of questions that you cannot really just use regular expressions, right? For instance, like you can use regular expressions to find out all the URLs in the text file, but you cannot really tell if it's responsive or not, or maybe you can find the string literals, but you can't really tell if it's looks at the password. But there are really like other tools. For instance, like you can use a HTTP client or a LLM to decide to answer these kind of questions. So the idea of semantic regular expression is that if we can extend the regular expression to allow it to have the power of talking to an external oracle, it will be largely improve its expressiveness. So over here is that you can basically we give the ability of the regular expression to like talk to an external oracle. So once it's a simple formalism, it's actually very simple. So we're only introducing one more construction in this syntax based on the classic regular expressions, where you have this so-called refinement operator. And the semantic of it is really just an intersection of the whatever is accepted on the left-hand side, which is also a SEMRE, short for semantic regular expression. And the right-hand side is just the oracle queries, where like we're modeling this oracle as a arbitrary function, just take a query string and input string and return a Boolean value. So here it's we treat oracle as a total black box. We're not assuming any kind of underlying distribution of the input or output. So it can be anything. It can be a SQL query, it can be LLM, whatever. All right. So one thing to notice is actually this formalism allow any depth of nested queries. So basically you can. So here SEMRE is basically asking whether there's a selected name whose name also has a city in the top of it. So which Paris Hilton would be an example. And to be clear, that this is not our new idea. There's this amazing work back in 2023 where they're using semantic irregular expressions to perform data extraction. But in their paper, they're more focused on the synthesis part. Where here we're talking about more fundamental problems. That's once you synthesize this SEMREs, how you're going to really use them in the practice, right? You really want it to be able to perform the matching quickly. So that's why it brings us to the question of membership testing for semantic irregular expressions. Whether you're given a SEMRE R and the input string W, you want to like determine if W matches R. And of course, like in this algorithm 101 class, is this classic example of using dynamic programming to evaluate irregular expression. We can do the same thing over here, or you have to do just like do the dynamic programming based on the AST and there's semantics. But it's very easy to write. I mean, you can write it in the afternoon, but the downside is that it's actually not very fast. It's actually cubic time, and it doesn't stay at all. And we all know that for these classic regular expressions, we have this fancy NFA-based algorithm that runs very fast. It can run in linear time. That's actually the reason why regular expression is useful after all, because it's very fast. I mean, when you type grep, you grep out everything very quickly. So let's just do a very quick recap of the NFA algorithm. So what we have to do is just take the irregular expression and do this very classic Thompson-style transformation to the NFAs. And right now, what you have to do is just like you want to determine if there's a path from start to end that encode the same input string W. So the question here is like how you're going to determine such paths if such paths exist. And for regular expression NFAs, you can do this iterative calculation of the frontier set. And basically, you start from the initial state, and after you're parsing the entire input, you want to see if the final state is contained in the frontier set. The secret why this algorithm is very fast is that the state space is just the frontier set is just a subset of the NFAs. So which means that at every step, the burst time complexity and space complexity is bounded by the size of the NFA. So this means that to process the entire input, it only takes a linear time. And the other way of looking at it is actually where, for the frontier, we only care if a state is reachable or not at any certain step of iteration. So basically, let's say you have like two tokens like performing epsilon transitions reaching the same state. You can eliminate any one of them because we only keep any one of them. So you can basically just discard any one of them. But we'll see that in SEMRE, this is no longer the case. So I mean, since we have this very good NFA algorithm, why don't we just extend it with SEMRE and see? Let's take a look at how it really works. So just like what we did for the to the definition of the SEMREs, we just introduced a new construction to the NFA that becomes the so-called SNFA. Right now we have two new kind of nodes where like there's an open of the query queue and a close of query queue. So which basically acts like a punctuation mark, just marks the boundary of the query. So when you really enter a state, open state, and you're now starting to accumulate a query, and when you exit at the close node, you're going to discharge that query. So right now, we're looking for passes not only that is W labeled, that is input label, the path has also to be feasible. That is to say that all the encoded query along this path has to be accepted by the oracle. So how do we efficiently determine if such path exists? So let's take a look at this example. Here's a very simple SMRE. Admittedly, this is not the good SMRE you want to write, but it's simple enough for the purpose of demonstration. So this is a possible SNFA that is corresponds to it, and we have an input string over here that says mid push at 4. We know that this string belongs to, will match by this SMRE because we know Bush is a politician. So let's see what will happen if we try to like just feed this string into the as an FA, just what we did to an FA. So see over here is that at here, this state at 0, you can choose to either enter the query boundary to S1 or just stay in itself. So let's say let's say 2 different passes when we feed this string to the SNFA. There's like this yellow and blue chassis, and the blue chassis is determined to enter the query 1 character earlier. So this ends up making the two chassis is actually encoding 2 different queries, and one is like whether T Bush belongs to is a president or whether Bush is a president. So the problem here is that there are 2 actually, or you'll get different results from the oracle. It actually affects your result for your matching. So it means that when you are like doing this iterative frontier calculation, you will have to keep all these chassis, because the problem here is that right now the token will carry some context information, and if you really do it naively, you will blow up the state space, and you're not going to do that in a reasonable amount of time. So how are we going to solve them? So our solution is a 2-pass algorithm. So basically, first we convert the input string W and the SNFA into a data structure, which is so-called a query graph. That's kind of unroll the input and just we distilled out all the query structure, and then we just verify the satisfiability over this new data structure that we call the query graph. All right, so what is a query graph? So to put it simple, it's a well-periodicized monotonic increasing DAG. Well, this is not simple at all, admittedly, but I'm going to show you that it's actually very easy to understand. And it's just, you can think about it as an FA, but with the label removed. They're only epsilon transition right now. So here's an example of it. You see right now we don't put any kind of characters on the edges, but right now we put numbers on the query boundaries. Right now you have these numbers, which is actually the index of the input string, because the query graph is binded to a specific input string. So let's say we have this red passes over here. So when it's in the SNFA, we said open and close. You have to look at the labels in the edges between them. But right now, you only have to look at the substring 2 and 3 over here, because you already have them indexed in the nodes. Here, this green pass is encoding the query of the empty string, because you're looking at the substring 3 as 3. So you can see about each of these passes, it's a conjunction of the queries. And because it's a DAG, so you only have a finite number of passes, so the number is very large. But you can actually treat it as a very huge DNF formula. And this query graph is a very compact way of representing it. So first, it's that we will have to like unroll the SNFA to like get this query graph. So the idea is really that we are kind of unrolling the inputs, the input paths in the SNFA. The question over here is that each input path will corresponding to infinitely many passes in the SNFA, because we know there's like loops that is introduced by the clean start operator. But the key observation over here is that all this complication happens when you're performing the epsilon closure. And let's see, I mean, in the epsilon closure, you might like enter a path, open, close it, close it, close it, open, open, or something. But the idea is that even though there's like infinitely many of them, their behavior or the queries they ask can be actually encoded into a finite set of equivalent classes. So basically, there's like open and closes, they kind of canceled out, because there's just corresponding to a query to an empty string, and you can just pre-discharge it earlier. And eventually, all these paths can be summarized by a series of close and series of open. And this number is actually bounded by the sets of depths. That is just the way how you return the SNFA is predetermined. It's a constant. So we kind of, if we can summarize all these possible transitions, we build this kind of structure, which we'll see earlier. It's just the key component of the query graph that kind of summarize all the possible epsilon transitions to the query context change. And this is what we so-called the inter-character gadget. So over here, this is a step that's just, we build a query graph that looks like the way you evaluate as an FA. So we have this gadget that is capturing all the epsilon transitions and all the context change over them, and we kind of glue all this gadget with the character transitions. And so this is the state where you kind of unroll the input string W and form this query graph. It looks very large over here, but it's actually linear to the size of the input. So that's why we can, it allows us to perform the computation in a reasonable amount of time. So that's a phase 1. And phase 2 is how we evaluate the query graph on it. So just similar to the SNFA, we can also define the satisfiability of the query graph. So for now, we can also define the definition of the feasible path, where you have a path in the query graph, and all these encoded query are accepted by the oracle. So now the problem is that how we're going to determine if the feasible path exists in this query graph. So notice right now this query graph, unlike SNFA, it's a DAG, so we eliminated all the loops. So the good thing is that right now we can perform dynamic programming on it just by the topological sorting. And so the idea is actually very simple. We introduce some definition, but all we care is that whether we have a feasible path from all the way from start to end. And we kind of extend this idea to every intermediate node. That is to say, we want to know, we say a node is alive if there is a kind of a path that goes from the start to it with all the queries that is accepted. Well, here we use the word tentatively feasible is because at the intermediate node, you might have a path that reach to it, but there are some queries that are not closed yet. But the problem is that as soon as all the discharge query are accepted, we'll treat this node as alive. So all we have to do is just like you use DP to calculate whether the end node is alive or not. So the rule of the dynamic programming is really not that hard, especially for the start and blank and open nodes. But the tricky thing is that when you encounter a closed node, you have to basically, you're starting to discharge queries, and you have to know what are the queries you have to discharge. So you have to have a way to efficiently look up all these paired opens. And here is that along with the dynamic programming, we maintain this data structure, the so-called back reference. It's just a way of like recording what is the closest open node along each path. So the idea is that once you close something, you're going to immediately update this back reference set. And unfortunately, the calculation of it will involve a operation that just close to a Boolean matrix vector product, which eventually becomes the bottleneck of our algorithm. So let's see how this algorithm really performs. So let's assume the oracle response in constant time. Everything before the query graph evaluation is actually in linear time. We build a query graph in linear time. But the thing is that these back reference calculations brings the algorithm all the way up to cubic time. So this is a summarization of the complexity. We can actually see that for the last two columns, for the unambiguous MREs or like the non-nested cases where you don't have like two queries nesting each other, the performance is actually really well. It kind of matches the lower bound. For instance, the lower bound is quadratic because let's say you see the president SMRs before. It's like in the worst case, you have to query all the possible substrings. That's actually in the magnitude of quadratic. But since when presenting this algorithm to an advisor is that, well, I mean, we already have a good result for some common cases. Why we can't just do it for the general cases, right? So we're going to defend this result in two ways. First is like, asymptotic complexity is not necessarily always the best measurement. So let's just do some experimental evaluation. We collect this two huge set of the input data, some spam email corpuses, and some Java code from GitHub. And we build 9 different MREs with all the variants of the Oracle backend. We have 5 different of them. And we evaluate their throughput with the size of as the size of the input increases. And this is our main result, basically demonstrate how this algorithm scales with respect to the input. So let's zoom in and take a look at one of them. So the x-axis is really the size of the input, and the y-axis is the logarithmic scale of the reciprocal throughput. That's just basically the time taken to process each line. So as you can see over here, our algorithm is constantly better than the baseline. And actually, our algorithm, you can see that the slope of our algorithm is actually it's even smaller. It means that our algorithm is actually asymptotically better. This actually matches our previous analysis because all these benchmarks are actually a common non-nested cases, which is quadratic in the complexity, but the baseline is actually cubic. Also, we might be interested in the number of Oracle calls you have discharged because we know LLM are very expensive to learn, so there are some oracles that are backed by LLM. So, and we discovered that overall we make like 51% fewer of the oracle calls. All right, here's the experiment result, but we're in PLDI, we want some series result, right? So where my advisor at this point is not 100% satisfied, so let's define my result even further. We prove that doing anything better in general cases that is better than cubic time will be very challenging. So how do we usually do that? Well, we find some questions that is related to it. Remember that the bottleneck is really introduced by this Boolean vector, matrix vector multiplication. And there's one related problem to it is just the very famous problem in the graph series, that's the so-called triangle finding problem. That all you have to do is just give an undirected graph and you decide if there's a side 3 cycle, that's basically a triangle. Of course, you can write these 3 nested loops, this very trivial implementation, but it will take cubic time. And if you're doing it more carefully, you can do this. You can calculate the cube of the adjacency matrix and just look at the diagonal element. And if there's a 1 over there, it means that you can have a loop of size 3 that goes back to itself. And if you do this with fast matrix multiplication, you will be able to do this, to do triangle finding in subcubic time. But it turns out this is the best thing you can do because there's actually no known combinatorial algorithm. By combinatorial, I mean this algorithm that doesn't involve fast matrix multiplication like Strassen, because those are not very practical. And the best thing you can do over here, the practical algorithm is actually running in cubic time. So what we have to do is just like link this problem to our problem. And the idea is that if we write out the graph like this, and all these 3 vertex tuple can be actually witnessed by ABC over here. And if we linearize the graph into a string like this, you can actually find all the 3 vertex tuple in this string as a substring over them. So all you have to do is just write a SMRE that looks for the substring where it is corresponding to a triangle. And it's very easy to do. All you have to do is just build an oracle that's just test if the 2 vertices are connected or not, and build this SMREs that basically you're looking for if the AB is connected, BC is connected, and AC is connected. Notice that this SMRE is a general case. It's a nested SMRE. So right now all you have to do is feed this input to this R triangle, and you will determine the membership for it. And if you can do this thing, anything subcubic time practically, you're actually solving the triangle finding problem. So that's why it's very hard to beat the general bound. Okay. So the conclusion, to summarize, we formalize this idea of semantic regular expression. We present these 2 passes algorithm that based only NFA, and it's practically working very well, and we prove a hardness result for the general cases. And you can find the artifact in the QR code, and thank you for your listening, and happy to take any question.
Thank the speaker. All right, does anyone have any questions? Really? Well, I have a question. I have to have a question. I'm a sessions chair. Oracle, huh? Database, I understand, but LLM, remember you had examples? Mm-hmm. That's non-deterministic, is it?
Yes. So, yeah, you're right. I mean, it's not deterministic. So in our evaluations, we kind of frozen the result produced by the LLM. So basically, once you produce it, the result is cached, and it's frozen over there. But yeah, indeed, this is a very good observation, and because the result by the LLM is just a distribution of the output token. And one natural future question is like, what if you have the oracle returning a distribution of the output, and then the membership testing will be a probabilistic problem? And this is actually one interesting question we're looking at right now.
Cool. Oh, thank you, Julian.
Is any non-trivial lower bound known on triangle finding if you're allowed to do anything?
What do you mean by if you're allowed to do anything?
Like you are allowed to use Strassen, for example, or any algorithm you can think of. Is there a non-trivial lower bound in this problem?
So I think it's like if you restrict the type of graph, for instance, if the graph is sparse or something, you might have a better lower bound. For general graph, you don't have any restriction of the graph, I think you can never do anything subcubic without using fast matrix multiplication. So right now, the lower bound is just the fast matrix multiplication in general cases, but those are anything subcubic will be very impractical, right? Those Strassen-like approaches.
So is there anyone who has proved that you cannot do it in linear time, triangle finding?
the graph is already cubic. The resistance matrix is already cubic. It's quadratic, so of course you cannot do it in linear time.
Another question I had is experimentally you show the slopes.
Mm-hmm.
Do those actually correspond to your worst case bounds, or is that
Yeah, it actually corresponds to our worst case bound because here the benchmark are no nested query. Those are quadratic, and that matches our observation.
Thanks. Very nice talk.
Thank you.
Hi, I had a quick question about space complexity. Do you have any theoretical results, or maybe even experimental results, about how much space and memory this takes up?
I don't think, we don't really have evaluation on it, but I think the space complexity is just more or less the same as time complexity. You don't really have to, store a lot of information I mean, you have the query graph, that's the largest thing, but actually you can represent it in a very compact way because the gadget is kind of duplicated. So I would say it's actually, the space complexity will actually be linear to the size of the input, yes. Or maybe some intermediate state DP might go to quadratic, but it will never be cubic. Yeah, I think.
Thank you. Thank you.
So this may be a dumb question, but I think you mentioned during your talk that you assume the oracle call is 01. I wonder if, because like you also mentioned like oracle can be larger than models, I wonder if you can do some analysis that assumes that the oracle call is actually very, very expensive. You want to minimize that. Yeah,
that's a very good question, and that's actually our subsequent work. Of course, if you have backend like, usually, I mean, initial work have their backend as LLM, which are super expensive to call. And actually, if you really run things well on backend, you will see the bottleneck is actually LLM itself. So it's very natural in that case to like replace the 01 with the actual complexity. But in that case, we're not talking about a black box oracle anymore. You have it's actually a gray box or a white box because right now you have access to the distribution of the tokens in LLM or some like the query structure in the SQL query. Over then, you can do like case-by-case optimization to the algorithm. But yes, that's a very good future direction. But this paper we're only focusing on black box oracle, so we cannot make any assumption on it.
Thank you.
Well, thank you. Let's thank the speakers. Thank you very much. And I think this concludes the session. Only 4, right? That's it. So I actually don't know what's going on tonight. I think there are some special dinners. I'm not the general chair. I think if you have on the program, I think there's women's dinner. There is some other events. So just watch out for it. Oh yeah, poster. Poster, is it now? At 6. Thank you for whoever is looking at the program. At 6 o'clock there is posters. Please go there. Check your program. Thank you.